Hello, guys. How we doing? Hello, guys. Oop. Hi. I've got. I made a PowerPoint. But I'm not going to be using the PowerPoint. I'll send the link in chat if you want to follow along. It's just kind of a guidance of what like what I need to cover. So that's for me. But I've got questions on here. Not all of the questions have mark schemes, so I'm going to put a link in the chat if you want to follow along with the PowerPoint. Some of the questions have mark schemes, some of them don't. Um, yeah, it's just kind of like a guidance for me to say, okay, we're going to be doing amines first. We are doing amines first. But yeah, cool. I really wanted, I really want to cover practicals today, just because I don't think we'll be able to in terms of the amount of content there is, because it's more or less all of it organic we're doing today. We'll be doing chromatography as well, right at the end. However, if just in case we don't get through the practicals, these are the three practicals I'm going to make a prediction on that are going to come up, potentially even a 6 marker. Yes, Rico. One of these I think is going to pop up. Yeah, either one of these. Potentially even chromatography as a 6 marker, or polymers and DNA they're going to make as a 6 marker. That's my prediction. If they're really nice, you might even get ion testing or like mechanisms. That would be like amazing. But this is kind of my prediction in terms of 6 markers. That's going to pop up. But the main focus will be on organic. If we get through everything, great. If we don't, then that's just something to know. Oh, there's chromatography. Chromatography is right at the end. To be honest, I think chromatography is made harder than it should be. I think once you've got the hang of it, they're all more or less the same. And even gas chromatography, I think, is all right. I'll show you kind of how it works. So we'll go through that. All right, we'll just wait like maybe 2-3 more minutes and then we will start. Let me check on TikTok as well. Hi guys on TikTok. This is for AQA. We'll be going through. So when we do HNMR, I'll mention the OCRA stuff. So I know that OCRA for HNMR looks at D2O, and there's a very slight difference that you don't look in AQA. So don't worry about it, I'll mention that. But mostly yes, it is AQA. We won't be looking at phenols in benzene, so we'll be going over like the benzene mechanisms and stuff. But we won't be going over phenols. Rates, again, we are doing rates, but we're not doing half-lives for the guys doing OCR, so sorry about that. But a lot of the stuff that we do today will transfer over to OCR. Okay, so guys on TikTok, if you want to come over to YouTube, just because I'll be looking at TikTok here and there, but most of my replies will be from the YouTube chat. So if you go to the link in my bio, the link tree, just click that, go to the YouTube chemistry session, just come there. It's not only exam questions, no. We're going to be literally just going over the content. If we go over the exam questions, there's no point. Yeah, I'll resend it in the chat, Ali. There's no point if you just do exam questions. So, for example, this is just kind of a guidance for me, what I need to tell you guys, and I'll tell you in the most easiest way possible for you guys to remember. So if you guys came to the paper 1 revision, you already have an idea of how we do this. Okay. All the content will be hard. Plan is 4 hours, 3 till 7, whatever we get done. So last time I did run over a bit. It was like we ran over like 40 minutes, which was fine. I didn't mind that. I'll try my best to cover as much as organic as possible. This is the plan. Hopefully, we'll be going through all the mechanisms. So I know I didn't say mechanisms here, but within the topics we'll be going through the mechanisms. The mechanisms will be your foundation for organic testing and your synthesis stuff. So I'll tell you how you can literally bang every single mechanism. In my opinion, they're 3 marks. Let's start at 3 or 5. And yeah, appreciate it, Anya. Appreciate it. Tilly, I'll put it in chat. If you guys, that's the name of the YouTube channel. But if you go to my bio, it will be there. You can just click it directly from there. Okay. All right. Let us. Bye, guy Rico. Let's start. You know why, Amma? It's because it was psychology that day as well. So I think most people are doing psychology revision. That's why. Yeah. All right, guys. You guys are locked in, yeah? Let's start. I'm not going to be using the, I have the PowerPoint on the side, there's like guidance for me. I'm going to be using my OneNote stuff, just because it's easier to draw. Last time it was glitching. Alright, let's start on amines. Okay, first thing we're going to start off with really is being able to name amines. Okay, you're going to have different types of amines. I'm going to draw a couple on the screen. Okay, and essentially this is going to be testing your IUPAC stuff. It's a good, nice warm-up. I'm just going to draw it. I'm going to try to draw in skeletal. If I draw in displayed as well, that also works. This is the easy one. Yes, you guys will hopefully cook with this session. All right. What is the name of that? What is the name of this molecule here? Let's start with some IUPAC stuff, and then we're gonna transfer over to like the normal stuff. We're gonna finish at 7 p.m. Hopefully. Last time we ran over a bit, but yeah. Come on, yeah. We're pushing 100. We have 86 on TikTok as well, so it's really good. If you guys on TikTok, if you want to come on to YouTube, it's just easier for me to reply. Just because I only have 3 screens. Only 3 screens. On my front one is my YouTube one. On the right is going to be my PowerPoint one. And then my down one is my graphic tablet, which is for my writing. Okay, so first of all, easy naming. How many carbons do we have in total? We have 1, 2, 3. If you're unsure on how to name them, draw them in displayed. Okay, we have 3 carbons here. Okay, draw this in displayed, and that's completely fine. Okay, this is 3, so this is going to be propan. Cool. However, it's not an amino. I know why you're saying amino, Tilly. However, this group is an amide, so we call this propanamide. Okay. Yes, my ear's being recorded. Yep. It'll just get automatically posted on YouTube like last time. Yeah. Great. Propanamide. You need to be able to recognize your group. So the difference between amines and amides is when you have a direct NH2 connected like this is an amine. So in this case, because we have 2 carbons, we would call this ethylamine. Or even if you call this one amino or ethane, that is also acceptable. Okay, both of these are acceptable. Where you use amino is really used when you have a branched chain. So if, for example, if we had NH2 like this, then we would call this amino. However, if it's on the end of a chain, it's NH2. But we'll come back to that later on. Okay, we're going to continue to look at some more amides first. We're going to look at the naming first, and then we're going to come back and look at making the secondary, tertiary, and quaternary amines. Okay, I'm going to draw another molecule, like so. This one's slightly trickier. I don't think these type of questions will not come up too much with this type of molecule anyways. Give this a try. Okay, how would you go ahead and name this molecule? Does that amino acids have, yes, Friedel, yeah. But this is not amino acids, this is amides first. So this is amines topic. Danny, if you go to my bio, there's a link tree, click that, and then you'll be able to click the chemistry live session. But if you're unsure, just type in Studies for Your Tutors on YouTube, you'll find it. Okay, amazing guys, amazing. So it's going to be 2-methylpropanamide. Why? Because we have 1, 2, 3 carbons here. Now, be careful how you name it, okay? Your naming does not start from this one here. It actually starts from your priority group, which is this. Okay, so you guys are saying 2-methylpropanamide, which is fine, okay? If I drew another carbon here, this will still be a 2-methyl group, because our priority group is this here. Yes, RS, you're correct, yep, because it causes it to become an amide. So this double bond O and N is an amide group. Okay, in this case, because I drew another carbon, this will still be 2-methyl. I just added another carbon, guys. So that's going to be 2-methyl butanamide in this case. Okay, make sure your priority group starts from your carboxylic acids or amides or even nitriles. If you have a suffix at the end, so for example, if I draw an aldehyde in this case, your priority group is this. So your carbon, this will be your carbon 1. Okay. Careful, it's not one amino, this is an amide. Okay, if I go back to the one we had originally, it would be 2-methylpropanamide. Okay, cool. How do I know the priority groups? Anything that's on the end. So your aldehydes, your nitriles, these are all priority groups. Your carboxylic acids, your suffixes. So butanoic acid, propanone, or even actually propanone would take a priority group as well. Actually, propanone. What else is coming to mind? Alcohol is kind of like down because it can get turned into a hydroxy. So this would, for example, if you had an aldehyde, this would be a priority group. So this would be carbon 1. This is carbon 2. In this case, what would you call this? 2-hydroxy. How many carbons do we have? 3. That's going to be propanol. Does that make sense? Okay. Cool. Let's go to the next amide. I'm going to draw a similar one to before, but this time it's this. What is this called? In fact, there should be a H up here. What is this? Can you help with making compounds cyclical? I know OCR does that a lot. I'll briefly check over that when we do the amino acid stuff. Okay, so just remind me on that. I'll make a note of this on the side. Let me put that in amino acids. What makes an amide an amine? Not an amine. It's because of this double bond O. Amazing, guys. Amazing, amazing. Good. So how do we call this N? Why do we call it N? The reason why we call it N at the beginning is because this is an N substituted amide. So your original, we had NH2. But what happens is one of the H's gets substituted out for a methyl group. If you're unsure, draw it displayed. We have 1, 2, 3. 3 carbons here, so this is going to be a proper. We have an amide group, so we call this propanamide. Propanamide. And then on the N, on the nitrogen, what do we have? We have N-methyl. Amazing. What if I went ahead and changed this to this instead? What if I did that? If you have questions, guys, make sure you guys are answering. Okay, asking. Okay. If you have 2 methyl groups, what would you call that? It's a very, very slight difference. Okay. Some of you have made this mistake. Now, this is what we would call this. We would call it N-dimethyl. So every single time you have a substitution, we just add another N. I know it's weird. We call it N-dimethyl propanamide. Okay, because we have this extra methyl group, it's just on the other end. If I added another carbon here, now how this changes, it's not N, comma N anymore because we don't have a dimethyl. What we have to do instead is we refer to this as our ethyl group. So we would have N-ethyl, then N-methyl. Make sure you're writing it in alphabetical order. E comes before M. Do not put N-methyl, N-ethyl. That's wrong. N-ethyl, N-methyl propanamide. Okay, if you have 2 different functional groups like this. Okay, that is your naming of your amides. Cool? Alright, let's start with creating secondary, tertiary, and quaternary amides. Okay, to start off with making secondary and tertiary, or yeah, the difference with this, actually, you know what, let's not even start with this first. I'm actually going to write this down. CH3Br plus XS ammonia. I want you guys to write down the mechanism for this. I'm going to give you guys about a minute. Okay, and there is also a condition with this. If you know the condition, write down the condition. Thank you, Anya. Thank you. It is a nucleophilic substitution. And then we will start with what the difference is in terms of amines. Thank you, Liam. Yes, this is AQA, but these transfer over to Edexcel and OCR. Good, Kylia. It is ethanoloic. That is your condition for this. Okay, and it needs to be excess as well. That is kind of your condition as well. Okay, good. That's even better. Warm and reflux. That is even better. In terms of mark schemes, though, to be honest, they're mostly looking for ethanoloic. But if you did put reflux, that's even better. Okay, we're going to be doing HNMR way later on. Okay. All right. I'm going to start with the mechanism. It's good to go ahead and draw it and display it. I'm going to put H3C here for now. And then we have a Br. Actually, no, I'm not. I'm going to make it displayed. H and H. All right. Now, the first thing we have is our ammonia. So I'm going to bring in NH3. And this rule, I want you to, Isaac, you can say dissolved in ethanol. Okay, Ali, I'm about to explain that. So, this is the rule I want you to follow for every single mechanism. Okay, negative to positive. This is going to help you a lot. For mechanisms that you never ever see, because they do this in AQA a lot, sometimes they give you a mechanism and they're like, finish the mechanism, use this rule. Negative to positive. What does this mean? This essentially means you're going to draw your arrow from the more negative area to the more positive area. In this case, we have a delta positive on our carbon, and we have a delta negative on our bromine. I'm going to draw a curly arrow from my lone pair, which is the negative area, to the more positive area. Cool. And then what we're going to do, yes, it's going to be uploaded. It'll get uploaded straight away. And then what we're going to do here, again, we're going to follow the same rule of negative to positive. Well, your bond is actually really, really negative. Why? Because the covalent bond has electrons. In relative to bromine, bromine will be the more positive, so bromine gets knocked off. And we create an intermediate like so. We're going to start off with the basic mechanisms anyways, and we'll get towards the more complicated. We're going to go through every single mechanism anyways, hopefully. But yeah, okay. We go ahead and swap out the bromine for the ammonia. Now the issue here is we have 4 bonds on nitrogen. We have 4 bonds on nitrogen, and nitrogen is in group 5. How many bonds should nitrogen have? Only 3. Okay, so because of that, that causes your nitrogen to have a plus. Now, how do we get rid of that? And that's why you have this excess ammonia. Now, your excess ammonia, another ammonia comes in, negative to the positive area, negative to the positive area. That's your whole mechanism done. Most of the time, you don't even have to draw your final molecule. But for the sake of this, I'm going to draw the final molecule, CH3NH2. That is your final molecule. Okay, I'm going to be doing NMR way later on, guys. Okay, that is your final molecule. And what is our side product? Well, our side product is because our NH3 takes on this H. What happens is it becomes an NH4 plus. And we have a Br minus. Well, that's your side product, NH4Br. Okay, so for every single halogen you have to use 2 ammonias. Sometimes what they can do is tell you, write down your equations. So they're going to tell you, you might have to just write this down. So if you do CH3Br, you need 2 ammonias. And that makes your final product. And also your side product. Does ammonia here acts as a nucleophile. This is a nucleophile. Oh, no, it's not going to be HBr. Ammonia acts as a base. Does it act as a base? In this case, I would say yes. Because it's taking the H+. So here it acts as a nucleophile. Here it acts as a base. Okay, it's not going to be HBr. It's not going to be HBr, guys, because we have an NH4 created from here. NH3 bonds to the H, which makes an NH4+. Your Br from before is going to be Br. Your side product has to be ammonium bromide. Cool. AlCl3 is for your benzene stuff. Either is fine. If they tell you to make an equation, if you put positive and negative, you still get the mark. That's fine. Your observation, there's not really an observation for this because it's just an amine. You might make a salt, I guess. This is probably going to be all in aqueous solution. Okay, all right. Let's move on to, I'm going to make the same equation. CH3Br. And this time we're going to have excess of our haloalkane. And we have ammonia. Now, if we do this whole mechanism again, like we did before, the first thing we're going to make is this. Do you guys agree with this? Okay, this is the same molecule as we made here. CH3NH2. Right? But what happens is because we have excess of our haloalkane now, we're not going to make the same thing anymore. So this is an amines topic now. Okay, this is your year 2 amines. Good, HM, we do. So now what we have with this is that this acts as your new nucleophile. You don't need to know the mechanism for this at all. So you don't need to know the mechanism for this, but I'm going to show you the mechanism, and then after that, I'm going to show you the quick way of doing it. So, because this acts as our new nucleophile, I'm going to draw my excess of this. So I'm going to draw another one of these. And it kind of just happens the same way. Negative to our positive carbon, negative to our more positive bromine. And then what happens is this Br goes away. Yes, I'm Melville. This Br goes away. And then the CH3 will attach on to this nitrogen. So we end up with CH3 and H and H and a CH3. But just as a problem as before, we can't have 4 bonds on nitrogen. It becomes a positive. One of the H's pops off. You don't need to know why. It just pops off. This is our secondary amine. You might start to see a pattern now. You're seeing the CH3s that are attaching on. One of the H's got replaced for the CH3. So what we're going to do is take this other H, and that continues to get replaced. So that makes your tertiary amine. And then in terms of your quaternary ion, why does it make a quaternary ion? Because it still has a lone pair. So it can potentially, you guys don't need to know this for OCR, by the way. You don't need to know about quaternary ions for OCR. But up to this point, this is for OCR. This part's AQA. You can make quaternary ammonium ions. And you need to know, because it has 4 bonds, this is going to make a positive charge. Why? Why does it do that? It's because of the lone pair. Every single time you have 3 bonds on your nitrogen, you have a lone pair. So this reaction just happens again. And then the H gets swapped. This reaction happens again. So the H gets swapped. And every single time, you would add on that chain. Does that make sense? Guys on TikTok, if you want to come over to YouTube as well, in my link in my bio. How do you tell if it's primary, secondary, tertiary? Good question. It's just the amount of carbons you have. Think about your carbocations and your major products. Look, this has 1 carbon, so this is going to be primary. This has 2 carbons attached to the nitrogen, so this is your secondary. This has 3 carbons, tertiary, 4 carbons, quaternary. You should be fine if you put the positive like so. I have seen mark schemes where they do allow this. You should be fine if you did this. How would you name this? Good question. You would call it, because it's an ammonium ion, you never ever asked about it, to be fair, but it would be tetramethyl ammonium. But usually what happens is, because it's an ion, maybe there might be a chlorine, it might be a bromine, doesn't matter. So you probably make a salt with this. Tetramethyl ammonium bromide. For this, the skeletal formula, pretty simple, to be honest, because each carbon is 1. We have 1, 2, 3, 4 positive. Cool. That's it. I'm gonna give you guys another one, and I want you to try go ahead and make me the tertiary and the quaternary amines for them. To be fair, Zara, that's the 1 marker. I was about to mention that. I'll mention that after we do this. But actually, you know what? Instead of doing that, I want you guys to use CH3CH2Cl, excess of this, with ammonia. And I want you to make an amine with the molecular formula of C8. You can probably guess now what it's going to be, though. If you want to start already, you can start. 20N. Okay, I want you guys to make a molecular an amine with this, and then if you know your 1 marker, what is the usage of that? What time am I going over NMR? I have no idea. I'm going to be honest. Maybe in like 1 hour, 2 hours. Where is HNMR? About an hour, I'd say. Okay. Is the same conditions for excess? So you just put excess. You normally even not.
You just excess of your haloalkane. That's the only thing. Ooh, it is not. Manufacturing dyes is for your phenylamines. Good. Surfactants. Good. Don't have to use cationic. That's a very, very nice word though. If you put that, it's better. Surfactants will get you the mark. Where can you get the slides? This is on my OneNote, so everything I'm doing is from my head, really. But you can use the slides, kind of follow along. It'll just say amines. I'll put the link in the YouTube chat. So yeah. When doing nucleophilic substitution, how does NH3 turn to NH2 if it's not in excess? Are you talking about... okay. So excess essentially just means that you have more of this. Ali, it just means you will still have some NH3s. In reality, you're not just going to have one single ammonium ion. Okay, you're not going to have one single ammonia ion. You're going to have maybe 2, 3, 4, but it just means excess just means you have more of this. Okay. What is a specific molecule that is a surfactant? Well, that's the question. Would the other product be 3Cl minus? You will make your ammonium chlorides. Your other side product will be ammonium chlorides, because as Ali said, there will be some NH3s that are flying about, and actually you will probably make some. You'll make ammonium chlorides as your side products, but you won't be asked about that. I've not seen a single question ever in AQA, anyways. I've seen it in OCR actually, but in AQA, you've never seen it in the question about making an equation with it. Okay, all right. Let's start with this. I'm gonna start with the mechanism again. So, when you react CH3 CH2Cl with NH3, just as your nucleophilic substitution, this will go to a CH3 CH2 NH2. Cool. Now, what happens is this will make. I've just separated it out like this. Actually, you can see that each of these are H's, and on this nitrogen you have one CH2 CH2 group. Now, to make it really, really quick, because we're just reacting it with the same molecule again, what you can do actually is just copy across that same chain. CH2 CH3, CH2 CH3, CH2 CH3. That is a really, really quick way of doing it. Now, to confirm what type of amine it is, I'm going to go back. Always look at your molecular formula, because I've seen questions like it. Okay, oops, yeah. I've seen questions like it, and it says C8. This will help you decide how many chains you're having. So if in the beginning we have 2 chains, and now we suddenly have 8 carbons, what are we doing? We're timesing by 4. So essentially you have 4 of those chains. That means this must be a quaternary ion. Does that make sense? And make sure you put your plus charge on. Okay. Sometimes it might be a tertiary, and it will refer to you. It will refer to it with the molecular formula. How would you name the quaternary ion? In this case, this would be tetraethyl ammonium ion, really. Yeah, of course. I'm going to go back. Let me do this mechanism again. Okay. 1, 2. This is your Cl. Okay. Yeah, 100%. You're allowed to skip. You're not getting marks for the mechanisms here, guys. You're not getting the marks for the mechanisms. You're only getting the marks for putting the quaternary ion. That's it. So what I'm doing here is showing you the method of how you can go ahead and figure it out, because it's better to understand rather than memorize. Side product would be an NH4. NH4Cl, yes, shush. So what happens is, bond breaks, this comes off, and what we're left with is the NH3. Okay, same thing as before. The NH3 comes in, swaps it out. This becomes an NH2. This is just same thing as your nucleophilic substitution as before. But what happens now, because we have 3 bonds on the NH2, this is a lone pair on the nitrogen. So what we need to do, because originally we have excess of this is now going to act as your new nucleophile. So you have 1, 2, you have Cl here. This goes ahead, attacks the carbon. The Cl pops off. What we're left with, this essentially just joins on. Guys, you don't need to worry about the name of the quaternary ion. I'm going to be honest. It is an amines, Bani. NH4Br is a it's not really an ion, it's a ionic lattice because it's ion bonded together. Okay, then we do the same thing. Because we have 4 here, one of the H's will pop off. Why? Because you have 4 bonds. You can't have 4 bonds on a nitrogen. Well, it doesn't want to. So what happens? This is a lone pair. Again, same thing happens. We bring another CH3, Cl, carbon, carbon. This attacks it again. Cl pops off. What happens? This will just bond on the bottom. You can start to see the pattern now. C, C. Okay, you're 100% M. Go ahead and do your papers. They're really going to be helpful. And then again, we don't want the H because it's just a lone pair. OCR people, you can stop here. But for the AQAs, you will have a quaternary ion. So what happens is it still can actually bond to another. So it goes and bonds to this. Boom. This pops off. What do you make? Another 2 C's. You can see the pattern here. Once you spotted the pattern, you just put on the chains. Okay. Yes, you're right. It's to do with your positive inductive effect. It is. We'll go over that in the amine stuff. The basic stuff. Okay. How would you get asked about this? Good question. So I do have a couple questions for that. So we'll have a bit of a practice. But this would be your quaternary ion. No, you don't know. You don't need to know why the H pops off. But if you really want to know, it's because of your NH3. Okay. Yes, Doddle. Surfactants, they're kind of like your conditioners, detergents, that kind of stuff. Okay, but anything that foams up. Okay, this is the usage of your quaternary ions. About an hour, potentially, easy. Alright. 1 second, guys. Okay. Let's look at this question. Yeah, I think this is a good question to look at. This is from a past paper. This one's alright. I think you guys can do that pretty easily. This one I think you can do pretty easily. I want to show you this part here. This is specifically in terms of the context, in terms of amines. Okay, we have when reaction for. I'm going to skip that part 1. Okay, you can see that 1.4 is asking us when reaction 2 happens under different conditions. So at the moment, this is just making an amine. This is your nucleophilic substitution. Now what happens is your molecular formula of C9 happens. C9H21N. Well, in our original, we only have 3 carbons. So this is not going to be your nucleophilic substitution as before. Instead, this is your excess of your haloalkane. So it's not really asking about your conditions in this case, but what it's asking in terms of what type of amine is this? Well, just by looking at the formula, we have 9 carbons. What do we do to 3 to get to 9? We multiply by 3. So chances are we're going to have 3 chains of those. So it's going to be tertiary amine. I want you guys to try draw this, and then we will look at this. This is for AQA. But if you guys are doing OCR, I will mention which is OCR relevant and which is not. Okay. But this tertiary one will be. So give it a try. Yeah, I'm live on YouTube, so if you want to come to YouTube, from my link in the bio, hop over. Classification, yeah, Ava. Primary, secondary, tertiary, quaternary. That's what it means. Okay, an easy way to do this is connect your N in the middle and then just stick on the chains of the carbons that you have. This is from 20. I'm making this up. I can't remember. 2019 or 2022, maybe even 2021. I actually can't remember. I'm sorry, Zara. You don't get how it's tertiary. That's fine. That's fine. It's because we have 3 chains. So what happens is we have a nitrogen in the beginning. How do we know it's tertiary? Yeah, of course. So we have 9 carbons here. I don't know if you guys can see that. Let me slightly zoom in. We have 9 carbons. But in the beginning, we have 3 carbons. What do we do from 3 to get to 9? We multiply by 3. So it's really about having 3 chains of them. Okay, that's what makes it tertiary. And you can always check the molecular formula at the end, but that's what makes it a tertiary ion. Sorry, a tertiary amine. Does that make sense? If it's 2C bonded to N, it's secondary. Yes. Okay. So we were looking at this amide stuff. That's what makes it a primary, tertiary, a secondary, and a tertiary ion. Does that make sense, guys? Of course. In terms of skeletal, Start with your N in the middle. How many carbons do we have? This should be CH2, CH3. How many carbons do we have? Well, we have 3 carbons here. 1, 2, let me try and make it nice. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, each vector, or each point is a carbon. What's the difference in conditions is that this is in excess. Lone pair you don't need to mention in skeleton now. Don't need to. You don't need to put lone pair in this. You're calm. Okay, since it's not a mechanisms question. The difference is in this is excess haloalkane for your secondary and tertiary. You just put it excess. They'll tell you it's in excess. Or if it's a question in terms of this context, you look at the molecular formula. Okay, it's told you that's under different conditions, and you make this compound. Okay, all right, let's move on. When will it become a salt? When it becomes a quaternary. That's when it becomes a salt, Joel. Okay, when it has 4, it gains a positive charge, and that's when it becomes a salt. All right. It depends, Ibrahim. It depends. It depends on the molecular formula. The molecular formula will tell you everything. All right, let's move on, guys. We're going to be looking at bases. Next part is your bases. Don't need to worry about the naming, but in this case, this is going to be tripropylamine. Or actually, NNN tripropylamine. Okay. Bases. We got ammonia as our middle base. We have some sort of alkyl groups, which can look like this. And we also have benzenes. Benzenes are your weakest base. If you ever see a benzene, automatically you need to think this thing is weak. Okay? Out of the 3, this one is your strongest. However, this doesn't mean it is the strongest base. Sodium hydroxide is way stronger than all of these. Okay? Do not confuse with the fact that just because this is a stronger base, that it is the strongest base. Does that make sense? Alright. Let's start with, I'm going to start with this one here. Because I think this is a good one to start with. So why is this a strong base? And this is the exact script that you're going to need to write down. Okay? First thing first, we have alkyl groups on this. And alkyl groups just mean the carbons. Okay? Because electrons are clouds, back in year 1 you learned that electrons were essentially an electron cloud. Okay? Essentially what we have is the carbon groups, they push electrons onto the nitrogen. Why? Why does this happen? If you go into the periodic table, let me pull out the periodic table real quick. It's to do with your electronegativities. 1 second. Let me take a screenshot of this. Now, I know carbon and nitrogen, they're very, very close together. Actually, next to each other. But nitrogen is more on the right. It's more electronegative than your carbon. So what happens is, the carbons, they donate electrons to the nitrogen. How would I name this amine? Of course, 1, 2, 3. This is propylamine. Okay. Or you can even put 1 amino propane. That also works. Then, what happens is, your electrons, or actually, before you move on, we call this the positive inductive effect. Yes. It's better to. Okay, I would advise that you put this term every single time. Next, what you've got is, because we have a positive inductive effect, electrons, or the lone pair of electrons on the nitrogen, become more available. Need this exact term, become more available. This is the main thing. Okay, and that just means it's more of a stronger base. Okay, the definition of a base is that it takes in protons. It becomes more available. You have a lone pair, you have more electrons. This area is more negative, so it can attract your H pluses. For nucleophilic substitution, yes it is, Shah, yes it is. We were talking about amines here. So this is when you have excess of this. That's a different condition. Okay, go back a little bit, and you'll see. More available to essentially just bind to H pluses. It becomes, you have a more negative area. Okay, they become more available to act as a base. So if you have more electrons, if you have more electron density on that nitrogen, you have more negative area. right? If you have more negative area, well, chances are you're probably going to bind to a H plus because it's a stronger attraction. That's what a base is. Does that make sense? Or aqueous and ethanolic. It depends. It depends. Some art streams they say reflux. The key thing is ethanolic and excess. Those are the key things, Sha. All right. Am I covering biochem? I'm going to be looking at amino acids briefly. I won't be looking at primary, secondary, tertiary amines. Is there a positive inductive effect because of different electronegativity? It's because, yes and no. It's more to do with the amount of carbons you have. Okay, so the carbons essentially push on towards the nitrogen. And because nitrogen is more electronegative, it attracts it more. Okay, yes, let's look at the benzene stuff now. So this is going to be the weaker base. The higher the positive inductive effect, the more stable it is. The more stable, not less, more. Now in this case, this is the complete opposite. Your cloud, or the ring here, this is going to be your delocalized electron ring in the benzene. And it has a high electron density. What happens is it takes electrons from your nitrogen. So electrons are pulled in from the nitrogen, and this is essentially called your negative inductive effect. What does that mean? That means there are less electrons, or less electrons available on the nitrogen, therefore weaker base. Yes, SN, there will be a, because the spec hasn't changed. Okay, cool. Now what you can have is questions on, oh, by the way, your ammonia in the middle is just there for vibes, or you can just compare. You want to compare your base and you want to compare your alkyl group here. Okay, how would we name this, by the way? We will call this phenylamine. Yeah, this would be less stable, or less basic, we should say. Don't say less stable, say less basic, because we're talking in terms of bases and pH. That's why. It's because it's just an electron ring. Okay, benzene just acts like this. Yeah, of course. Or this is linked to your OCR stuff. You'll see this in OCR. Now, you'll see questions as well. Surfactants are basically like stuff that forms up, like conditioners, shampoos, detergents. You'll see questions. Actually, in fact, I'm not going to draw it myself. I do have a question here, which I'm going to refer to. Let me bring it up. This question right here. Boom. This question came up in one of the past papers, and I think it's a really, really good question. You can see that every single one of these has benzene. Yes, benzene is a weaker base. Am I covering naming aromatics? We can do it like we're doing here in a second. Okay, so this essentially has all the weaker bases, but we still need to compare it. Can you guys just look at this and tell me which would be your weakest base and which would be your strongest base? Thank you, BMZ. F is strongest. G is weakest. Okay, we have G is weakest. We have E is weakest. Okay. All right, we got a difference of answers. All right. So the weakest one is actually E, and the strongest one is F. The reason that is because of how close your nitrogen is to your benzene ring. At the moment, this is going to be your weakest, because there are no alkyl groups on the nitrogen. This is going to be your weakest. Why is it that this base is stronger than E? Let me make a little. There we go. Why is it that G is stronger than E? It's because there are still some electrons being donated towards the nitrogen. Yes, some are being taken away, but some are going towards the nitrogen, so it becomes a little bit stronger than E. It's a bit more available than E. Okay. However, F, yes, it still has a benzene. Yes, it's still weak, but this time the ammonia is furthest away from the benzene ring, so they're donating towards the N. Okay. If you're going to talk about this in terms of 6 marker, talk about both positive inductive effect and negative inductive effect. Okay, this is how you would probably talk about this. I would probably talk about E being the weakest. Okay, so it has negative inductive effect due to delocalized electron ring. So electrons on nitrogen less available. And then you just say the same thing in the opposite way for F. Is it a predicted area? Potentially, I think amines always comes up. Has more positive inductive effect and less negative inductive. Talk in terms of context. Talk about your nitrogen and electrons and availability. Okay. And then F is your strongest base because you have positive inductive effect because there are more alkyl groups. Okay. And you also want to talk about the fact that nitrogen, because this has alkyl groups, nitrogen is furthest away from the ring. Should probably say delocalized ring. Okay. Therefore, electrons more available. Therefore, stronger base. Cool. This is AQA, but this is not good for AS. I can't lie. You don't look at this AS. Inductive effect. Essentially, inductive effect is the electrons being pushed towards or being pulled. It's just a movement of electrons. You don't really have to mention anything. As long as you talk about E and F in some way, it's calm. It's good to talk about G. E has no inductive effect now, because there are no carbons. In fact, it is negative inductive effects because it's being pulled. Okay, if it pushes electrons, that is positive inductive effect. Okay, if it pulls electrons for whatever reason, it's going to be negative. Can you see that electrons are delocalized into the ring? Yeah, that should be fine. I would advise you just put negative and positive inductive effect. It covers that kind of whole term, the whole sentence with that one phrase. Until 7 o'clock. You look at this in OCR, yes. This is OCR. This is common in OCR very easily. Okay, you're not taught this explicitly. You're just taught that benzene is weakest, ammonia is strongest, ammonia is in the middle, and alkyl is strongest. That's all you're taught. Even in AQA, you're taught this. Okay, this is just the application of it. OCR. You can talk about G. It's because I've said that N is the furthest away. I've kind of took account of G. If you just said this, if you said without it, then you wouldn't get full marks. Okay, you need to specifically say that nitrogen is the strongest and take reference of it because both of these have alkyl groups, right? But because I mentioned that nitrogen is furthest away from the ring, I've kind of taken account of G. Okay, you can just say G is in the middle and say that nitrogen is right next to the ring. That's completely fine as well. Okay. Yes, you do. You need to know the nucleophilic substitution of how. Yeah, you do. All right. Next bit. What we've got. We finished amines in 40. Have we finished amines? Oops, that's bio, guys. I don't teach bio. Okay. Nitrile to amines. This is an equation you need to know. So if I draw, this is just an equation you guys need to know in terms of organic synthesis, converting nitriles into amines. Okay, learn this. If you have a CH3CN as a nitrile, why is NH3 stronger than benzene? It's because there's no negative and there's no positive. That's why UB. If N is furthest away, it's harder to. Yes, easier. Yeah, exactly that. If you're converting nitriles to amines, this comes under your organic synthesis. Essentially, what we have to do is you're going to be using. There are two, but you're going to be using hydrogen gas and nickel catalyst. Yeah, you can put 200 degrees. That is great. Yes, P, that also works. So the other one, if you've learned this instead, you only need to learn one. But if you're going to put AlH4, you need to put dry ether. You need to do this. You need the ether bit. Okay, because I've seen mark schemes. You're going to need that bit. It's not dilute acid, it's ether. Ether is different to an acid. Okay, I would recommend, this is the easiest one to learn. But if you've learned the second one, great. In my opinion, that's calm. How would you write this out? Now, when you're using the let's start with this one actually, because they're actually different in terms of their equations. Let me move this one down. If you're using hydrogen gas and nickel catalyst, well, if we're converting it into a CH3 into an amine, well, what happens is your C also has to gain hydrogens. This becomes a CH2 and that becomes an NH2. How many hydrogens have we added? We've added 4 hydrogens in total, so I'm going to add 2 H2s. How do I know which one to put? You can just put any. It doesn't matter for it. Where does the ammonia come from? What do you mean ammonia? This NH2? It's because of the hydrogen gas. Okay. If you decide to choose this, make sure you use the reduction equation instead. Okay. It is different. Plus 4H, because this is a reduction. Okay. You will not get the mark if you decide to use this and if you decide to use 2H2. Okay. You need to choose the relevant equations for whichever one you choose. Okay. I think the first one's easier, but if you memorize the second one, that also works. Okay. Cool. Okay. Yeah, this one's a reduction. The second one is a reduction. This first one is what's the first one be? First one wouldn't be considered a reduction. It's because this is the reducing agent, right? That's why. 6H plus on top of the arrow instead of plus. You're going to be using 4. 6 is for something else. 6 is for nitrobenzenes. I'm actually going to get onto that now. So for nitrobenzenes, this is also an equation you need to know. No, put it as plus, Shah. Put it as plus. Nitrobenzenes to phenylamines. This is also an equation you need to learn. Now, there are some reagents with this. First of all, you're going to be using tin and concentrated hydrochloric acid. However, when you decide to react this, rates are going to be quite further on. Okay, when you decide to react concentrated hydrochloric acid with, sorry, there should be NO2 there, with this, what happens is a salt is actually made. You actually make a phenylamine salt. And to get rid of that excess bit, you add NaOH. Or in fact, sorry, that's wrong. You go ahead and take NaOH to go ahead and neutralize the HCl, but you'll be making some salt as excess. Okay, so for this, in terms of your equation, you make 6 H pluses as your reduction, and you also make, well, how much? Let's kind of figure it out. We've used 2 oxygens. Well, there's no more 2 oxygens anymore, so we have 2 O's. We've used 2 hydrogens. How many hydrogens do we have left? We have 4. What will that make? We'll make 2 waters. What's the first homologous series called with NO2? Nitrobenzenes. It's just NO2. I don't get what you mean. Your nitrogen oxides, you mean? Do you have to mention NaOH? This will most likely get you the mark. It really depends on the mark scheme. So what actually happens with mark schemes is that if too many people are getting it right, they can actually, so for example, like the first 5,000 papers, if everyone is getting that question right, they can actually just be like, okay, we're going to add on NaOH because it's an extra bit. So the first 5,000 people that got it right, and the second 5,000 people, if they didn't put NaOH, they got it wrong. They can do that. Okay, so it's a bit on luck, I'd say. It's a bit on luck. Just to be safe, just do this. Okay, they can do it with, not really with maths, because maths is maths. They do it with chemistry, with bio. It's just that. It's a thing. Okay, if too many people are getting it right, they can do that, man. They should do that. Yeah, my chemistry teacher back then, she was good. Oh yeah, one last thing: the usage of these. Someone said it a while back. The manufacturing of dyes, or you can just say dyes. Dyes will get you the mark. That's the same thing. Right? That's the same thing. Yeah, Ifa, yeah. NaOH is for the yes it is, but it's part of your reagent still. This will get you the full mark, most likely. I'm gonna give it a 95% chance it will. Okay, if it ever asks, this is your extra bit. Okay, what's the bit for? That's for your NO2. That's like your trinitro. That's TNT. I remember this tetra nitro something. Yeah, this is phenylamine. Yes, this is nitrobenzene phenylamine. No, I haven't gone through peptides and DNA. Okay. I'm going to skip past that. This is good. This one's a good question. Just looking at time as well, because we've just finished amines now. But to be fair, amines is a decently sized topic, so I'm actually happy with timing on it. Why is a primary amine more acidic than a secondary? Why is it more acidic? It's because it's less alkyl groups. That's why. Yeah, yes, it does, Raheem. Yes, it does. It's because there's less alkyl groups. So your you can argue. Basically, you can say your electrons are less available. That's why. Yeah, manufactured dyes. I always put dyes. Dyes got you the mark. To be fair, you probably should put manufacture. Manufacturing dyes. Yeah, that's probably the better term. All right, have a go with this question. Have a read, attempt it, and then we'll go through it. I'll give you guys 3 minutes for like the first bits. Oh yeah, Tom, nice, my guy. Trinitro to toluene. Guys on TikTok, if you want to come to YouTube, I'm replying more from YouTube. Like the chat is like right in front of me. TikTok, I'm looking here and there. So, and you can see me as well. Let me have a look at stream. Okay, give the IUPAC name for region X. Nice shot. It is that. Perfect. 2 chloro. Ethanol chloride. Ethanol chloride. Why is it an ethanol chloride? It's because of this CO. Oops, wrong pen. It's because of the COCl. Okay, it looks very, very similar. It's because of your priority group. Okay, it's because of your priority group. So your priority group is this. So this is your carbon 1, and this is your carbon 2. Your priority group is your suffixes, anything that's on the end. So carboxylic acids, aldehydes, ethanol chlorides, ketones, arguably. Actually, no, I'm not. I'm going to take away. I'm going to say no to ketones. Nitriles. I'm trying to think what else comes to my head. Mechanism: nucleophilic additional elimination. Potentially. Outline a mechanism for step 1. Yes, it is. Can I go over OCR how I named it and why it isn't? Oh, can I over why how I named it? Yeah, of course. Why isn't it cyclical? It's just because of the molecule. It can be cyclical. I can see why you're. I can see why you're saying it's cyclical. In this case, it won't be. But the reason how I named it essentially in that molecule, you have an ethanol chloride. So this is your ethanol chloride group. When you have a double bond OCl, that's your ethanol chloride. This is a Cl attached to that C. This is carbon 1 and this is carbon 2. Why it's carbon 1 is because this takes priority. If ketone, it still be a propanone. So you'll probably get like 1, 2, it'll be probably like 1 carbon or 1 chloro, something propanone. It really just depends. Most of the time, because with ketones, they try to be symmetrical. If they're not, try put the ketone on the lower number. Chloroacetyl chloride, yeah, you can, but we're not in America, man. We've got to be using IUPAC. We're going to be using IUPAC names, Rungi. So I can't lie, allow the acetyl stuff. You probably would get them out though. You should. I don't see why you shouldn't. But you need the 2. Nah, I can't lie, no, you won't get the mark. I'm going to take that back. You won't get the mark. It says IUPAC. IUPAC naming. Alright, in terms of mechanisms, I was planning on putting this in the carboxylic acid topic anyways. But let's just do it now. This is your nucleophilic addition elimination. How does this work? I'm struggling to draw a benzene ring. 1 second, guys. There we go. CH3, NH2, CH3. Now, your mechanism, it essentially works on the seal bit here. Actually, it's not even an addition elimination. 1 second. Because it's not binding from that Cl. Oh, it is binding from the Cl. I'm tripping. 1 second. Let me move this down. Just so I have a bit more space. Okay, so what we have, C, double bond O, Cl, CH2, Cl. I'm going to separate this out as 2 H's. Now what happens is, how many how many bonds? Yes, this is OCR as well. How many bonds does nitrogen have? At the moment, it has 3 bonds. So what that means is this has a lone pair. Now, the lone pair, as we said from before, we do negative to positive. Learn this rule. For all your mechanisms, negative to positive. All right, you want to do Arrhenius too? It's just... Nah, I'm not. I'm gonna keep it like this. Let me clean this up a bit more. Okay. 1, 2, 3, 4, 5, 6. My guy, one note. Yeah, that's arts. Okay. N H H. There we go. That's cleaner. That's cleaner. Okay. Lone pair goes to the C. The C is going to be your delta positive. Technically, you have delta negatives on both of these. That's fine. But this group will attach to the C. Okay. But what happens is because this attaches, this bond ends up breaking. Okay. Negative to positive. This is a more negative region. Okay, so when it attaches, this is our second molecule. You can actually do this in one step even if you want, kind of. So what happens is you have your C, double bond, actually it's going to be a single bond O now. Why? Because this double bond breaks. We give a negative charge on that O. Cl is still going to be here. CH2Cl, the same molecule. And then on the bottom, attaches this whole group. So what we have is N, 2 H's on the side, and then we also have our benzene ring from before. I'm just going to see how we can attach this. And that's going to be CH3. Any questions so far? Yes, this is nucleophilic addition elimination. Yo, who's yo, chill out. Can't be having that. Stop impersonating me, man. Yo. Can't be having that. Who's impersonating me? Chill out. Might have to block you, bro. That's crazy. Let me put you on timeout real quick. A 5-minute timeout. Yeah. Don't do that. You made a whole account. Broski made a whole account, bro. That's crazy. Yo. Alright. Okay, yeah. So nitrogen at the moment has 4. So it's going to have a plus charge. Let's start to clean it up now. The chlorine pops off. Why? Because we don't want the chlorine. Every time you go ahead and react with the ethanol chloride, remember, you will always make HCl as your side product. You'll always make HCl as your side product. Okay? What else? We don't want 4 bonds in this nitrogen, so one of the H's pops off. One of the bonds comes back, and this becomes a double bond. Okay? These are 3 curly arrows you need to learn. Negative to the positive area. The electron's really negative. Chlorine pops off. This pops off. This becomes a double bond again. Okay? Use your final group to help you to figure out what your final product should look like. Okay? So if we go ahead and clean this up a bit more to make our final product, this will be C, double bond O on the top, CH2Cl. We have N, 1H, and then our benzene ring, like so. And we can compare that with our final molecule, like before. Can you do it one step? The Cl curly arrow going off the bond to the chlorine. Yeah, you can do this all in one step, by the way. Okay. The only reason why I'm doing this in two steps is because we need another diagram to show that this is a single bond and a lone pair. But you can do this 100% in one step. And also, just make sure. I know your teacher probably told you this. Make sure they're connected to the bond. Otherwise, you probably will lose the mark. They are very picky on this. But yeah. Okay. That will be your final molecule. Always should check your bonds at the end. Carbon has 4 bonds, great. Nitrogen has 3 bonds, great. Okay, are your bonds correct? Cool, we're good to go. And that will be your final molecule. Okay. Alright, amazing. Name the mechanism for step 2. What is the mechanism of step 2? Oh yeah, that's alright. That's not too bad. What is the mechanism of step 2? Nice. It is nucleophilic substitution. Why is it nucleophilic substitution? The chlorine pops off. It's getting substituted on. It's just nucleophilic substitution. Why is it nucleophile? is because nitrogen, when it has 3 bonds, it has a lone pair. Okay, nucleophilic substitution. Amazing, guys. Lidocaine is used medically as a salt lidocaine hydrochloride. Suggest which one of the nitrogen atoms labeled A or B is protonated in lidocaine hydrochloride. So essentially what it means is which one gains hydrogen when it becomes a salt. That's what it's asking. Why do you say B? Sure. Is it A or is it B? Which one, essentially it's asking which nitrogen gains a H. Is it this one or is it this one? Okay, we got A's and we got B's. Trying to see where the hell did I get this question from? Okay, yeah. Okay, well, someone said C. Correct answer is D. I'm joking. Correct answer is B. Reason being, this is to do with your amine stuff. This is to do with your quaternary ions and such. Okay, when it gains a H, what happens? This becomes a quaternary ion. And essentially what happens is this becomes a plus. We cannot attach a H on this because it already has 3 bonds. Yes, this has 3 bonds, but because the way that this is attached, this is not acting as an amine group, it's acting as an amide group. Okay, so if we decided to attach a H here, it wouldn't work here. Okay, because it's acting as an amide. We can only attach the H's or make a quaternary ion when we're looking at amines. Does that make sense? Okay, so the answer would be B. Explanation. Let me look at the explanation, guys. B has more negative inductive effect. I do like that answer. Yes. Yep. A has more negative inductive effect. More available lone pair on B. Cool. Amine accepts H, amide doesn't. It's to do, yes, think of it like that. Yo, he's back, bro. This guy's back. This guy's actually back. Yo, Rico, man, where you at? Yo, I'm gonna leave you there, yeah? I'm gonna leave you there for now. If you misbehave, you're out. I want him to study, man. I want him to study. Yes, Speed, how are you, man? Okay, let's move on. That's more or less amines complete, by the way. Actually, that is amines complete. Let's look at alcohol testing and making an oxidizing alcohol. So, alcohols. We have 3 types of alcohols: primary, secondary, and tertiary. Can you talk about positive inductive? Yeah, you can 100%, because specifically it's more of a base, right? Because it's more basic than this area here. That's the whole point. So because it's more basic, it's more likely to accept that H+. Okay, can I explain the difference between negative? Negative, it takes electrons away. Positive, it adds electrons onto the N. Okay. Yeah, man. Yeah, me versus me. Crazy. You're gonna ban him. Okay, primary alcohol is pretty simple. We're gonna have an OH on the carbon here, on the first carbon. B has more. Yes, UB. Secondary, you're gonna have the OH on the second carbon, where you have 2. Tertiary, you have 3 OHs. How would that even work? Actually, I'm trying to think off the top of my head. Like this. That's your tertiary. Which part? I made a quick brief answer. More available, I should probably say. Yeah, that also works actually. A has more negative inductive effect and more available lone pair on B. But you should, I kind of mixed it up, but B, you can put B has more positive. That works. Alright, cool. Why is it more basic? Is because it has more positive inductive effect, Diana. Alright. Alcohols. I want to move on because we've spent an hour on that. And we are 25% of the way through. Now, testing for your alcohols, pretty simple stuff. Make sure you put acidified potassium dichromate. You need the word acidified. Without acidified, I can't let you not getting the mark. Okay, you need acidified. And this happens in reflux. Now, when we're testing or when we are converting our alcohols, something happens in the reflux. Something happens. I'm going to draw the reflux structure, and you guys also do need to know this by heart. We will have a heat from the bottom, and it's not a Bunsen burner, it's heat. We have our solutions. We have anti-bumping granules specifically to prevent violent reactions. We also have a thermometer and probably a stand, and in distillation you also have some condensers. Oh yeah, you do have a condenser on the outside. Let me do that in a different color. Let's do that in blue. Condenser. Make sure you're putting water from the bottom, not from the top, from the bottom. And make sure you try to, look, I've kind of made a mistake here, you can see this is closed. Make sure you have the right amount of lines, open lines. So do not make lines closed, as in, do not do this, that's wrong. You will lose the mark. Do not do that, that's wrong. Make sure they're open. They're very, very picky about that kind of stuff. So water in from the bottom, this is your condenser, and water out from the top. Why do we put water in from the bottom? Is because so the whole condenser gets filled. Otherwise, the water will just directly fall. Good. Now, does anyone remember what is the color change when we put a primary alcohol into a reflux with acidified potassium dichromate? What is... Yes, Shah, yes, exactly. What is the color change from acidified potassium dichromate? Yo, where'd you get pink from? Where'd you get pink? It's orange to green. Okay, good. Orange to green, guys. Well done. Make sure you are learning and confident with the color change. Okay, this is how you test. This is how you test for thing. But I can see why you're saying that. It's because in OCR they do use potassium permanganate. I can see why they're saying that. So you are right about manganate. All right, good. So when we are testing our alcohol, what actually happens is, and you guys do need to know about your equations for this as well. This goes to an aldehyde first, okay? And if you want to separate for an aldehyde, we can slightly adjust our reflux diagram into this. And you can essentially just add a condenser onto it. So this becomes like so. Again, water out from the top, water out from the bottom. Okay, and make sure you inserting this into an ice bath. Okay, and what happens is this is specifically for your aldehyde. Okay, it has a condenser. And make sure you're kind of drawing it properly. I've kind of drawn it a bit clapped. Yeah, make sure there's single lines. Okay, good. Water in from the bottom, water out from the top. Did I say out from the bottom? Did I say that? My bad. In from bottom. Alright. Oski. You're a Sigma space here. My guy. Alright. That's how you make it aldehyde. But if you continue to go ahead, yes. So you add it with it basically. It's like a solution. You don't just add your alcohol, you mix it up. And then the aldehyde continues to get reduced to your carboxylic acid. How do we test for aldehydes? What's the test for aldehydes? There are two tests you need to know. You don't need a bung, Jacob. If a bung goes, your thing's exploding, man. Okay, if you say Brady's for OCR, you are correct with that as well. Hamza, I want to know what's the color change for Brady's. Good. Tolerance and feelings. Good. Very good. All right. So when we're making aldehydes, we're going to be using tolerance reagent, and you guys need to know some equations for tolerance. Okay. Ibrahim, we use a distillation for that. So this is the practical. This is your equipment for this. So when it goes up, it cools down and makes an aldehyde straight away. Okay. So for tolerance reagent, you make a silver mirror. Okay, and you need to know some ionic equations for this. This can pop up. It's not necessarily that it will. this is your equation for this. So this is essentially your tolerance reagent. What happens is you add electron. This kind of comes from your sample. That makes a silver mirror and 2 ammonias. That is your equation for tolerance. Shouldn't we use a bung? No, don't use a bung for reflux. Do not use a bung for reflux. Actually, you could, not for reflux. Use it for distillation, yes. Actually, avoid bung. Don't put bung. Don't put bung. The other thing's gonna explode, bro. Don't put bung. Don't put bung, bro. Alright. Yeah, don't put bung. Alright. Feelings. Perfect. You guys said brick red precipitate for this for a positive result. There's also an equation for this. This is going to be Cu2 plus electron makes a Cu plus. Let me just check that. I believe that is correct. Yeah. Okay. This is for feelings. Carla, I don't know who ramps it, man. I don't know who ramps it. This can pop up. It might not. This is there. Okay. Now, there are some, what was I going to mention this? Oh, I've forgotten what we mentioned. I've just gone, oh yes, I remember now. Okay, there are some equations you need to know about your alcohols making to aldehydes and aldehydes into carboxylic acids. Okay, so, when you have an alcohol like this, CH3OH, you're going to be using an oxidizing agent. This is your oxidizing agent. What is the purpose, actually? What is a reagent for acidified? How do you make this acidified? What is a reagent for this? No, they're both being oxidized. Should be they're both being oxidized. Thank you, Anita. Thank you, Eggy. Amazing. H2SO4. What is the purpose of H2SO4? What is the purpose of this? HCl also works, Tilly. What is the purpose? Nope. Catalyst. Catalyst. Whenever you talk about H2SO4, talk about catalyst. Okay? This is more or less all of organic, okay? This comes in, the only exception is in group 7, and you guys are not doing group 7 anymore. That was in paper 1. Okay, and actually, for the guys that did paper 1, I can't lie. Inorganic, beautiful, bro. Beautiful. Not for impurities. Okay, it's for your catalyst. This for OCRA, kind of, Ahmed. I know OCRA looks at potassium permanganate, but potassium dichromate you guys also need to know about. So yeah. It's going to be concentrated. Dilute is for, it's not coming to my head, for KCN. Alright. This makes this. That is wrong. No, it does not make that. This is not. You can't make an aldehyde with a. Oops. CH3CH2OH. That's your ethanol. That goes to a COH. Plus H2O. Yeah. Okay. Balance your reactions. We have 2 oxygens here. We have 2 oxygens on the other side. This is going to be your equation for this. Okay, one of the H's comes off, or 2 of the H's come off, sorry. One of the, what we have left remaining, we have an oxygen. It's just going to make an aldehyde and water. Okay, ester formation, that will be in our carboxylic stuff. Sorry, CHO, yeah, you're right. Sorry, BMZ, you're right, it's CHO. That's my bad. Yeah, absolutely right. Okay, and then when we go ahead and make a carboxylic acid, again, we're going to add another oxidizing agent. This one is pretty nice. It's just become a COOH. Okay, completely balanced, and we just leave it like that. If you want to combine your equations, you can just kind of combine it like you do in terms of electrodes. You can combine them so you have 2 oxidizing agents, and you also make a water as well. Okay, these are equations when you're working in terms of alcohols. Now, in terms of your mechanisms for aldehydes, you have 2 types of mechanisms, or in terms of ketones as well. Okay, you have, well, not 2 types, you have 2 mechanisms. Both are going to be reduction. Okay, now these Let's use this molecule here. CH2, no, CH3, CH2, let's keep it simple. CH3, CH2, CHO. Okay, and the first molecule we're going to use is NaBH4. Is reduction a reaction, not a mechanism? Yes, it is. But these are reduction reactions with two mechanism melts. Cool. Amazing, Saifola. So what happens is, both of these make, or in this case, you're going to make a primary alcohol. Now, the mechanism for this, I'm going to put CH3 here. C, double bond O, H. And how are we going to start this? What is the equation for the reduction of? This is just making an alcohol into a aldehyde, aldehyde into carboxylic acid tilly. Okay. All right. For the mechanism for this, we are going to start with a H minus. What is the name of this mechanism? Anyone? What is the name of this mechanism? Thank you, Hisham. Thank you, Ali. Nucleophillic addition. If you guys are unsure on how to name it, well, your nucleophile, there are two things. Your nucleophile is an electron donor, a lone pair electron donor. Should probably yeah, you can say electron donor, and an electrophile is an electron pair acceptor. Okay, I should probably put pair here. Okay, these are your definitions for nucleophile and electrophile, and they can help you figure out, okay, is this nucleophilic? H minus is a nucleophile. We've got a lone pair here. So what we're going to do, use our same rule, negative to positive. This is delta plus, delta minus, arrow towards a C, double bond breaks. Would you dilute the H plus? So here BMZ, your H plus actually comes from water. Okay, so this is actually going to be aqueous. And arguably you can probably use acid here as well with this, but usually it comes from water. It's not ethanoloic. Don't need ethanol for this. You can use dilute acid for this as well. Yeah. Okay, so you either have H plus from acid, from weak acid, or water. Okay, so your H minus comes from the NaBH4. It doesn't really matter. It doesn't really matter about the. It just needs to be aqueous in something. So methanol is also fine because we just essentially need the source for your second H plus. Yes, FK. All right. The second step, your second intermediate or first intermediate actually. What happens is the H bonds. H3C, CH like so. This becomes a single bond. Again, very, very similar to our nucleophilic addition elimination as before. This is negative. This is H from before, and then our new H. But we don't want this molecule here. What does your aldehyde go to when you reduce it? Well, it makes an alcohol. It's essentially the reverse of this. This is being oxidized. Your aldehyde gets oxidized. Your alcohol gets oxidized into your aldehyde. So aldehyde gets reduced back into an alcohol. So what we're going to do, we need to make this back into alcohol. We could just use a H plus. Okay, H plus, negative to positive. Boom, attaches, mechanism done. Okay, for LiAlH4, not for this. That is for specifically your nitriles to amines. Okay. But sorry, you can't. That's fine. Yeah. Nitrile to amines. Yeah. Cool. That is your nucleophilic addition for NaBH4. Where does the H plus come from? This depends on what you've dissolved it in. It can be from water. It can be from dilute acid, maybe like HCl. It can be from methanol, ethanol, whatever. You just need some sort of solvent that you're dissolving in. Okay, I personally like water. It's pretty nice. But yeah, exactly the same for your hydroxynitrile. Okay. Yes, Raheem. Yes. So in this case, if you were to make an equation, you would use two reducing agents. Okay. Let's try the same thing. I want you guys to try KCN. And actually, this is your reagents. KCN plus dilute acid. Do not put HCN. HCN is not your reagent for the second one. Okay, we're going to be looking at enantiamides in the second round. Okay, do not look at HCN. Do not put HCN. Put HCN a dilute acid. Reason being, you cannot have HCN, bro. I do like acids. I mean, acid. I do like water. I don't like acid. Okay, the question, so this is just for your reagents for your second mechanism. Okay, I'm going to put down this molecule here. C double bond O, H, H. I want you guys to reduce this. Okay, using KCN and dilute acid. Avoid it. Avoid HCN. Okay, exactly, because the reason why I'm saying avoid HCN is, one, sometimes they might not allow it. As the reason I said before, they might change it. Secondly, it's because it's just a dangerous molecule. You'll never ever find HCN on its own. You can't buy HCN. You can't make it. Actually, you can make it, but when you do it in terms of your reactants, you always have HCN and dilute acid. This is just actual chemistry. Okay, your A level is based off real chemistry, so based off real chemistry. That's why. Oh, you have in your basement. There's. Alright, guys on TikTok, if you want to come to YouTube as well, let's keep on throwing it out there. Alright. Follow the same mechanism as before. Do the exact same thing. What's the P? What's the product? If you got a... It's not from aldehyde to carboxylic acid, you're also reducing this. You're going to make a secondary alcohol with this. Yes, we will be doing exam questions here and there, yeah. So, not for this one, just for the main topic. So, I've got a couple here. Main thing is going through content. But a lot of the stuff that I'm going through is going to pop up. The way I teach, I mention every single little bit. The CN is a lone pair, yes. The C, not the nitrogen, the C. The first carbon. The first molecule. Tilly, you made a mistake there. Felicity, there's also a mistake in there. You'll get marked down. You'll not get a mark for that. I know what you mean. You spelt it a bit wrong. And I know it's stupid. But yeah. Ester formation mechanism. There we go. Yes, it needs to be propane nitrile. There needs to be an E there. You'll get marked down if you propane nitrile. It needs to be propane nitrile. Okay? Alright. So, let's start with the mechanism. You're going to start off with the C. Negative. Okay? This bonds to your C here. This is delta plus, this is delta minus. Follow the exact same rules. Bond breaks. Our intermediate. We have CH3 here. C, single bond. Our CN attaches from the bottom. Okay? Then what we want to make this into an alcohol. Our H plus comes from our acid. Negative to positive. Mechanism done. In terms of naming this, okay, this is going to be a hydroxynitrile. Why? Because your nitrile takes priority. What is your longest chain in the group? 1, 2, 3, or you can go left as well. So this is going to be a propane nitrile. Your nitrile is your priority group, so this is going to be carbon 1, carbon 2. So this is going to be 2 hydroxy propane nitrile. Can H plus come from water? Not in this. From the other one, yes. Not in KCN dilute. You need dilute acid for this. Why doesn't benzene undergo addition reactions? It can be. You just need a catalyst. So if you did OCR, you look at I believe it's not inductive effect. I forgot the name of it. But you can essentially need a catalyst for it. NaCN is fine. Yeah, that's fine. That's okay. KCN, NCN doesn't matter. You just need that CN group. What happened to the methyl? The methyl's still there. You can add. You don't look at an AQA though. It's dilute acid, man. That's just dilute acid. This is going to be also nucleophilic addition. Okay, you're taking a nucleophile. Your CN is your nucleophile. What are you doing? You're just adding it on. You're not substituting it to anything. So it's just going to be nucleophilic addition. Okay. On the left, what do you mean methyl? Yeah, sorry. You're absolutely right. Oops, forgot about that. Absolutely right. Cannot forget about the methyl. Thank you, Ibrahim. Thank you, thank you, thank you. So yeah, it would be 2-hydroxy, 2-methyl. Yep, sorry about that. Yeah, no, you guys are right, you guys are right. You guys, BMG, you need a catalyst for it, that's all. Okay, cool. Yeah, no, you guys are right, you guys are right. Sorry, guys. Okay, now we're going to look at optical isomers real quick. Okay, so optical isomers, they don't have to necessarily form from, yes, Shah, you do. They don't necessarily form from aldehydes only. So you, as long as you have 3 different bonds on a carbon, you have a chiral carbon. Okay, to make a optical isomer, you essentially need 4 bonds. Okay, why does it happen in terms of this? Okay, and I'm going to show you a diagram. So I'll go back to up here, and you can see at the moment we have 3 bonds attached to the center carbon. Okay, so I'm actually going to attach it like this: C double bond O, CH3, CH3. What is the shape? What is the shape here? What type of shape is this? Planar? Yes, it is. What type of planar? What type of planar? Give me the full name. Trigonal planar. Thank you. Any angles? What do we know about angles? Good. 120 degrees. Okay, we have 3 bonds, and it's 120 degrees. Okay. What I'm going to show you guys is how the isomers are made. Give me a second. 1 second, let me just pull this up. Try and bring it to out the screen. There we go. Okay. So, what you have essentially here is your molecule that we just had before, right? This one here. Now, what happens is your CN comes in, okay, we're going to attach. We're going to attach from this. But in reality, these are 3D molecules. So what can happen is, this can attack from the top, or it can attack from the bottom. And because of that, you can make 2 different isomers. One looking like this, and one looking like this. They look really, really similar. But these are not the same molecule. If I move this to the left, you can see the yellow is not in the same place as the pink. These are 2 different molecules. And that's how we call these optical isomers. Your teacher will show you on paper and with the drawing and lines and stuff. But I think it's a really, really good idea to see what's actually happening in terms of 3D. These are your 3D molecules. Okay, and these are your 2 isomers. And the way we draw them is like so. I'm going to use this this structure here again. And I'm going to show you how to do this in terms of drawing the optical isomers. No, it's not Desmos, it's not Desmos. Okay. That's a Roblox. It's not Roblox. But put your center carbon in the middle. Okay. On the top, you're going to put OH for both of them. And then we're going to draw these 2 shapes. It doesn't matter where you put them really, as long as you're consistent on both. Just needs to be like that. Perfect shot. Ibrahim, if I go back to this, originally, yes, it does. Here, we can see it has 1, 2, 3, 4 bonds. This is 4 bonds. Okay. Alright. On the bottom, keep it as CN. And then what you're essentially doing is just swapping these 2. Oh shit, that's wrong. That's supposed to be something else. CH2, CH3. Let me put that as that. Okay. CH2, CH3, CH2, CH3. Make sure you're having 4 separate bonds. Oh, sorry, 4 separate molecules attached to each carbon. And then this will be H3C, H3C. Okay. Oops, I've done that wrong. Swap these 2 around. CH3, CH3, CH2. Okay, just swap these 2 molecules around, and that's your 2 optical isomers. Easy peasy. Okay, CN stays in the same, OH stays in the same. Yeah, it's better to. I'd say it's better to. Actually, I'm going to say you have to. Okay. These are mirror images. Now, they're not the same thing, Srija. They're not. Okay, these are not the same thing. Okay, if I go back up to here, you can see these are not the same. Look, they look the same. The blue is in the front, the green's on the top. But if I move this to the left, these are not the same molecule. Okay, all right. It's because that one's in the front, one's on the left, one's on the right. Okay, now what happens with optical isomers is that you can test for optical isomers using plain polarized light. You need to know this for AQA. Do you not need to know this for OCR? You need to know this for AQA. Okay? Now, it's like your hands. And actually, I'm going to put this term here, super, because you guys said it in chat. I'm just going to write it down on screen. Superimposable images. Oh, sorry, non-superimposable images. Because you guys did say it in chat, which I'm really happy about. All right, cool. How you can test for these optical isomers, because essentially these are all colorless. They don't have any color. You can use something called plain polarized light. Now, what is plain polarized light? What is it? I'll show you what it is. Back onto my my diagram. This. Now I might lag a bit. Essentially, this is plain polarized light. You have a really, really thin light that's passed through. Okay. And what happens is each sample. So you have two test tubes. You have two test tubes in this. Okay. One light will go through this. Or yeah, it's a bit dodgy, man. It's 10 FPS. You guys are gonna have to firm it. But essentially, the light will rotate one way with one of the samples, or with one of the isomers, and then the other way with the other one. Let me show you this from this side. Ignore the box moving because I couldn't figure out a way to rotate that. Okay. So essentially, your light ends up rotating when you put it through. So think about glass. It's about refraction. Okay, the light ends up rotating because of the isomer. One of them might rotate maybe 30 degrees. The other way rotates maybe minus 30 degrees. Don't need to know the angles. I'm just making these up on the spot. Okay, but the key bit is, yes, Ibrahim knows. Ibrahim knows. Okay, the light ends up rotating one way. The other isomer ends up rotating it the other way. Okay, that's how you differentiate it. Okay, this is what you're going to put down. Plain polarized light causes or is rotated by each isomer in opposite directions. That's how you differentiate between the two. But in reality, when you go ahead and do this mechanism, you're not going to make this or this. Why? It's because if you go back to the diagram again, let me pull up my diagram. This happens 50-50. Some of it will be at the bottom, some of it will be at the top. So what happens is you make 50-50 of these, and you make a racemic mixture. That's what a racemic mixture is called. So you make a 50-50 of both isomers. Okay? If you make a 50-50 of both isomers, what happens to your rotation? What happens to your rotation? You don't need to, Shell. You don't need to. You just need to know about plain polarized light. It just becomes really, really thin. That's all. Exactly. So if it's going 30 degrees in one way and then minus 30 degrees in the other way, they cancel out. Light rotation cancels out. Light rotation cancels out. Therefore, no overall rotation. Okay, that is your racemic mixture. Okay, if it ever asks you, oh, one sample is this and we have two samples, how do you differentiate between them? It's because you rotate. What are you confused about, Ali? Plain polarized light, you use it to differentiate between the two. Okay, but when you make the original reaction, when you make the reaction in the first place, you actually make a racemic mixture. Both. Optical isomers and enantiomers. Enantiomers. I can never say the word. They're both the same thing. Okay. If you ever see this, enantiomers / optical isomers, they're the same thing. Okay. So don't panic if you see that word. Okay. Plain polarized light, differentiate between the two, but in reality, when you make it with the mechanism, you make a racemic mixture, which is 50-50. These are 2-3 markers. Can you talk about the stability, which is major or minor? There's nothing. It's not really to do with your major and minor stuff here because it's optical isomers. Racemic mixtures is when you do the mechanism in the first place. It's when you do the mechanism in the first place. That's why. Okay. That's when you make your racemic mixtures. But let's say for some reason the scientist has one sample and he has another sample separated out. How would you differentiate between the two? Use plain polarized light. Does that make sense? Okay. I would recommend that you talk about them being planar. Okay. Talk about them being planar. For this part here, actually, they're planar. They're planar molecules, specifically your carbonyl group. Okay, and that means that your CN can attack, or you should say your nucleophile can attack from either side. Okay, this is actually a very, very key point as well. Tilly, that's good. That's actually a really, really good term. I like that term. Optically inactive. That's beautiful. I'll get you 4 marks for that. Okay, just make sure you're talking about planar molecule that's flat and that your nucleophile can attack from either side. I want you guys to try this question. Okay, it's basically what we've just done now. Write this down, and then we'll look at some electrophilic addition and ozone, and we should start to speed up a bit on the topics, and then we will get to CNMR in probably 25 minutes, or HNMR and CNMR in 25 minutes. That's the ETA. Maybe even less. How many different stereoisomers are there? You have cis-trans. Basically, stereoisomers, they're a big group. You have EZ, you have cis-trans, and then you have your optical isomers. OCRA you don't need really for plain polarized light. You don't really look at an OCRA. I'm gonna be honest. It's mainly for AQA. With the equal property, yeah. Yes, sure. Yeah. Yes, Daniel. Great. All right. Describe how you would distinguish between separate samples. We use plain polarized light. Plain polarized light rotates in opposite directions for each isomer. I also want you guys to go ahead and name this molecule, please. This is practice for your IUPAC stuff. What would you call this molecule? If you want to also practice your skeletal stuff, go ahead and draw this out in a skeletal formula. Okay, and then we'll go over this in a second as well. Cis-trans, it's very similar. Cis-trans is more, it can appear in your, so if it's a double bond, cis-trans is basically the same as your EZ. However, you can have cis-trans in like optical, in octahedrals, where in that case it's different. Okay, I'm going to draw this out. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that's going to be a hexane probably. We have a nitrile here. OH here. This is your priority group. So this is going to be carbon 1, carbon 2. It's going to be 2 hydroxy hexane nitrile. Make sure you have the E. You're not getting the mark if you don't put the E. Okay. Cool. This one, racemic mixture, talk about planar. So carbonyl groups, you can even just draw it out like this, 4 marks, are planar, meaning they're flat. Your nucleophile can attack from either side. Attacks from either side. Therefore, it makes a 50-50 mixture of both isomers. Perfect. This is AQA, but you will need to know this for OCR. First part, you don't need to know for OCR. Second part, you do. Can I explain the second question? Yeah, of course. Because we have a carbonyl group, so we're talking about kind of our where's it gone? Our like mechanisms that we did here. Okay, when you do a mechanism, because it's flat, let me go back to my diagram. Okay, because it's flat, this is your double bond up here. This can attack from the top or it can attack from the bottom. And it's essentially a 50-50 chance. Okay, it's a 50-50 chance. Chances are you're going to make 50-50 of this. That's what a racemic mixture is. Yeah, of course. Alright. We'll have a break at 5:50. What you do? What? No break. No break. I said no break. We'll have a break at 5:50. I mean 4:50. 4:50. Yeah, it's better to. Yeah, Raheem. Yeah.
Okay. I'm having a break just for 10 minutes. 10-minute break. 10-minute break. Okay. Next bit, electrophilic addition. Let's look at electrophilic addition real quick. You'll see 10-minute break. 10-minute break. 4. 7 o'clock. NK. All right. 10-minute break, guys. Yeah. You're guiding, yeah? All right. I'm gonna keep it simple for now. Actually, no, I'm not. I'm not gonna make it simple. CH2, CH3, CH2, H. I want the major product, and I want the name of the major product when you go ahead and take HBr and you go ahead and react this. Okay. I also want the name of the, I kind of said the name already. Name of mechanism. Okay. Draw the mechanism out, and we'll do the mechanism, and then after this, we'll stop at 450. Yeah, we'll do the sulfuric acid in a sec. What other groups are planar? Just anything with 3 bonds, Doddle. Okay, it's really to do with your shapes. So, for example, this. I mean, this is not really a real molecule, to be fair, but for example, this. Okay. Just anything with 3 bonds, it's just your planar. So you're thinking about your trigonoplanar stuff. Good. It's electrophilic addition. Perfect. All right. We'll have a break later on as well, because I need to break as well, that's why. We'll have a break later on. Alright. We're going to start with a H and we're going to start with a Br. Remember, and this can come up, your double bond is a high area. Oops, I can't spell at all. High area of electron density. Okay, this can come up. And this is your more negative area. Okay, so negative to your more positive, this is delta plus, this is delta minus. Why does that happen? It's because of your, it's kind of Van der Waals stuff essentially. It's an induced dipole because this is your really negative area. Technically this has a dipole already, but because it's a negative area, this causes this to become positive. Okay, arrow to negative, negative to positive, sorry, negative to positive. Okay, and then we're going to attach on. Now when you think about, the first thing what I could do is actually just split up the bond. Okay, so this becomes CH3, this becomes CH3CH2. I haven't really written this nicely, to be fair. H2C, H3C. Make sure you try to bond to the correct carbons. It's going to be H, and it's going to be H. Now, which one are we going to bind if we're trying to make our major product? Well, our major product is going to be when bromine attaches here. Actually, it doesn't really matter in this case. To be fair, it doesn't matter. It doesn't really matter in this case. They're going to both be the same. So both of them are going to be secondary. So let's say if I attach the H here, you want to attach a H first, by the way. Yeah, no major product in this case. Bromine, lone pair, goes to there. Okay, this breaks off, and you end up with this. Cool. Now, in terms of naming this, we have 1, 2, 3, 4. That's going to be a butane. That's going to be one methyl, 1 bromo, butane. Why no major product? It's because if we attach Br onto this, okay, this is only bound to the 1 carbon. Yes, it should have a yes, it should have a plus. You're right, Jacob. This carbon here is attached to 1, 2. This carbon here is attached to 1, 2. KP, does KP pop in paper 2? Did it not pop in paper 1? Was it not in paper 1? This is going to be your electrophilic addition. 1, 2, 3, 4. Am I tripping? Pentane? 1, 2, 3, 4. Your longest chain is 4. Oh, it's 5. Oh yeah, it's 5. Oops, sorry. I'm tripping there. I don't know why I said 4. I don't know why I said 4. I'm sorry, guys. That's 5. It is pentane. Yep. That's 2, 1, 2, 3, 3. Yeah. Guys, maybe I'm getting a bit tired. 2 bromopentane. Sorry, guys. Yeah. 1, 2, 3. In this case, I decided to swap the H's out. So if BR was there, that should be 2. Okay. Yeah, I can't. Let's have a break, bro. Let's have a quick break. Let's have a break. Alright. KC can pop up in both. KC, I think KC probably will come up. Alright, we're gonna have a 10-minute break. Yeah, NMR, we're gonna be doing NMR. We'll come back at 5. If you want to do something, you can chill here if you'd want. I don't mind. I'm still here. Alright, and then we'll start back up at 5. We're gonna go over the other two mechanisms. It's not really other two, it's just one more I want to really look at for sulfuric acid. What topics have I done so far? Amines, aldehydes and ketones, mechanisms alongside it really. Optical isomers, like plain polarized like that comes under it. But yeah, we'll be spinning up a little bit just because these are small topics, and then HNMR is going to be a big giant one again, which is going to take some time. Spend an hour on amines in the beginning, and it's all recorded anyway. So if you go into my YouTube, you can come see that. Where did the extra methyl group come from? It's because who asked that? Rungi. It's because of this. So if I let me do this again real quick. Okay, so if I just split up this bond here, C, this becomes CH3. I'm just going to turn this to CH3, CH2. Make sure you attach it properly. That's probably how you shouldn't attach it. But yeah. Okay, I'm going to attach H here anyways, just because we don't really have a major product in this. And then UBr, this is going to be a plus. This becomes a negative because the electrons go to the bromine from here. This attaches like so. What's our predictions for tomorrow? Let me go to my PowerPoint and I'm going to bring it on screen. I don't know if we'll be able to do practicals today because there isn't like a lot of stuff. I had more slides on paper 1 to be honest. But I think this are my predictions. I think it's going to be a 6 marker. Either on this, one of these practicals, either on DNA and polymers. If it comes up on DNA and polymers specifically, or / proteins, I can imagine there will be a 6 marker on primary, secondary, and tertiary structures. Okay. If you guys do biology, you're cooking. Okay. I'm not going to be going over this. Talk about like your bonds, the hydrogen bonds, and that kind of stuff. I'll be going over amino acids. If you have time, I'll probably stick it in this bit here because I want to go over chromatography as well. But I'll go over it. I'll try my best. Depends on how quickly we get through HNMR. If you get through HNMR quick, then yeah. Okay. Or there could be a 6 marker on what did I say last time? Oh, I told Jimmy. Jimmy, what did I tell you? Are you still here? What I said? Maybe iron. I don't think I said iron testing. Iron testing is too easy. If it's on iron testing, I can't. You guys are gonna be so calm. Oh, why is it bold? It's just because we're gonna do it anyways. Just the stuff that was bold here is just what I've covered. Yeah. Oh yeah, chromatography. Yes, chromatography. Chromatography 6 marker could come up. I can imagine it being explain the differences between TLC, column and gas. Yeah, Natalia, that's perfect. Disappearing cross practical is when you have your sulfur. It's when you add the sulfur and it's essentially your rates of reactions practical. I think it's RP6 off the top of my head. Let me just double check that. Rates of reactions required practical. That's my prediction anyways. I predicted the transition metals. RP5 is for AQA. If you're good with paper 1, paper 2, then you're done for paper 3, man. Okay, having a break, guys. We'll be back up. We'll start again at 5 p.m. So yeah. Yes, Timra. Yes. So if you guys want to come to YouTube, you can even come to YouTube now, Timra. Go from my link in my bio. Will I be live for paper 3? Good question. I don't know yet. Nah, I'm gonna put it later on. It's not time for us to see it. I look better from a few months ago. I appreciate Adrian, man. I appreciate my guy. My guy. When was the last time you seen me?
Yo, guys, it's not Roblox, by the way. It's not Roblox. Who said it's Roblox? Cyphola, was that you? Yeah, bro. It took me some time. Every time, yeah, I explain isomers, I end up making this, and then I always deleted it. I've taught like a couple guys this method. What's the integration value? Integration value is essentially when you have limits, and then you bring in like this, and you have to integrate it with like a delta H. That's integration. No, I'm joking, man. I'm joking. It's not integration, bro. Ali is study tutors on YouTube. I'm starting LSE in September, so I haven't gone yet. But that integration value, that's in HNMR stuff. I got an A star. I got an A star in chemistry. If you want to know. Did I see the buffers question? I've not seen the. Really want to see the papers. One of my students told me about the buffers question. I did see the mark scheme. I don't know. I can't remember off the top of my head what the thingy was. We went over buffers in my paper one session. My UCAT was, I did last year, man. What am I covering right now? We're having a break right now, bro. 5 p.m. But right now we're doing Electrophillic addition. How long did I revise for my chemistry exam? I can't lie, for chemistry I didn't revise that much. It was probably my least priority. My highest priority was bio. My bio was like, oh, Shah send me that. Don't just got to send me that, please. But honestly, I hate bio. It was my weakness. I got an A in bio. I was 2 marks away from A star. The thing is, I was good about, with my content, I was new inside out. I just couldn't. Just the mark schemes, this pissed me off, man. Appreciate Jacob, man. What should you focus on? Focus on the after today's session. We'll be going through that in benzene, Michelle. But focus on practicals. Get your practical stuff down. Specific heat capacity practical, no inside out. There's a graph part of that question, and I can still see that coming up for 6 marker. I'm not talking about in terms of your Q equals MC delta T. I'll put it in the chat. Look in the description of the YouTube thing, Shah. You see it. I'll be going through amino acids in chromatography part. Yeah. Just join that. Let me see it. Because I actually really want to see the paper. Because I know people said there was a lot of inorganic. One of my students, from the beginning when I started teaching it, I told him revise all of this inorganic stuff. What practicals am I doing? And I don't think I'm going to be doing any practicals other than recrystallization and chromatography. But the key points you need to know about gas chromatography, it's essentially, just while we're in this 3 minutes, I'll briefly go over it. It's mainly to do with your chromatography stuff. There's two key things here: your stationary phase and your mobile phase. Okay, in gas chromatography, your mobile phase is the thing that's moving. Okay, so essentially what you have is a sample thing, and then you put it into like a swirly thing, and then it comes out into a detector. Okay, and this is your computer. Now, in the swirly thing up here, actually, no, let's start with the sample thing. The sample bit here, you insert it with a gas. Okay, your gas is your mobile phase. Inside this swirly thing here, you have oil. The oil is your stationary phase. And essentially what you're testing is how quick does it move with it? How quickly does it come out of the swirly stuff and go into the computer? The more the retention time, you can have different peaks. The more the retention time, the longer it takes to come out. It just means it's more retained by the stationary phase. If it goes out quick, that means it's more retained with the mobile phase. Okay, that's essentially what chromatography or gas chromatography is. And you can link that with your mass spectrometry as well. That's called gas chromatography, mass spectrometry. Don't really need to know about that much. Just add this and then your mass spectrometry stuff, from topic 1. I don't even look at physics mass tutor predictions, bro. I can't lie, they ain't that good, bro. They just make some papers like a while back and you just stick it into questions. Most predictive papers they're us. I'm gonna be real. They're not that good. Most of the time they just make it, and I don't even think they're as hard as the normal ones. I don't really like predictive papers like that because I feel people don't put time into it. I think this is a cash grab. Let me show you. Yeah, this is potentially my predictions
for 6 markers anyways. Everything we're doing is probably going to come up. I think it's going to be very organic heavy anyways. Yeah. Sure, don't worry, bro. Don't worry. Our Discord is full of that. Let me see this. Ooh, I've just seen this now. That's crazy. That's very interesting. What I'm looking at right now is my Discord, by the way. I'm just looking at this. M sent this in the chat. It's actually very interesting. So whatever we've been doing, yeah, still continue on. I will look into this 100%, which is crazy. So yeah. Cool. Do you think a comparison with calculate and equalizer model? Potentially, it came up before. I doubt it will. But I'll go over like the properties of benzene and stuff, anyways. All right, should we start back up again? How long have I been live? I started at 3. Yeah, it's AQA focused. All right, let's go. Let's start again, man. At 7 o'clock, hopefully. We might run over depending on how quickly we finish stuff. Okay, back onto electrophilic addition. Let me pull up my PowerPoint and just see what I need to cover. Okay. All right. When are we doing NMR? After this, I'm going to quickly go over ozone, then IR spectroscopy, talking about carbon dioxide, global warming stuff, and then HNMR. Hopefully, we'll start. Okay, we're not that far. Okay. Let me see when is benzene as well. Benzene is after recrystallization. Okay, cool. Yeah, 100%. Arrhenius is coming up. I think Arrhenius is coming up. I think PVNRT is coming up. Time of flight is not coming up this year. Time of flight is going to come up as one of the multiple choice questions. Mass spectrometry might come up as a multiple choice. Yeah, and Born Harbor, that will come up as a definition or a. It's going to come up multiple choice somehow. I think so. They're not adding in paper 3. You guys are not going to have a nice paper 3. Yeah, you know what? Let's do that quick. Actually, no, we're gonna do that after electrophilic. BMZ, remind me that. Just tell me that again after we finish that electrophilic. Okay. So when we're just about to start ozone. All right, electrophilic addition with this molecule here. I want you guys to try this mechanism. Exactly the same mechanism as before. C double bond C, CH3, CH3, H, CH3. Okay, and this time you're going to be reacting it with H2SO4 until 7 o'clock. Can be. Till 7, but we might run over. Yes, Mouse, of course. Give me a sec. Let me go back to the bottom slide. There you go. Is that okay, Mouse? Cool. Now with this, right, I'm actually going to throw in a little bit extra content because I've seen this come up. They can actually ask you to draw the structure of H2SO4. It normally comes up more on your period 3 topic, but it could still come up. There's still no reason why they can't ask you to come up. Ask it, to go ahead and then draw the H2SO4 molecule. Essentially, it starts with the S. You have 2 double bond O's, and you have 2 OHs. Now, it's very important that you know why it looks like this, or how it looks like for this. You don't necessarily need to use this whole molecule. You can draw it in a different way, or write it in a different way, and I'll show you how you can write this. And there's multiple ways you can write this. First thing you're going to do is write down H. That's the first thing. Secondly, you need to start with the oxygen. Okay, because this H is your alcohol group essentially from here. Okay, and what is bonded to the O is essentially the S. So it needs to have the S next to it as well. Everything else doesn't matter. You can put SO2OH. You can do that. You can also do SO3H as well. That also works. But you need to have O and S in this order. You need to have O and S in this order. Check
Does this overall molecule add up to H2SO4? It does. Cool, happy. Okay, but H and O and S need to be in that order. Okay, I'm gonna stick with OSO2OH like this, but OSO3H also works. Send it in the chat, Shah. Come. Send it in the chemistry chat. It might be because I'm on streamer mode right now. That's why, because I'm streaming. So I think it might not let you DM me just because you haven't added me. Okay. Now, exactly the same thing. We need to think about which is the major and which is the minor. So, bond breaks, or arrow from the negative area goes to the delta positive H. This is the delta negative. Okay. Bond also breaks here. Make sure you're attaching the bonds correctly. And then what I'm going to do is I'm going to split this double bond. So this becomes C sigma bond C, H, CH3, CH3, CH3. Which carbon is going to be my more priority carbon, which is a stronger carbon? It's going to be this one. Why? Because this is tertiary. Okay. If I ever ask you about the major product stuff, I've seen this happen a lot more now. They don't used to do it that much anymore. But you also H2SO. Sorry, this should be OH there. Sorry, that should be OH. Sorry about that, not me. Yeah, you're right. Yeah. So with major product, there's also a little script for this, exactly very, very similar to your positive inductive stuff. There was just a beeping outside. I don't know if you guys can hear that. But so what I'm going to do is attach the H to this one here. Yeah, we are peaking, Rico, man. We are. Everyone's locked in, bro. Click it. Click the tick, Shah. Just click the check, bro. Click the tick box. And then it'll just it'll give you all the channels. And then what we're going to do, SO2OH, we need to have the negative charge. I'll tell you where the negative charges are all the time. It's always going to be on the first carbon. Or the first molecule, I should say. Or even atom. Negative, and then a lone pair. This is a plus. Attaches. If it just asks you for the mechanism, will you lose marks for drawing them with the minor product? Yes, Asib. Yes. Even in AQA, all specs they want you to draw. No, you will. They want you to draw the major product. Major product. Don't do minor. Do major. You will lose marks for minor. Very, very. If you're lucky, you'll get marks for the minor. Most of the time, they'll tell you draw a mechanism with the. Yeah, you're gonna lose marks with it with the minor. They might, Rico. Why is a major more stable? Good question, Snape. Good question. So, reason being, this carbon here, what type of carbon is it? It's going to be a 1, 2, 3. This is a tertiary carbocation. Okay, this is going to be more stable in comparison to the other one, which is going to be a primary, even a secondary carbon cation than secondary carbocation. And then we need to include this line here. Tertiary has more of a positive inductive effect. I've noticed this a lot more in terms of mark schemes. Okay, add this in. Still can't send. What did it say? What error did it say to you? Oh, I know why. 1 second. I think I know why. It's probably disabled the files, so I'll enable that real quick. Give me a second. Okay. Cool. Anyone know what the name of this is? This is going to be the major product. So why this is like a 3 marker for the major product. Okay. Add this. Can you guys name the product? More alkyl groups, you need to talk about the positive inductive effects. Okay. That's what makes them more stable. Where the hell are you? Would this always be the answer? Yes. How do you know if it's tertiary or secondary? See how many carbons are attached to this carbon here. So this here has 1, 2, 3. This is going to be 3 carbons, so it becomes tertiary. Okay. Whereas in the other one, if we attach this I don't want to give it away what this group is called. This part here onto this C, we only have 1 and 2. So this would be a secondary. Okay. See how many carbons are being attached to that carbon. Okay. Does this affect which carbon the H joins to? Yes. Okay, we need to make sure that the H attached to the minor. Good try, Ibrahim. Good try. I've seen it like very. I think I've seen one question where it asked for the name of this, and I don't know. I don't know if it was I don't think it was a past paper. So yeah, very close, Ria. Ria is the closest so far. All right. In terms of how we name this, let's look at the longest chain. So I'm going to redraw this. We have CH3, CH3 here, CH3 here. We have a OSO2, OH here. And then we also have H's here. Our longest chain at the moment is, well, this is going to be our priority group, right? So our longest chain will be 1, 2, 3. So this is a propane. Okay, we have 2 methyl groups on the first carbon. So that's going to be 1,1 dimethyl propane hydrogen sulfate. I probably should say 1 hydrogen sulfate. So that becomes your priority group. It's a hydrogen sulfate group. Is it 4 carbon? 1, 2, 3. Yeah, did I miss off a carbon here? It's because this is a priority group. Actually, no, you guys are right. Yeah, 100%. No, you're right. Yes. So yeah, so that becomes 2. That's yeah. I'm gonna change that. No, you guys are right. Absolutely right. 2 hydrogen sulfate. We have a propane, butane. So this becomes a butane because of the 4 carbons. Methyl is on second carbon. So that's gonna be 2 methyl. Yeah. 2 methyl butane, 2 hydrogen sulfate. Okay, it's not diol. In this case, it's not considered diol. I've seen it once, Yamlika. I don't think there is. I don't think they'll ask you. It's very unlikely. It's butane. Thiosulfate. I can see why you're saying thiol, but it'll be hydrogen sulfate. For priority groups, Luke, there's not really a sheet. I would advise that your priority groups, the ones that if it's carbon 1, there's 3 or 4. Okay, carboxylic acid. Okay. You also have your ethanol chlorides, okay, and your aldehydes. Okay, so these are your priority groups, and even actually nitrile. Okay, let me make a list of that real quick. C double bond OH, C double bond OCl, C triple bond N, and your C double bond OH. These are your 4. I'm gonna say there might be more if there's any more. If I've forgotten, just let me know. It's just coming to my head right now. These are your 4. This. Why is the chain not 4? It is 4. Butane. 1, 2, 3, 4. BFC. Amides 2. Amides. Yes, amides. That comes under your C double bond O stuff. Okay. Your naming. Don't worry about the naming too much. I'm gonna say it's like a 2% chance that the name is gonna come up. I'm gonna be real. Okay, this is AQA, but this can 100% come up in OCR. Okay, the mechanism is what you should be more concerned about, and making the major product. That should be your major focus. Why is it not dimethyl? It's because there's a 4. Okay, 1, 2, 3, 4. That's your longest chain. Hydrogen sulfate on the second. CH3. Okay, and I take back the fact where I said earlier this is a priority. It's not a priority. Will there be a paper 3 live stream? Mechanism finished. It is finished. Yes, you need to know the mechanism. That's the whole mechanism done, and this is your final product. Yeah, of course. All right. Your next example, I'm going to give you guys one more for this. C double bond C, C, H, 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 CH2, C, H, and H. And what you're going to do is you're going to go ahead and react this with, go on, you're going to react to H2SO4. I don't care about the name. Essays, scripts, and essays. I don't care about the tenor, guys. I don't care about the tenor, bro. I really don't care. I don't even know how to set up the donation or anything, man. I just got the stream, bro. That's it. I just put on the stream and we just wing it. Yes, RS. Literally right after this. Right after this. I was gonna do it at some point. Where's it gone? Yeah, we'll do it. Yeah, we'll do it with this. Okay. Well, I'm also gonna mention actually while you guys have probably already done this, right? If you haven't, that's also okay. I'll do the mechanism with you guys. But the key thing with I've actually forgotten what the hell was I gonna say. With free radical substitution is that it can come up a lot in actually your organic synthesis. Specifically because I think a lot of people know about the free radical substitution stuff, but I think when it comes down to your mechanism or in terms of questions of using it or applying it, it's harder to think about because it doesn't come up that much. And I'll show you what I mean by that. So just by finishing off this mechanism, this becomes a CHH. The H is going to go here. This is going to be a single bond C. It's going to be a CH2. This is going to be a CH3. Okay, this is your priority, or I should say your more stable carbocation. So you get OSO2 OH, lone pair, negative, goes to this part. That's your final mechanism done. Most mechanisms, to be honest, in OCR, they want the final product. In AQA, to be honest, if you don't put the final product, you should still get the mark, unless they say so otherwise. There might be some Pfizer, probably just some outside. My window's open in the back because it's so hot. An alcohol. Yes, programmer. That's for your hydration and dehydration scripts. Yes, you're absolutely right. You guys are absolutely right. Yeah. Okay, but specifically though, you don't really see any terms of like they don't say make this mechanism and then add water. Instead, what happens is in terms of your hydration scripts, or not hydration script, your hydration mechanism, what happens is your H2SO4 is essentially your catalyst, right? But this would be your intermediate when you're making your alcohol with this. So essentially what happens is we add water, so this is your hydration. When you're turning an alkene to a alcohol, okay, this is how you're going to do this in terms of this. Okay, first thing what we're going to do is add a H+. Why do we add a H+? It's because of a H2SO4 catalyst. This is your different mechanism. Double bond to a H. What happens is this attaches like so. But wait, we have 3 bonds on this carbon, so this is going to be a positive charge. We're going to add water to hydrate it. This has a lone pair, negative to our positive. The whole rule we'll be following from before. And the H+ is your catalyst, by the way, programmer. Yeah, I keep saying programmer, it's pro gamer. My bad. Anyways, this attaches. This becomes CH3, H, and then we have 3 bonds on our water, on our oxygen. We don't want 3 bonds. This is O+, negative to positive, and our final product is just going to be H3C, and then this is going to be your ethanol. Okay. Does that make sense for your hydration? You need to know from alkene to alcohol, you need water, and you also need H2SO4. Okay, you can't do H2SO. No. You need the H+, because that's where the starting molecule comes from. That's where the CH3 comes from. You need the H+. Without the H+, you can't do it. Okay, if you decide to do H2SO4, that's fine. This is actually what happens in reality. The OSO2 OH binds off, and the OH kind of swaps. But this is the whole mechanism. Okay, you will get the full marks for doing this mechanism here for hydration. Why does the O become positive? We don't want 3 bonds. Oxygen has 3 bonds on it. That's why it's positive. Okay. All right. Let's move on. As much as I want to do dehydration as well, dehydration is just backwards. I'm not going to do dehydration. Okay. If you do want to know about dehydration, essentially what happens is you still have a H+. This is a lone pair. It attaches, and it just happens backwards. Okay. Try to think about what happens. You're trying to get rid of that OH group. Okay. I want to go over your free radical substitution. Yes. Yes, it is electrophilic addition, yeah. Water's fine. Water's fine. We don't have to worry about steam in this case. Free radical substitution. I'm gonna bring up this question here. I know that it's not exactly the same. In fact, you know what? I'm not gonna use that one. I'm gonna use this instead. This hexo, this cyclohexane with the H and H2O B delta positive. Yes, Jeremy. If we want to convert this to this, we use free radical substitution. Okay, a lot of people get confused with the fact that, okay, they have a normal alkane and they're like, and when the question tells them convert this to a bromo, they're like, okay, how do I convert it? Okay, you guys know it. You guys know it inside. Like, you guys learned this in year 1. Free radical substitution. To convert this to this, you use this mechanism, and essentially the reagents for this would be Br2 plus UV light. You won't really be asked in terms of, you know, draw the mechanism, because I know in terms of cyclohexane it's a bit harder. But for example, if you have CH4 and you want to convert it to CH3Cl, I want you guys to try the free radical substitution for this. Do your initiation, do your propagation steps, and also do your termination steps. Okay, it's a pretty simple one. I know I'm not going to make it too complicated in this case. Free radical, just because it's a small topic. I want to try to get to HNMR as soon as possible. That's my main focus. But yeah, can you do alcohol to carboxylic acid? That's your, what's it called, oxidation stuff. No, it's just UV light. UV light is fine. Okay. Oh, sorry guys. Okay. Initiation. Well, obviously we have UV light as our conditions. Oops, I don't know why I put initiation. UV light. Okay, initiation will be your chlorine goes to 2 radicals. Okay, you can put 2 Cl radical if you want, chlorine to chlorine. Your propagation will be your CH4 takes this radical, goes ahead and reacts with this. Okay, and then what happens is you make a CH3 radical and you make HCl. What also happens is, because this is happening in 2 steps, you don't just have one molecule, you have millions and millions of these molecules. You have CH3 radical, goes ahead and reacts with a Cl2 from the beginning, and this makes a CH3Cl plus a Cl radical, and this radical can go ahead and react with this again. Okay, cool. Your termination step, that's just going to be any sort of radical reacts with a radical. You can have CH3 radical plus CH3 radical. It doesn't matter with the dot is, to be honest. You can just put it in front, and this makes C2H6. That's one of your steps. Another step might be Cl plus Cl makes Cl2. That's also valid. I would probably avoid this one. It is a valid step, but I would try to avoid it. And another one is CH3 plus Cl radical makes CH3 Cl. That's also a termination step. Okay, in my opinion, this is the nicest one. This is the one I always used to put. But those two are completely fine. Okay, just any 2 radicals. Those are your termination steps. Okay. Do not forget about your free radical substitution. Just one S. This one. Okay, I'm gonna show this question for ozone. Don't avoid doing 2CH3. Oh, for termination? Good question. I think you'll be fine. You should be fine with that. Okay, I want to look at this question. I think this is a really, really nice question. And this is to do with ozone stuff. And you need to know your equations for these. These, in my opinion, they are literally 3 marks. Okay, if you ever see this word, chlorofluorocarbons. No, Matty, no, it doesn't. No, it doesn't. Okay, if you ever see chlorofluorocarbons, CFCs, this is 3 marks. Literally 3 marks. Okay, to be honest, I wouldn't even read the question. I'm going to be honest, man. This is all you need to know. Okay, you're going to be using chlorine as your radical. Okay, actually, I take that back. Read the question. Make sure you read the question. Okay, chlorine is going to be your radical. Why? In this case, you can see we have CF and CCl. If they ever ask, your CF bond is really, really strong. Okay, it's a really strong covalent bond. Okay, in comparison to CCl, which is a weaker bond, it's more likely to break. Now, what happens is, because ozone is in you know, protecting us, UV light from the sun breaks it up. Okay, and this causes CCl to essentially pop off and make a Cl radical. Okay, and we're able to have two equations without ozone, and you need to know these equations by heart. Your O3 plus Cl radical makes a ClO radical and O2, and another O3 reacts with this ClO molecule and makes 2O2 and your Cl radical. If we make Cl radical at the beginning and we had it at the start, what is that? What is the word for that? Yeah, give me a second. I'll go back to dehydration. That's hydration even. Yes, UB, yeah. Amazing duo. Catalyst. Cl radical is a catalyst. Okay, it is regenerated at the end. That is your 4 marks. Okay, that's 4 marks. Okay, if it ever asks about your bond being weak, or why does Cl pop off, why is it Cl radical and not an F radical, it's because your Cl bond is much weaker than your Cf. Okay, someone wanted to take a screenshot of the hydration one. There we go, that's the hydration mechanism. Oops. There we go. Hopefully that's okay. Alright. Next bit. Will apply to OCR. This ozone stuff won't apply to OCR, but the mechanisms will. Okay, mechanisms will pop up for OCR. Alright. Infrared stuff. I made a video on this yesterday. I don't know if you guys watched it or not. I think some of you did. Infrared spectroscopy. Spectroscopy. Oh yeah, catalytic converters. Thank you for reminding me. Actually, before I move to infrared, let me quickly show you this real quick. Okay, this please cram this in your head. This is a cramming equation. Learn these two. No, not yet. Okay, these are flue gases. These are flue gases. Cram these equations if you see anything about flue gases. Cram these equations if you see anything about catalytic converters. Okay, I'm not going to go over any explanation. Just learn it. Alright. Was flue gases paper 1? Was it? Alright, don't need it then. That's cool, don't need it. I mean, I'll keep it there, but you probably don't need it anymore. If it was paper 1. Alright, but catalytic converters, this is your script. That's all you need to know about it. Okay, it converts your toxic gas into these less harmful gases. Okay, cool. If it was, then that's alright. Okay. For what? Catalytic? No, that's it. Not that I know of, anyways, or that's coming to my mind. There might be, but that's what I've got for now. I believe it's just this. It's just this. You might have NOx. You might have NOx potentially. N2CO2H2O. There's no water. Platinum. Platinum is used. Zeolite catalyst is to do with the cracking. I recommend that you guys go over cracking as well. It could potentially come up. I don't think it will, but it could come up. To be fair, it hasn't come up in a while. Okay. Okay, IR spectroscopy. If you guys watched the video, I want you guys to try this question. Okay. Not this question. Actually, I will leave this question on the screen as well. I want to go over this in a second. But I want you guys to try this question. Without using your formula book, try this question. Okay. You can probably get it very, very quick. And if you finish that, try to attempt this question. I will put this on screen. Okay. I'm going to go to the toilet real quick. I'll be back in like 2 minutes.
Okay. I'm back. Alright. First one. I'm gonna move these out of the way. Don't even need this. Alright. If you guys watch the videos that I put on my most recent one. Where's my pen gone? Okay. You can see that this has a really tall peak. This tall peak represents a C double bond O. Now you can see here, this is a difference here. Is this peak a smooth peak or a fat peak? I mean, a smooth peak or a jaggedy peak? It is actually a smooth peak. But what is this? This is actually your CHs. So this is actually going to be your OH alcohol peak. And you can see this is really jaggedy. So this is going to be your OH acid peak. And both of these, as you can see, they still have this long peak here. Someone in the comment section did ask, is it a C double bond C? No, it is not. It is a C double bond O. Okay. Now, if you'd ever had a C double bond C, it'd be a really thin peak. It'd be like that. Okay. You can easily differentiate. You don't even need to look at the formula book. Now we can compare. This, you're absolutely right. Carboxylic acid. This one is going to be some sort of hydroxy ketone or hydroxy aldehyde. And this one is just double bond O. Well, here we have an ester group. So this is going to be F on the top. Okay. Here we have an OH alcohol group. So this one is going to be G. This is your hydroxy ketone. And then lastly, what have we got remaining? E. Don't even need the formula book. Okay, that's how you guys do it. 3 marks. Infrared is literally 3 marks. Okay, cool. Next bit here. State how the infrared spectrum of carbon dioxide in figure 3 is not what you might predict from the data, providing table A and data B. Which one's arene again? Arene's like your benzenes. Arene. Yeah, arene's your benzene stuff. It's like, this one's your C double bond, it's CH here. Is it free? Yeah, it's free, it's 3 months. Oh, you said 3, it's free. F-R-E-E. Okay, anyways, state how the infrared spectrum of carbon dioxide. Well, carbon dioxide is going to be this, right? Now, the reason why it actually varies is because you can see on this double bond C, we have 2 double bonds essentially, and that's why it kind of distorts your infrared spectrum. But essentially, you'll say that your C double bond O is not on what the data book says, which is 1680 to 1570 to the minus 1. Okay, whenever you're talking about the peaks, make sure you're talking about from the formula book in terms of reference to the wavelengths. Okay, just copy directly. Okay, in comparison to the figure. And then I'll probably put as well where it is on. It's like 2300, 2250. Okay. All right. Explain how carbon dioxide causes global warming. Now, I think there will be a question like this because I think it's so like small. I think it will pop up potentially. Okay. So essentially, talk about this peak here. Okay. Carbon dioxide bonds specifically, so these are your C double O bonds, or you can just say C double O. Okay, and I should probably say C double O. C double O bonds, they are absorbing infrared radiation. Okay. Now your carbon dioxide, when it's in mid-air, when it's in the atmosphere, it absorbs your infrared radiation. And what's the frequency of that infrared radiation? It's this. Why is it infrared? Well, it's infrared spectroscopy, right? So it's going to be infrared radiation at 2250 centimeters to the minus 1. Okay. And then the IR radiation is then reflected back to the Earth which raises global temperatures. Okay. Does that make sense? So it just uses the context of this. Now it's a very small part of the spec. Oops, I don't know why I dragged that there. I'm supposed to drag my Streamlabs so I can see YouTube chat. There we go. Okay. You can say absorb and emit. Yeah, that works. But you need to say about the fact that the IR spectroscopy
the IR radiation is absorbed. That's the key thing. Okay, and that the temperature is increasing. All right, cool. That's it for IR spectroscopy. I can't lie. I'm gonna go over this part here as well. I'm not gonna go over IR spectroscopy too much because I think it's just use this rule. It's gonna help you a lot. Okay, let's go over this one. I think this is a really good question. Oops, there we go. It's a really good question. You've probably seen this before if you've been doing the past papers. But describe how you can use tests to distinguish between these. Okay, and we're going to start NMR literally after this. Yeah, I think we might actually run over, you know. I'm looking at this. We might run over. That's alright. Yeah. Okay. If you have a go at this question, it's a 6 marker. I think it's a really good 6 marker. Yeah, wallpaper engine, bro. Of course, you already know. Both Dodo. But it'll be primarily on HNMR first. I mean, HNMR, but we'll go over carbon NMR a bit. I'll show you how to do carbon NMR with like benzene and stuff. Okay, you said tolerance first. It doesn't really matter which one you do first. Essentially, what you need to do is kind of get rid of, kind of test for one and then cancel them out. Last bit of the question, one of the tick boxes, how to differentiate between the two molecules, they both have OH groups in them. Actually, yeah, of course. It's because, as you can see, this is OH acid. The jaggedy is the OH acid. The smooth is the OH alcohol. This little peak here is your CH, by the way. Okay. The jaggedy fat one is your OH acid. All right. Let's go through this. Essentially, what we need to do is we need to cancel them out one by one. Okay. So at the moment here, we have a carboxylic acid group and we have an OH group. We have a bromine here and a primary alcohol. We have a carboxylic acid only, and we have a aldehyde. First thing I'd probably do is get rid of the aldehyde bit. Okay, so what we're going to do, we're going to put tolerance in all the solutions. Tolerance reagent. Tolerance reagent in all of the solutions. Then what's going to happen? Only N, only N forms a silver mirror. So essentially you have 4 unknown test tubes, 1, 2, 3, 4. We put the solution in all of them, and what happens is only this one makes a silver mirror. Then we can move it. We can say this is N, and say, okay, we're going to do the test on the next 3. How did I choose G and E for both? Because this has C double bond O, and this is they both have C double bond O. This is OH alcohol. This is OH acid. If it's an OH acid, you can only make that when you have a carboxylic acid. Okay, so if I go back to this molecule here, you can see that this is this part here has to be carboxylic acid, whereas this one is not. Okay. Tolerance and AgNO3. So you're saying AgNO3. Failings is fine, yeah. Yeah, failings are absolutely fine. There's not one right answer with these, by the way. So what I would personally do after that is I'll probably use AgNO3 as well. One second. What would I use? 1 second. Primary alcohols. Yeah, no, yeah, I'd use AgNO3. Okay, and then what happens is AgNO3 will create a... What type of precipitate do you make for bromine? Yes, Angie, you can. You can. But you have to be careful about that. I'll tell you why not. Why do we use AgNO3? Good, Michelle. Good. We make I don't dawdle, but if you want to ask me something, I'll tell you if you can use it. Good. We make a cream precipitate. Okay, so this is essentially your halide test. Precipitate. Okay, why? Because we have a bromine bit here. The reason why I'm avoiding using our potassium test right now, our potassium acidified potassium dichromate, is because at the beginning, and you asked N. We can't use it for N straight away because this will react, but this will also react. and this will react. So we have three things that react. We need to have a test that causes only one thing to have a positive answer. Okay, so yes, this will make a cream precipitate. Specifically, absolutely right, Afreen, you make silver bromide. Okay, I'm gonna say yes and no to that, Jeremy. I'm gonna say yes and no. I've seen a question on it. I've seen a question. I know exactly which question you're talking about. And I've seen a. What I would recommend is you just understand which one's a condensation and amide bond polymer, and which is a normal polymer. Okay, that's probably the best advice I can say. Don't bother memorizing it. The structure is just too long. Okay, it's actually very, very long. I don't think it'll pop up. I think they took it off the spec. I think that was a very, very old question, maybe in 2017, 2018. But I think they took it off the spec. All right, best thing I would say is memorize what type of molecule is it. Is it amide, linkage, S linkage, or is it a CC? Polymers, potentially, maybe. Let's have to check on time. Okay, after we've done this, well, we've cancelled out N. We've cancelled out, we should also say, for only L. Now we've got K and M. How can we differentiate between K and M? Anyone know? What can we use? And why? We can't use sodium carbonate. The reason why we can't use sodium carbonate is because both of these have carboxylic acids. Can't use sodium carbonate. No. Both of them will react. What can we use? UB, we use AgNO3s because we're doing a bromide test. Okay, we're doing a bromide test, that's why. We're testing for that bromine bit. Absolutely right, guys. We're going to be using acidified potassium dichromate. Why do we use acidified potassium dichromate? It's because of this OH bit. Okay, when you have carboxylic cycle, we can't use. Why do you want to say litmus paper? It's because both of these will be acidic, no? Both of them will be acidic. But the reason why we use acidified potassium dichromate is because the carboxylic acid is not the bit that's reacting. Okay, that can't get oxidized anymore. The only bit that gets oxidized is this hydroxide bit. So actually in M, you have no change. M will have no change, K will. I can understand why you're saying it's a tertiary alcohol, Ibrahim. I can understand why you're saying that. But because it's a carboxylic acid group here, this still gets oxidized. I can understand why you're saying it's tertiary alcohol. It won't be considered. It'll be considered as a. Actually, no, it's not. It's a secondary. It's a secondary. It's not a tertiary. It's a secondary because you have 1 and 2. It's not tertiary. All right, cool. So we're gonna use acidified potassium dichromate. Okay, and then your positive test only K will have a color change. I should probably say in reflux, but it's fine. It will have a color change to green, and then you can also talk about no changes. I would also recommend that you say M has no change. Okay, perfect. All right. Yeah. Shah, don't be rude, man. Not yet, Kitty. Not yet. All right, guys. We're gonna start with some HNMR. Finally. Ooh. Okay, let me get my notes up for HNMR. Where is it? HNMR. Okay. Start with HNMR. I'm gonna stay on here for now. There are 3 things we need to know, and for the OCR guys that are still here, I will also so be ready for this. Okay. TMS is relevant for everyone. TMS is a reference molecule, and I recommend you learn its properties using this acronym, LINE. Really good. Okay. First of all, TMS has low boiling point. Do not say melting point. Say boiling. Say boiling point. Specifically because we're able to separate it out and remove it very easily. Okay. Secondly, it's inert. It doesn't react with any of your samples. Tertiary. Thirdly, it has 1 peak. Okay. Specifically at 0 ppm. And lastly, it's non-toxic. These are the properties for TMS, and you need to know them. Okay, this is NMR. Okay, TMS, you need to know the structure for this. Silicon and 4 CH3s. Specifically, it will be in a tertiary structure. I don't know why I've drawn it like this. Okay, it will be in a tertiary structure. The COOH, it will make it acidic because it's a carboxylic acid. What's next? 0 ppm. This means 0 ppm, meaning, so essentially when you put your sample into the NMR, it can't automatically detect. So you have some peaks, right? But it doesn't know where the peaks are until you say, okay, TMS is 100% at 0. It's about your calibration. So the purpose of it is a reference molecule. It's for your calibration. Okay, you need to know how this looks. So this is it's called tetramethylsilane. Don't need to know the name of it, but you do need to know the structure. Now, there are some solvents that you're going to be dissolving, not necessarily your CNMR stuff, but for HNMR. And there are 2 you need to know for AQA, and then 2 you also need to know for OCR, and I'll mention them. Okay, for AQA, you need to know about CCl3 and CCl4 and CDCl3. Okay, for OCR, you need to know about CDCl3 and D2O, and potentially CCl4, but I'll go over that in a second. Volatile unreactive, that's fine. That's okay. So these 2 solvents, they're both used. Actually, all of these solvents are used because HNMR, this also uses radio waves, by the way. This is one marker. It uses radio waves. Essentially, all of these have no protons. HNMR can only detect hydrogens with an odd number of MR. So it can detect H1, so it can detect protons. It can detect H3s, H5s, and so on. But it can't detect it with even numbers. So this D essentially represents deuterium. So it's an isotope. Good question, Luke. It's just because, for example, HCN, it's just for you to be, it's just a property of it. It's just a property. Okay, it's just a good thing. If it's not toxic, it just means it's just a better thing to use. Okay, so deuterium, D essentially is an isotope with 2 MR. So it has 1 proton, 1 neutron. And we use that as our solvent. Now, what's the difference between CCl4 and CDCl3? Essentially, CCl4, and even both of these molecules, they're both tetrahedral. Okay, but CCl4, all your dipoles get cancelled out. Okay, so this is a non-polar solvent. If it's a non-polar solvent, what you use is you dissolve non-polar molecules in this, or your non-polar sample. In comparison, CDCl3, this is not non-polar, it's a polar molecule, or polar solvent, so you dissolve polar samples. Okay, that's the whole purpose of using these. And this also applies to OCR. For D2O, you don't really need to know much about D2O, to be honest, in AQA. But essentially, the purpose of D2O in OCR, I'm just going to go over this briefly. If you have carboxylic acid groups, or OH groups, or NH groups, what happens is in your peaks do not appear anymore. Because what happens is these get swapped out for ODs. Okay, and your HNMR can't detect deuterium. So essentially, you have no peak for that. Okay, it will always tell you if there's a D2O, what sample is using. So you can just take account of that. Okay, that's all you need to know about D2O, and just take account of that in terms of your question. All right. Let me get some questions up. Give me a second. Where's HNMR? Okay. You know what, let's start with this, but let's start with this. So I think a lot of people struggle with the fact in terms of selecting the environments. I'm going to start with CNMR. CNMR looks at C13. God, I don't want your tenders, man. Bye.
If I wanted a tenner, I would put a price on this live stream. I'm not Bison, bro. The leak is crazy. Yo, I actually want like access to the papers, but I'm not like an official teacher or anything. Only like the teachers in schools, they get access to the papers. You know, I'll take that. I'm joking, man. No, I don't want it. I have to do my paper 3. Okay, so for both HNMRs, look at symmetry. I teach all my students this. Symmetry is the main thing. Okay, so in this case, our symmetry line is down the middle, and you can see. Now they get access after they get access right after the exam is done, and then they get the mark scheme 24 hours later. Total. Yeah. Yo, stats and mechanics for 50. Yo, I don't want the 50, man. That's appealing though. It's not bad. It's not a bad price. Not a bad price. But okay, the amount of environments this has, you can see these are in the same environment. So, sorry, not in the same environment. They have a line of symmetry. Therefore, they are in the same environment. See that? You can see that this has a CH3. This also has a CH3, and it's just down the middle. Okay. These will both be in the same environment. Therefore, it has only one peak on your CNMR. This also applies to your HNMR as well. There's a symmetry down the middle. H, that's one environment. But because there's a symmetry, these are also part of the same environment. So these are both one peaks. Okay. This question, again, very, very similar. There's a symmetry down the middle. Okay. These will be part of the same environment for CNMR. And then what's left in the middle? 2. So you have 2 peaks for this. This also applies to HNMR. 1, 2, 3. 1, 2, 3. Same environment. Okay. And that will be your 2 peaks for your HNMR as well. Okay. Symmetry is key. Look for symmetry. Now, in terms of splitting, I'm going to be doing HNMR and CNMR kind of at the same time. I know I shouldn't really be, and when I've taught this, I'd split them up, but I'm conscious about time. We have to be careful about splitting. So, HNMR splitting, this is 1 peak and this is 2 peak. This is your second peak. It doesn't really matter, or environments, I should say. This is going to be the integration of your first peak. Okay, how many hydrogens are in that same environment? We have 6 hydrogens in that environment. Therefore, your integration is 6. In our second environment, we only have 2. So that's going to be integration 2. Now we need to think about the splitting as well. Splitting also comes up. Both. It's between carbon and hydrogen kind of at the same time. Okay. Now in terms of our splitting, we have to see what is kind of next to it. So this carbon and our peak 1 has, well, another carbon. How many hydrogens is on that carbon? 2. We use something called the N+1 rule. So if you have 2 hydrogens on that carbon, 2 plus 1 makes 3, therefore it's a triplet. So this peak here on environment 1 has integration 6, and it's a triplet. Environment 2, how many peaks do we have, or what type of splitting is on environment 2? This carbon, or these 2 hydrogens here. What's our splitting on environment 2? Yeah, of course. So the carbon we're looking at on the first one. Okay. The carbon we're looking at the first integration. Which one is it? Which one is it? Multiplet or quartet? Which one? Which one? Which one? No, splitting. No, splitting and integration not for CNMR. No. Quartet and multiplet. Which one? Pick one. It's a multiplet. Guys, it is a multiplet. Because we have to look at both sides. Okay. We have 1, 2, 3, 4, 5, 6. This is an integration of 6. I know you guys are looking at the same side. But it's going to be a multiplet.
Okay, it doesn't matter if it's 6 peaks or whatever. It's just more than 4. So you have singlets, doublets, triplets, quadruplets. Anything above quadruplet is going to be your multiplet. Okay. Let's look at. I want to continue looking at in terms of your peaks and stuff. Okay, and we're going to be looking at splitting. I feel like CNMR should be okay. If it's not, don't worry. There's a bit of benzene stuff, so I'll go down and look at your CNMR stuff. Okay. This is both AQA, OCR, doesn't matter. HNMR is all the same. Okay, there is multiplets. So you have singlets, you have doublets, you have triplets, and you have quadruplets, and then anything after 4, or you can say quadrates as well, that also works. And then anything after 4 is multiplets. Yes, exactly, Cambig. I'll call it Cambig. Alright, how many peaks do we have on this molecule? Draw it out if you need to, okay? And then tell me environment 1, environment 2, environment 3, what is what, okay? So in terms of, tell me it's, you can say quartet or quadruplet, either's fine, fire it. Okay, tell me what type of splitting it is as well. Guys, that's saying 4 peaks. It is 4 peaks, yes it is. Okay, there's no line of symmetry in this. Okay, there's no line of symmetry, so it's just going to be 4 peaks. Each one will be on its own. Okay, that's 1, that's 2, that's 3, and this is 4. Okay, I'm going to call this environment 1, environment 2, environment 3, environment 4. What makes it a different environment? Again, symmetry. Luke is symmetry. Okay, if there's no symmetry in the middle, then they're all different environments. Okay, until 7 o'clock, but probably we'll run over, I think, just by the rate of this. Okay, all right. Let's look at environment 1. Environment 1, we're going to check the adjacent carbon. On this adjacent carbon, how many hydrogens do we have? We only have 1. Therefore, environment 1 is going to be a doublet. What makes 1 and 4 different? Good question, Victor. Again, there's no line of symmetry. It's because this carbon, this CH3 is bound to CH2, whereas this CH3 is bound to CHBr. There's no symmetry. So therefore, they're different environments. It doesn't matter, Raheem. Doesn't matter. Doesn't really matter. It's just symmetry. You can call it 1, 2, 3, 4. They'll normally, in HNMR questions, you're normally going backwards to make the product. So yeah. This is for HNMR. There's no splitting in CNMR. There's no splitting in CNMR. I know I'm trying to kind of mix it up. That's my bad. The plan was to separate them, but this time. Okay. This one in the middle, adjacent. So we have two adjacent. So here we have 1, 2, 3, but we also look on the other side, 4 and 5. That means this is going to be a multiplet. Environment 2 is a multiplet. Okay, both adjacent. Okay, environment 3, carbons are both 1, 2, 3, 4. Again, a multiplet. 4 plus 1 is 5. That gives you a multiplet. And lastly, the one on the end. When you have 1 adjacent, 1, 2. 2 plus 1 is going to be a triplet. Okay. Normally, I can't lie, you won't see multiplets. You're not going to see multiplets in your questions. Okay. This is just for the sake of doing practice questions. All right. What about this one? How many? Yes, Kitty. Your hydrogen environments in CNMR is very similar. Chances are your CNMR will be the same amount of peaks as your hydrogen. Sometimes it's not. But how many hydrogen peaks do we have in this for HNMR? And also, tell me its splitting, please. No. You'll never. Usually, you won't see multiplets. It's very unlikely you'll see multiplets. It's just for the sake of the question. Okay, I'm gonna draw this out as a displayed formula. So you have 1, 2, Br, H and H, CH3, CH3, CH3. This has 1, That's one environment. This has 2 hydrogen peaks. The definition of splitting is your singlet, doublet, triplet, quadruplet, that kind of thing. That's just splitting. There are 2 peaks. Okay, let's look at the splitting now. Well, on all of these, let's look at on this carbon here. On the adjacent carbon, there are no hydrogens on this carbon. I'm going to draw this out fully, actually. Let's draw this H's out fully. H, H, and H. On this is the adjacent carbon. On this carbon, there are no hydrogens. Therefore, this environment 1, this pink environment, is going to be a singlet. And same for the other. There are no hydrogens on that carbon. Therefore, it's also a singlet. You have 2 singlets here. Okay. How many... Okay, we're going to slightly change it up now. How many environments do we have if this is CNMR? In terms of... Now we're going to change to CNMR. CNMR environments. This is probably a bit more easier. Good. It is 3. Okay. So we have 1 environment here. 2 environments here. Literally for CNMR, just count how many carbons you have and then try to spot your symmetry. And this is your 3rd environment. Why? Because they're bound to the same C. Again, it's a type of symmetry. Okay. I'm going to look at benzene. The HNMR peaks. What do you mean the peaks? Or in terms of graphs. We'll look at the graph stuff. I have some questions in terms of the graphs. Okay, we're gonna look at HNMR in detail. Like, I'm not gonna skip over it much. Okay. Okay. How many peaks for CNMR here? And I'm gonna show you this. So use symmetry. Use the idea of symmetry. Alright, we've got carboxylic acids, benzene, recrystallization script, chromatography. Well done, guys. It is 4 peaks. An easy way to do it, again, line of symmetry. Draw down, and then this is what we have. This is your first environment, second environment, third environment, and your 4th environment. Cool. Well done. What about this one? Again, rotate your page if you need to. Line of symmetry. It's going to be your best friend. Three? Good. It is 3. I'm going to rotate this a bit so it looks like so. Boom, 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 boom. 1, 2, 3. That's the same color. That's 2 different colors. There we go. 3. Easy. Easy, easy. You're not going to get asked much about your benzene for HNMR, I'm going to be honest. In OCR, most of the time you kind of just look off the structure. It's very unlikely. In OCR, to be fair, you look at benzene a bit more to the HNMR. But if you look at the formula book, it just tells you there's a peak at that point. So it's not too bad. Alright. How about this one? A, B, C, or D. Or you can say the number as well. This is a bit more trickier. How many peaks do we have? Think about line of symmetry. Yes. Oh yeah, Arrhenius is there. You got the same 5? Okay, we're getting a mix of answers. Okay. It is actually... I'll wait a bit more, Oh, so it's a 20. You know, 20 is the right answer, guys. Guys, it's 20. Okay, the actual answer is D. There is no line of symmetry. So what actually happens is, because there's no line of symmetry,
every single carbon becomes its own environment. That's 1. That's 2. That's 3. That's 4. I'm running out of colors. That's 5. That's 6. That's 7. And that's, let me make another color. Blue. 8. Because there is no symmetry, specifically because of the sulfur. The sulfur has ruined it all. Okay? And actually this carbon bond here as well. Double bond. That causes every single carbon to become its own. If it was symmetrical, let's pretend it was symmetrical. What color were they using? Orange. Okay, I'm gonna draw another molecule. 1, 2, 3. Boom, boom. I'm not gonna put a double bond there actually. Okay, because that will affect the symmetry. Now we can have symmetry here. A line of symmetry is down the middle. So in this case, how many environments would we have if it was symmetrical? It's because of the sulfur. Actually, the way it works, essentially, you need to think about, okay, what is this carbon attached to? It carries on the whole chain. So it sees this, and it attaches to S. Whereas this one here, 1, 2, 3, there's no S here, so that has to be a different environment. Yes, exactly, RS. And this double bond here. But yeah, exactly. Okay. 1, 2, 3, 4, and 5. So if you said 5, amazing. Okay. Yes, Ava. Use it for HNMR, use it for CNMR, use the symmetry rule. It's gonna help you a lot. Okay. Here you can see the level of symmetry is in this case the same kind of CH3s on here. But yeah. Okay. One more for CNMR, and then we're gonna look at some HNMR questions. It's light, innit? It's light. It is light. But we're gonna look at some proper HNMR questions now. Yeah, just do this last question. And then I'm gonna skip this one. We're gonna look at this one here. Okay, yeah. We're gonna look at this question afterwards. How many peaks in this? This one's actually pretty easy as well. This is a benzene. Draw the benzene. 1, 2, 3, 4. Pretty simple. Line symmetry down the middle. It's make sure you count it properly. This is 1. This is 2. This is 3. And this is 4. Make sure you count the carbons on the ends. Those are part of it. So it's 4. We've been looking at mechanisms throughout Osman. Okay, but we haven't done the benzene stuff yet. So after HNMR, we'll be looking at benzene. It is 4. Alright. I'm going to pull up some HNMR. Have a read, have a try, and we'll go through it together. Okay, I'm not going to give you the formula book for your infrared stuff. I'm not going to do that. Actually, no, you know what, I am. I take that back. Let me pull up the formula book real quick for the HNMR. 1 second. I'll give you guys a screenshot for that. This is for infrared. And this is for HNMR. Alright, give it a try. See what you can work out. If you guys can't work it out, that's alright as well. We'll go through it eventually anyways. Why isn't it 3? It's because of the carbons on the end as well. Zn. Okay, so they count. Okay, I know this one's a bit tough. I'll give you guys like 3-4 minutes to start off, and then I know you won't finish it in that time. But give it a try. Okay. In terms of organic synthesis stuff, I really recommend that you learn your mechanisms. Draw out the molecule. It's essentially the same as that. Don't memorize that map of ChemRevise. I can't lie. That thing is so long. It looks like some next maze. I love that, bro. I didn't even look at that for my revision. What was the answer for the question before? It was 4. And G. Oh, you got a good point. Wait. He has a very, very good point. He has a very, very good point. Actually, yes. It's a very, very good point. Yes, it is 3. You've got a very, very good point. Got a very good point. Yeah, it's 3. It is 3. Yes, it is 3. Because it has a line of symmetry down here as well. Because of that. Shit. Damn. There's a line of symmetry down there as well. So there's 2 lines of symmetry. So yeah, my bad, guys. That's my bad. Okay. All right. Easy fix though. Still line of symmetry. My bad. It's name. It happens. L. You can say L. Okay, let's start with the infrared stuff. Yeah, RS. Well, yeah. 3 is the answer. 3 is the answer. Sorry about that. Sorry, guys, if I said 4. Sorry, guys. Okay. What have we got here? We've got an MZ spectroscopy. Okay. We've got this. So this peak here, you can see that we have a really big long peak here. Okay. This is going to represent your C double bond O. Okay. It says compound A has 6 carbon atoms and can be made from propene using several steps. Okay. So at the moment, this could mean anything. But just by looking at peaks and just the way that we know our shapes, well, this is clearly not your OH acid. It's not any of your hydroxide groups. It's not OH. Okay, and we don't really have any amines. We could actually have amines, so it's a possibility, but I doubt it will. It's most likely a CH. It's most likely is a CH. It doesn't have an OH as a C double bond O. It's alright. Okay, now your proton NMR spectrum. This is how I want you guys to do your proton NMR spectroscopy, okay? This is what you guys are going to do. For every single peak that you have, you're going to write this exact script, okay? Let's start with 4.0. And this will help you pick up this will literally get you marks, okay? Because the way that AQA NMR is laid out normally, there's like little sections. There's like, what's the peak at 4.0? You're never ever going to get a question like this. It's more even in an OCR style, okay? So let's start with the 4.0, okay? At 4.0, we have a single peak, which matches with only one of these. Well, 2 of them even, okay? It's going to be this one. Absolutely right, BMZ. Absolutely right. We'll cover that in a second. We'll look at the integration stuff in a second as well, okay? So, we're going to be looking at this one. The reason why we don't look at ROH is because of our integration as well. So, it's essentially 2 possibilities at the moment. It's either that or it's the 4.1. It's probably going to be this one. So, what you're going to do is this. You're going to draw that part of the piece. C double bond O, O, C. Now, I'm going to do this in a different color, and you can do it in a different color. However, I recommend your final answer needs to be in black. Luke is very thin and very short. Okay, it's very thin and short. It'll look like that. It's probably not going to be this one here. Reason being. Good question. Reason being. Why can't it be that? I don't have a valid reason, to be honest. I guess it's a bit of intuition. It's because it's gonna have a C double bond O. I'm gonna say that's my answer. Normally you will have a molecular formula. But yeah, your NH bond is kind of like a big fat peak as well. But you'll notice that if either there's the NH or there's a C double bond O. Oh, sorry, OH alcohol, or OH alcohol, OH acid. But it's going to be this one. Okay, now this 2H refers to your integration. So essentially, on this, you see this bold bit here. Essentially, it's talking about that's the HNMR being tested. That's the bit that's being HNMR tested. So we have 2 hydrogens on that bit, on that carbon. Okay, that bit that's bold, that's essentially your integration level. Yeah, exactly. So it's not singlet, it's a triplet. Okay, so if it's a triplet, it cannot be ROH. You're absolutely right. Okay, all of your hydroxides, these have to always be singlets, by the way. These are always singlets. I should probably say that out. All of your OHs are singlets.
Okay, and then if it's a triplet, that means on the adjacent carbon, like we figured out before, there must be a CH2, right? Because n plus 1 rule, 2 plus 1, it's a triplet. That is one of our sections. That is a puzzle piece. Okay, and you're gonna write this exact script down when you do this. Okay, first of all, you just write this down. Okay, you're gonna say that if it's a triplet, you're gonna say that adjacent carbon, exactly what we've just done actually. Adjacent carbon has 2 H's, and integration 2. You can just write integration 2. Therefore, 2 H's on carbon. Okay, if you guys have done that, done the whole question, great. Which is really, really good. Okay, exact same thing for each of the other bits here. Okay, I'm gonna move this one out of the way for now. I'm just gonna put ppm 4.0. Okay, and you should actually mention the ppm as well from the formula book, and then just plug that down. Next bit, we have one around at 2.4, 2.1, 2.2, 2.3. So ppm 2.3. That is probably this one. No, no, it can't be. It can't be. It can't be less than 1 because if it's less than 1 NK, then there's no hydrogen. Oh, are you talking about? Oh, yes. Okay, so if it's in that, yeah, that's the way that Bob said it. Yeah. So if you have decimals, you have decimal numbers, make it into the ratio. So you know how you do empirical formula, divide it by the smallest number and then make it into whole numbers. Yeah, that's what he means by that. Yeah, integration can never be 0. So yeah. Yeah. Okay, this part here, again, same exact thing. We have this one that's bold on here. This one's bold. What's our integration? Our integration value is 2. So I'm going to put 2 H's on this. Okay. My splitting is a quartet. So we're going to have a CH3 attached to this. So this is going to be your N chain. If the question doesn't tell you the number of hydrogens, that's a problem. That is a problem. Okay, if the question doesn't tell you the number of hydrogens, either they'll give you an integration value that you have to work out. They'll have to tell you, otherwise you can't do your HNMR without it. You just can't. Okay, I'll give you an example in a second. Let's finish off this question. I'll give you an example afterwards. Okay, this is our second piece. Okay, make sure you just write down this little bit here. Why am I using 3.1? Oh, sorry guys. Did I mess up? Oh, sorry. Yeah. Sorry. I misread that. That was me talking while doing the work. That should be a C-double-bond-O like that. Yep. That should be C-double-bond-O. Yeah. No, you guys are right. Cool. Still follows the same rule though. Okay. Double bond H on that, and then you attach the CH3 on the side. If both C's are connected to one O, did they have the same value in the data sheet? Yes and no. So what happens is with that, I've seen questions where it can slightly vary. I think I've seen an OCR question where it was like a 4.2 or 4.3, and then it was still like using this one. Well, not this exact one, but like you get the context. Okay, so it slightly varies, but what you can do is still use a molecular formula. How do you know the 4.01 is in the 3.1 to 4.2? Good question. My best answer is intuition. I'm going to be honest. They haven't given any in terms of molecular formula. Normally, you would get a molecular formula to see, okay, does it have Cl, does it not? It's just because there's a C double bond O here. That's why. Okay, I guess if you just use the information, page 18. Yeah, this will be page 18. So with propene, you need several steps. It could. I'm not saying it can't. Okay. Like, there's a chance that it could. And the final molecule that we end up with, if we end up with the wrong MR, that's a problem. Okay. Alright. Let's keep on going. We've just done the first two. Okay, this one's like 1.7. So 1.7 is probably going to be 1.6. Probably even this one, actually. But let me just double check. You don't get integration ratio. Integration ratio is just the amount of hydrogens you have on that carbon. Okay, so this is integration 2, so you have 2 hydrogens on this. So integration 2, so you have 2 hydrogens on this carbon. And then these blue ones are your splittings. Does that make sense? Okay, so this 1.61, I would probably say it's going to be this one here. Yes. Because we have 5 peaks as well. Just 1 second. Yeah. Okay, so we got C. Okay. Then we have 3 R groups. 1, 2, 3. And we only have 1 H on that. But it is a multiplet. But because it fits within there, and this is what I mean in terms of that exception. Now you can see it kind of becomes an R2CH2. That's where it becomes a bit tricky. Okay. Because we have an integration of 2 and it's still a 1.6, it kind of transfers to this 1.4 thing, but it's not. We still have to use that 1.6 rule. Does that make sense? Everything else doesn't fit. We don't have any RH. It's not a singlet. So the only thing it can be is this with the integration of 2, which essentially is your R2CH2. Does that make sense? Does that make sense or not? Okay, we'll keep on going. So this is not the AQA style question. I know I pulled a hard looking question. Okay, but this is the way you're going to pull up marks. Okay, I'm not asking you guys to make the final product. That's the hardest bit. Make the structure. Say it's a triplet. Say it's an integration. This will be 2-3 marks. This is automatically 2-3 marks. Okay, draw the structure. Mention the ppm. Say what type of splitting it is. Okay, this is going to be a quadruplet. Okay, therefore adjacent carbons on adjacent carbon has 3 hydrogens. Okay, and then talk about integration 2. That's also 2-3 marks. Okay, I'm going to go back over this because you guys are feeling a bit confused over this. This is ppm 1.6. Yes? This is ppm 1.6. The only thing that matches is this one here. But there's an issue. There's a HNMR. There's an issue. The issue is that if we draw a carbon with 3 R groups, and in the integration it says H. In the integration it says H. We can't BMZ. We can't because we can't make the original structure without the splitting. You get me? Okay. Then, but the question says 2 H's, so we just add on another H. Why is it 1.6? I've just read it off the graph. Okay, 1.6, 1.65, 1.7 still fits with that within that range. 1.6, 1.65. Okay, with AQA though, I don't think this is an AQA question. I think it is an OCR question. Yo, it's outside, man. It's outside. It's outside. It's not my brother, man. It's outside. These guys are screaming. Yeah, exactly, Aisha. Does that not make sense? Okay, because it has 2 hydrogens, it has to have on the integration, you have that. Okay, and if it's a multiplet, well, that means that there's going to be some hydrogens here with more than two hydrogens, so it's going to be a multiplet. But we'll leave that for now. Okay, I'm going to leave it like this for now. And actually, this is probably a CH2 like this as well. So chances are it probably looks something like this. So I'm going to bring this down like so. Okay, and usually what you'll see as well, if you ever see 2 triplets, yeah, if you see 2 triplets like this, actually no, I'll take that back. I'll mention that in a second. Okay, we'll fit it together in a second. We'll fit it together. Okay, 2 triplets. Okay, this is around 1.1. This is 0.7 ish. And then if each of these have 3 hydrogens, chances are these are going to be CH3s, probably CH3s, and they're different environments, and they're both triplets. So both of them will have with CH2s on the side. That's how it's splitting. Okay, so we have 2 of these. And remember, there can be overlap. Okay, there can be overlap. So these, oh, my light's turned off. So these, essentially, you're joining all of these together in some way. No, they don't. I'm gonna be honest, they don't. Okay, now we need to join it in some way. Well, I think this is a good place to start, this molecule here. Okay, you can see that this really looks similar to this part here. Okay, but we're missing this oxygen here. So this part, actually, chances are, this this is going to be flipped around like so. So I'm going to draw it again, flipped around. CH3. Anything that has a CH3 is going to be on the end of your chain. Okay. So you can see that this is the overlap. You're not going to have these two separate. This is going to be an overlap like so. You see that? Okay, so that's overlap like so. This CH2 in the middle, this is your two R groups, and these are multiplets, right? Well, this one's probably going to be here, most likely. But we'll worry about that in a second. What else are we missing? Well, we have a propene in the middle, and we have 6 carbon atoms. How many carbons do we have at the moment? 1, 2, 3, 4, 5. We're going to have another CH3 at the end. Okay, and that's it. That's your structure done. Yes or no? What you should do on these type of questions, spend time on these bits, on the mini sections, okay? Spend time on these mini parts. I'm gonna show you guys another question. I think it's easier, in my opinion. Let's start with this, okay? Let's start with this bit here. There's quite a range in terms of how difficult the questions can be in terms of HNMR. Okay, let's start with this. This is pretty simple, I think. Okay, just say 5.1, 5.2, what is that? Okay, and I'll show you guys how to do the next HNMR bit. I believe this is from 2023. Yeah, just 2023, yeah. Can I go through full structure again? In a second, bro. I'll show you how to do. I'll show you the structure in this because I think it's potentially easy to explain in terms of if we have it in sections. Because we don't have it in sections like in the previous question, it just looks a lot harder. No, you're not getting data sheet. Nope. No data sheet. No data sheet. No. Look at the graph. This one's AQA. Look at the graph and tell me what bond it is. Where's 1725? And tell me what that is. Good. C double bond O. Thank you. C double bond O. Okay. If it's a tall peak, if it's a really tall and thin peak, it's a C double bond O. Am I gonna do rates? Looking at time, it's 6:30, but yes, we'll run over. I'll push it to 8 o'clock. Okay, but I'm gonna pray at like 7 o'clock. So yeah. All right. How many carbons do we have? I mean, how many environments are there in molecule of Z? Let me zoom in a bit more. It's a bit blurry, but 1, 2, 3, 4, 5, 6, 7. 7 environments. Easy peasy. All right, you guys are cooking with that. All right. State the type of carbon environment that causes the peak at that. I'll give you the formula book for that. Let's move. 1 second. This is HNMR one. Let me bring the HNMR one down. 1 sec. This is a CNMR one. I'm bringing 1 second. 1 second. Don't use that one. There we go. Okay. CNMR one, 174. It's going to be esters to acids. But which one is it? RCO, yeah? Salima, you get the mark for that. Good, it is ester. Why is it not acid? Yamlika, you lose the mark for that. Why is it not acid? Why is it not acid? No acid peak. Good. There's no acid peak up here. There's no big fat jaggedy peak. So there is no acid. Okay. Good. Well done, guys. Alright. Now let's look at the HNMR. Some more HNMR. In my opinion, this is actually really, really nice. And I think you can pick up, in total, I think it's out of 11. You can pick up 10 marks pretty nicely without doing the overall structure at the end. Alright. This is exactly how I want you to do this, guys. Okay. What you're going to do is you're going to look at the HNMR. Let me bring the HNMR down. Okay. Attempt this question real quick. I'll give you guys 2 minutes to start, and then I'm going to show you how I want you guys to do this to get full marks. And you know, I'll zoom out slightly just so you guys can see the next part of the question as well. Okay, and if you guys want to rush ahead, for those who can, I'll also put the next part, which is essentially deduce the structure, and this total is 11 marks. Let me put my light on charge while you guys are doing that. Guys, it's a nice day, you know. It's actually like, it's not that sunny right now, it's actually really cloudy. Planning on going beach next week, hopefully, if the weather's good. And then, to be fair, you guys have 1 week left now. Yeah? That's so sick. 1 week left. This is AQA, but very, very relevant to AQ, OCR and editor. Guys, what are you doing in the summer? Anything interesting? To be fair, I'm off London as well soon. The guy living down south. For exams, yeah, damn. Yeah, 1 week left, boys. That's it, Saifola, that's it. To be fair, you have a bit at the beginning as well. You do have the molecular formula. I should probably given that. Molecular formula C7H12O3. Guys, if you want to write that down, C7H12O3. I will also. So you have a C double bond O, C7H12O3. That is your molecular formula. Should have given you guys that. Sorry about that. And you also have 7 carbon environments. There we go. Okay, that will be helpful. Good. Go through sleep. We have not gone through benzene yet. No. After this, we'll be going through benzene, recrystallization, and start carboxylic acids. Yeah, I'm studying econ. You can pick up quite a bit from it, Julia. Studying pure econ at LSE. Your favorite stream. Are you gonna clip me, bro? You're gonna clip me crazy. You're gonna draw the whole thing at the start of the exam. No, props to you guys. You've been here since from the start of the from the stream, doing really, really well. Honestly, your work's gonna pay off. Okay, your work is gonna pay off. If you wanna subscribe, bro, just subscribe to the channel, bro. I need a couple subscribers, man. It won't pay off. It will pay off, bro. All the work that you did, it will pay off, 100%. I was originally doing dentistry actually, so that was the original plan. I didn't get in, not because of my grades. I got my grades, but I just didn't get through my interviews. I had 4 out of 4 interviews, but Sheffield gave me an offer, and they were like, "Nah, we made a mistake," so they took it back. That happened. So I was going to reapply this year. Well, last year, October. Didn't apply, and then plans changed. Decided to gamble for LSE. I'm going to LSE Economics. I had further maths, so I guess that did help. Can you make me uncooked? You can watch the stream. I think you came late, Julia. If you correct me if I'm correct. Yeah. Just how it is, man. All right, let's start with this here. 4.1. So 4.1 ppm, we have integration 2. This is what actually I would write straight away. Okay, you have integration 2. Therefore, you have 2 hydrogens on the carbon, and you also have a quartet. Therefore, you have 3 hydrogens on adjacent carbon. And you actually get marks for making the structure itself. So what I would recommend is look at where 4.1 is. 4.1 is this. Okay, we don't have a Cl in our molecular formula, C7H12O3, so it has to be that one. So what I'm going to do is I'm going to draw that structure below here. Okay, exactly the same thing as we did before. Okay, how many H's do we have on the carbon? We have 2 H's, so I'm going to do 1, 2. How many hydrogens do we have on the adjacent carbon? Because there's a quartet, 3. That's part of our structure. Okay, secondly, 1.26. 1.26 is, where's 1.26? is here. Okay, so it's R2CH2. It's going to look like so. And again, talk about the splitting, talk about the integration value 2, and also it's a triplet, therefore 2 hydrogens on adjacent carbon. And that looks like this, CH2, and then on the adjacent, we'll also have a CH2. Okay, if you ever have this, by the way, if you ever have 2 triplets together and with integration 2, chances are they're going to be a CH2, by the way. Okay, and that actually reflects here. So just take care of that. Okay, it's a yeah. Rico is OG. Rico is OG. Is it integration 3? Am I tripping? No, it's integration 2 for... Oh, I'm sorry. I'm sorry, guys. I misread that. No, you guys are right. 1.26. Integration 3. So if it's integration 3, again, following the same thing, like so. And then you have a H, C, H, H. Okay, sorry about that. Misread that. Singlet integration 3. If you have a singlet integration 3, chances are it's just going to bind to a carbon like so, or it might even be on the oxygen. We'll worry about that in a second. Calculate the structure of Z that causes the peak at 2.19. Well, 2.19 is this. 2.19 is going to be this one, right? So that actually just looks like so. C double bond O, C integration 3. Okay, so that's going to be H, H, H. No adjacent carbons. Sorry, no adjacent hydrogens on the carbon. So that's it. That's it, side folder. Okay, that's your 1 mark for that bit. Okay, these are picking up your marks. This is 5 marks, by the way. This is 1 mark. Okay, and that, by the way, you know how many marks that is from the beginning? 10 marks. 10 out of 11 marks without you even making the full structure. Beautiful. Absolutely beautiful. You can skip that last bit if you really want to, man. But at bare minimum, I want you to make these. I want you to say the quartet. I want you to say integration value. Okay, and if you're really willing to connect it all up, how many carbons do we have? Just make sure you have 7 carbons at the end. I will start with your longest chain. Okay, I think the longest chain is the easiest one to do. They should have a H at the bottom. Okay, you can see that this matches with this, so this is actually an overlap. 1, 2, 3. This is on the end. Okay, so I'm actually going to flip this around. Oops. 1 second, let me move this to the right. And I'll show you how to join it up as well. I'll show you a really easy way to join it up. This is your other structure, right? And this, because it has a CH3, it's also going to be on the end. So this is going to be C, H, 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 C double bond O. Now, how do we connect these in the middle? Let's actually check our MR so far. We have 1, 2, 3. 1, 2. Okay, we have 5 carbons. How many oxygens do we have? 3. 1, 2, 3. What are we missing? We're missing 2 carbons. So what do we do? Just stick a CH2 in between. Easy peasy. That's it. That's your final molecule. Okay. This will be your final molecule. Just always double check your environments at the end. In this case, they're all separate. They're all going to be 7. 1, 2, 3, 4, 5, 6, 7. You have the right amount of MR. Light work. Okay. Cool. Understand it now. You understand it now. Where does the C2H4 come from? Just because of this, but this is the reason as well. If you have 2 triplets, and integration 2s, just stick it in. Okay. Alright. But if you have the end chains, make sure you just take the end chains, see what you have remaining, and you just add on CH2 in the middle. Alright. But the main marks, it doesn't matter about the end, yeah? In the main marks, just add this. Use different colors. Use different colors. And then every carry forward. No, Cam, no. No, not for this, no. You won't get the mark for that, no. Error carry forward is really dodgy in chemistry. Even in maths, you don't get in the chemistry, you don't get that much error carry forward. It's a bit annoying, but it is what it is. Okay, as long as you're doing the quartet stuff, as long as you're saying the integration and you're making the mini puzzle pieces, you're gonna get majority of the marks. Okay, it doesn't matter. I'm not bothered if you guys make the final molecule or not. Okay, without the final structure, you still get 10 out of 11. Okay, all of this is light. All of this is calm. This is probably the hardest bit in my opinion. Calm. All right. We'll look at. You know what? Let's move on. Are you guys happy with HNMR? I'm gonna take that as a yes. You guys are happy. Oh, well, yeah. One more thing. If you guys had the integration ratio, let me quickly go up the integration ratio like this. Sometimes you might have the integration ratio like this, yeah. Okay. If you go ahead and just divide by the smallest number, so divide by 0.2, this will be. Let's put this as 0.3. I don't know how this will work, but let's see. I'll just pick some random numbers. This will be 1. If you divide by 0.2, this will be. Don't know what that will be. Let me check. Let me pull up my calculator. This might actually not work at all because I just picked horrendous numbers. 1.5, 0.60, 0.2, and 3. Oh, this works quite nicely. And you times that by 2, 6, 2, and 3. This will be the integration ratio that you'll be using. Okay. Also, something else to notice. Okay. Sometimes you might have an integration ratio of 6. Sometimes you might have an integration ratio of 9. Do not panic. Okay. Essentially, what it means is that you have carbons within the same environment. Okay. You cannot have a carbon with 6 hydrogens. Okay. But you can have this. Okay. If you ever see also an integration of 9, this is the first thing I want you to put down. Okay. Straight away, I want you to put this down if you ever see an integration of 9. Okay, there's an NMR question for 2024 paper 2. I wish I had the 2024 paper for AQA. I just don't. That if you have it, if you have the paper with you or a screenshot of it, come to my Discord, send that to me. I'm more than happy to go over that. Okay, but I did sit the 2024 papers myself. That was my year actually. So yeah. All right. Why do we multiply by 2? Just because you can't have 1.5. Okay. Just make it into whole numbers. Divide by the smallest. Okay, and then make it into whole numbers. The way they'll phrase it, they'll the numbers anyways, they'll go into whole numbers eventually. Okay, you put it in the Discord. Let me have a look. One sec. Yeah, please, man. If you can, that'd be nice. Just take a screenshot. I think files might be disabled, just because of stuff. Just take a picture. You should be able to send screenshots. Okay. All right. Go into my link tree, Cads. There's a hopefully there's a Discord link there is. Okay. All right. Let's have a quick 10-minute break because I actually need to go pray as well. So we're gonna have a 10-minute break. If you guys send the question in Discord, that'd be great, and I'll go over that in a sec. And then afterwards, we more or less finish HNMR. I want to go over recrystallization, benzene mechanisms, and carboxylic acids, and chromatography. And then I think we're on track of finishing off at 7:30 potentially, maybe. Okay, cool. So yeah, of course. Let me zoom out for a bit. I'll be back. I'm gonna go AFK. 6:55, maybe less. I'll be back in a bit. Or 6:53. Yeah, that's good. 6:53. Okay, no worries. We'll do Arrhenius equations at the end. Yeah. Did I not say that? Yeah, Arrhenius and rates. A mix of both. It'll be Arrhenius, on the Arrhenius focused. Okay. Right, I'll be back, guys.
Right. Cool. Let me check Discord real quick. Did you guys send it? Okay, nice, nice, nice. Let me go through this. Is this from the 2024 paper? I've never seen this. Well, I have seen this once. Okay, let's attempt this. I'll go through it in terms of my thought process. This like the more or less you can consider the first time I've seen it with you. So yeah, one sec. Let me just get everything on screen. Okay. Everything okay. That's 2024. All right. Cool. 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 Compounds. Oh, where's okay? Yeah. Compounds B, W, X, and Y are isomers with molecular formula C5H10O2, and then V and W are carboxylic acids. So these are both isomers of each other. Okay. First thing I'd do is actually even try to make some sort of isomers with C4 and H9. First thing that comes to my mind is an easy one. 1, 2, 3, 4. Double bond O, OH. Another one could look something like this. And then maybe a branched off group. Okay, that's what I would do. Okay, given an equation for the reaction of this with sodium hydrogen carbonate, pretty simple. Okay, when you go ahead and react any sort of carboxylic acid with sodium hydrogen carbonate, we always make carbon dioxide and water and salt. Okay, in this case it will be C4H9 COONA. Na like so. I'm going to check, is it balanced? It's not balanced. It's not balanced at all. Yeah, that looks horrifically wrong, bro. Yeah, we use sulfate. So yeah, that's not right. Am I tripping? I am tripping, bro. C4H9 C11O minus, and then it's going to be NaHSO4. Sorry, NaSO4 plus. So you get that. Am I tripping? Oh, why did I put HSO4? Yeah, my fault, guys. Yeah, I'm tripping. I don't know why I did that. That's my bad, guys. That's my fault. My fault. There we go. Yeah, cool. That works. I don't know why I put HSO4. I would think of sodium hydrogen sulfate. Yeah. That's it. Right? Cool. I believe that's balanced. That's CO3. Yeah, that's calm. Alright. Isomer V has an asymmetric carbon atom. Describe the structure of V. Well, if it's asymmetric, it's just going to be this one here. Okay, this one's a symmetrical one because it has 2 C chains. This one does not. Pretty simple. 6.2 done. 6.3 isomer W. Well, it's going to be this one. I think it's going to be using this. Okay, but I'll drag this down. Voice correct. Describe the structure of W. Or deduce the structure of W. It has 4 peaks. I'm going to check the peaks real quick. 1, 2. Ooh, this has 3. Oh, never mind. That's my bad. Let's talk about HNMR. So let me quickly draw this out. This is going to be like so. Double bond O, OH. And then CH3, CH3, H. One, two, three. That'll be 1, 2, 3 environments. It's saying 4 environments. Unless I have potentially done the wrong structure. Let me just check the amount of carbons it has. 1, 2, 3, 4 carbons. Okay. Decent integration ratio. Have you got any other information? We do not. For piece in HMR, do the structure review. For V, you're saying CH3, CH2, CH, CH3. Like so? You're saying? 1, 2, 3, 4. Oh, in fact, that could be. No, that's the same. So you're saying is this?
CH3, CH2. Am I tripping? 5 carbons. Ah, it's 5 carbon. That's the issue. Yes, yes, you're right. It's 5 carbon. I put 4 carbons at the beginning. Yep, that's my bad, guys. Yep, it's 5 carbons. That's what you do. That's what you get for doing 4 hours of chem straight. Okay. 1, 2, 3, 4. One more. 5. There we go. There we go. All right. So now we can make a different amount of isomers. So we have one like this potentially. Okay. We can potentially even have one like so. 1, 2. OH. Na2. Why Na2? It's not Na2. It's going to be sodium hydrogen carbonate, not sodium carbonate. Like so, I think. That would make also a asymmetric. So that would be 1, 2, 3, 4, 5. Yep, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I would say these are the 3 different isomers that you can make with 5 carbons this time. Okay. And then HM is saying that there's going to be CH3, CH2, CH. So CH3, CH2, CH, CH3, COOH. So you're saying it's this one. I do not agree. No, I do agree. What asymmetric means, it's going to be a chiral carbon, meaning you have a different chain here. That's your CH3, CH2. This is your CH3. There's a H here, and this is also your fourth carbon. Where do I put any? Yeah. That's why, yeah. Yo, am I getting clipped, guys? You guys have clips in your name, bro. You guys clipping me. This is AQA. Alright, now the other one is either going to be this or it's either going to be this, but it's told us that there are 4 peaks. Okay, so I'm gonna draw this out in skeletal. No, I'm not. I'm gonna do it in displayed. CH3, CH3. This is a H, C, H, H, and this is a C double bond OH. How many peaks does this have? This has 1 peak, 2 peaks. This is going to be 3 peaks, and this is going to be 4 peaks. Therefore, my molecule is going to be this. Okay, just by doing the isomers at the beginning has already given me a good idea. It's just made it a lot more easier for me. Okay, deduce the integration ratio. Well, I have. I should probably do this in a different color for these two. So that's going to be 6 because that's in one environment. My second environment is going to be 1 for here. My third environment is going to be 2. My fourth environment is going to be 1. Okay, we've got carboxylic acid left and chromatography and rates. All right, 6.4. To do isomers, essentially just do as much as you can. Like, you've got this original molecule here, and just try branch it off into different things. Okay. So you see how I did it here at the beginning. I did make a mistake between 4. It is 5 carbons. Okay. So make all the different molecules you can. So start with the most simplest one. This is the most simplest one. Okay. And then take this carbon chain off and just attach it there. Okay. And then you can make another one. Maybe you can do 2, like so, branch off twice. Okay. Can I do the ratio again? Yeah, of course. Our integration ratio, well, since this is our molecule here, we just have to think about the environments. Okay, we have 4 environments, 1, 2, 3, because those are on the same carbon, and 4. Okay, what's the integration ratio? In the first, the orange one, we're going to have 6 hydrogens in that environment. In the green one, we have 1. In this one, we have 2. And the last one, we also have 1. It's okay, Simon. It does take time. It's all right. If you think that it's okay to, skip the question, do it and come back to it later on. Isomer X. Okay, isomer X. What's isomer X? Isomer X is some sort of molecular. So this could be potentially a carboxylic acid, not carboxylic acid, an aldehyde or a ketone, or maybe even a hydroxyketone. Isomer X has 3 singlets with an integration ratio of 1 to 3 to 6. Okay, honestly, a lot of this is experimentation. It doesn't matter. No, it doesn't, Zainab. How did I do the isomers? Essentially, I drew the simplest one. I drew the simplest molecule. Okay, and then I just took off the carbons one by one, and then I just made it into a branched. Okay, and then I took that one off, and then made that into a branch as well. That's how I did it. Until you can't do any more branched. But isomer X has to have a molecular formula of C5H10 or 2. I would say this is probably going to be some sort of ketone or aldehyde or potentially even alcohol. It could even be a diol. Okay, so it's very unlikely it will be an ether just because they don't really like to do ether unless they're giving you the ppm. So don't worry about ether too much. 1 ether is just that. So don't worry about that too much. Okay. In terms of its ratio, we have 1 to 3 to 6. So if we have a 6, it could be an ester. It could be, yeah, actually right. I'm gonna add that in. Because we have a 6, what I'm gonna start off with is I'm gonna start off with 2 CH3s on the end. Okay, and even actually I'm gonna take that back. It probably isn't symmetrical. It's very unlikely that it's gonna be symmetrical. So what I'm gonna do is 2 possibilities. Either is this, or it's a H3C and a CH3 like so, and there's something in the middle. It's one of these. I think most likely it's going to be the one on here, but let's see. It has 3 singlets. Okay, so definitely I don't think it can be this. Why? Because we're probably going to have a C and a H and a H. But it's told us that there are some, actually it could, I guess it could. It could even be an ester. It could be a diester even. So I'm actually going to take that back. It could be this one here. But the thing is, they're all singlets. And what I'm actually going to do is draw 3 parts. So I have one like so. I have one with 3 H's. Why have I done that? It's because of my integration ratio. And chances are we're probably also going to have an OH, I think. Because if it's a single bond, it's probably going to be OH. But let's have a look. C double bond O C. Okay, let's join these together. Okay, I think it's probably even just this. I think that actually joins very nicely. That joins nicely. Look, that's it. That's I guess that's all right, right? So I took the CH3s. I just joined the CH3 from this integration ratio here, and the OH is always a singlet. So there you go. That's my structure. That worked pretty nicely. Okay. Explanation: why the peaks are singlets is because there are no adjacent carbons with any hydrogens. 2 oxygens. Oh, you have a very good point. There should be 2 oxygens. You've got a good point. You have a very good point. So you know what? I'm going to stick an oxygen in between here. There you go. That works. 1, 2, 3, 4. There's no 5 carbons. Good point as well. Shit, good point. Let's also go back on that. Yeah, man's tired, bro. Man's tired. Alright, let me go back. Let me go back. Sorry guys. Too much NMR. Okay, let me separate these out again. Okay, because they are absolutely right, we do have 2 oxygens. Make sure you keep on looking back on your molecular formula. Okay, there's also probably going to be, I think, a C double bond O. Okay, so I think it most likely it's going to bond like so. The C double bond O comes in through here. I think this still works, and then we can just attach the OH here. That still works. Okay, could it be an ester? Potentially, it can be an ester. So if I did this as an ester, it could still also work. I would probably just be a bit... No, it would not be an ester. The reason why it wouldn't be an ester, I'll show you why. If we did decide to do an ester... 1 second. If we did decide to do an ester here... Let me clean this up. This actually looks horrendous, bro. This actually looks horrendous. I don't like this. Give me a second, guys. C double bond O, O, C, H, H, and H. Well, you can see that this looks good for now, but we have to have a H here. How many environments do we have now? 1, 2. No, that works. That works. Never mind, it does work. I take that back. It works. No, it's still a singlet. It can. Okay, yeah, so we can't have 2 answers. So this is one of the answers, and then you can also have the CH3, C double bond O, carboxylic acid, and CH3 on the end. Fez. Very nice. It's an alright question. I think it's pretty tricky. It's probably one of the harder ones there. But yeah. Okay. Alright. 6.5, draw the parts of structure of Y. Let me get the formula book thing. This is going to be the one. Okay. 3.65. 3.65 is this one here. So I'm going to draw this. So that's going to be like so. What's my integration on this? I have integration of 2, so I'm going to draw 2 H's on there. It's a singlet, so there's actually no adjacent carbons with any hydrogen. So this could be an oxygen, it could be anything. Okay, but it's still an isomer Y, so our chain is C5H10O2. I believe that is the molecular formula of that. Yeah. Okay, so we just have to remember that. Okay. And this is a 6-marker question as well. So 1.19 is probably around here, and it's telling me that it's integration of 3. So what I'm going to do is do an R group, 3 hydrogens, and this is also a singlet. So this is going to be something else. All right, what else do I have? I have a structure of Y, and that's it. State how many peaks there are on this. That's all I get. It's crazy. Do I think there's always NMR? I think there's always NMR. Okay. Let me go back to the original question. Do we have any informations? Okay, it's not necessarily a carboxylic acid. And to be fair, Brain, I do agree with you, you know, because it says V and W are carboxylic acids. So you know what? I think it can only be the ester that we've got. So I will actually cross that out just because of what you said. I completely agree with you for that part B. It has to be an ester because it's told us that it can't be a carboxylic acid. I completely agree with you. Absolutely right. Yep. Okay, let's go back to the question that we're just doing now though. We have to somehow join these up. But we've got CH3, we've got this molecule here, and we know that in between there must be no C's or O's that can join. Okay, but to be honest, I think it potentially has to be some sort of ether group like so. Okay, how many carbons have we got left? C. We've got 5 carbons in total, so I'm just going to make this CH3. That's what I'm going to do. Okay, it hasn't really given us much information. I'm just trying to think, is there any more information we have here? Not really. H. That's what I'm going to do. 2 plus 3 is 5, but there's 10, so it's a 4 to 6. That'll help. Where did you get 4 to 6 from? Ah, you've done it like that. Ah. Do we have only 2 hydrogen peaks though? Yeah, it is only 2 hydrogen peaks. That's all the peaks that we have. No, you're absolutely right. Yeah, no, you're absolutely right. So CHH. So actually, because it says that there are only 2 peaks, your ratios can actually be simplified. So this could be a 4 to 6 since we have absolutely right H. I mean, a smart guy. So yeah, you get 4 to 6. And because we only have 2 peaks, we can only have this. So essentially what we have is, sorry for the background noise on TikTok, but 3.65, with 3.65 again, 3.65 is this. Okay, so essentially we have, did I pick the wrong one last time? No, I didn't, I'm tripping. Okay, so we can have 2 of these, so we can have C, H, and H, like so, but because it's integration ratio 4, chances are we're going to have some sort of symmetry, so it will look like so. That's wrong. C, H, and O. Okay, and similarly with the other one as well, 1.19, which is this. We just have 2 of those, so we're going to have integration of 3, but we're going to have 2 of them essentially. How the hell do we join these together? How do we join these together? Because if I do this, these are not singlets anymore. I guess what you can do is, because this is 4 carbons right now, I missed off something. There are 2 peaks, yeah, they're symmetrical. I believe what you can do instead is, because we have an integration of 6, what you can do instead is you can do CH3, like so, right? We can flip the oxygens. Why are you saying? Yeah, we can flip the oxygens. Let's flip the oxygens. Okay. We only have 2 peaks. We have to recognize that we only have 2 peaks, and because of that, this becomes a bit more trickier. Or you think structure is cyclical? It's a hard question. I can't lie. I'm not very good at this, man. Was this in my paper? You're telling me this was in my paper? I don't remember this being in my paper, bro. What AQA paper did I say? Because I found my paper pretty good. My chem was pretty good. What paper? What 2024 question is this, bro? What 2024 question did I say? Because I saw the 2024 paper, bro. Let me restart for the guys that are a bit confused. Okay, let me restart. Essentially, because we only have 2 peaks, your ratios can be simplified, right? So essentially, what we can have is an integration ratio of 4 to 6 instead, because we have a total of 10 hydrogens. Okay. I want to move on to reads as well. But let's quickly finish this off. But you guys are saying it is a cyclical, which is fair. Okay. This would be H, this would be H, H, and H. Actually, no. It would go like this, C, H, H, O. This would be a... The thing is, this doesn't connect very easily, though. So how are you getting that? I don't even know what I got paper 2, man. Yeah. I don't even remember this. I'm gonna be honest, I don't remember this, man. Maybe I've just forgotten it. I have no idea how to make this. I'm gonna be honest. I have no idea how to make this. 1 sec. Let me think through this, guys. 1 second. One second. Ah, I know why. You don't have 2 CH3s. You have 3 CH2s. Essentially, you have 3 CH2s. Okay, so what you have basically is this. 1 second. All join around. Yeah, you have this basically. Okay, so if I join this around, okay, C, C, C for 5 carbons. 1, 2, 3, 4. That's going to be an O. And then there's also going to be an O here. There we go. These are going to be H's. These are going to be CH2s. This is going to be... I've missed a carbon off. No, I haven't. And this will be a CH2 as well. 1, 2, 3, 4. I have missed a carbon off. Essentially, it goes in this order. It goes in this order. Okay, this O will bond back here, and that makes you ether groups. That is disgusting. I can't lie. That's absolutely disgusting. What I don't know is 3. It's 3 CH2s, not 2 CH3s. That is absolutely disgusting. I can't lie. I don't think that will pop up. I hope it doesn't pop up. 1 oxygen, C, oxygen. Okay, there we go. And then CH2s on all of them. There we go. Damn. Does that make a triplet? No. It's not a triplet. It's because of symmetry. So your symmetry would be down here. The symmetry would be down here. 1 second. Yeah. Alright. Leave it, boys. Leave it, boys. No, leave it. I look at this question. It's actually very cool. I'm gonna make a video on this at some point. It's actually very, very interesting. Someone's mark scheme. Yeah, please send me that. Put the mark scheme on chat on the screen. Boom. No, I didn't add CH in between. No, it's because it needs to have 5. Okay, so well they've joined it up like this, which is fair. Okay, and then they've done the CH2 things that I've done. Do your individual parts, that will get you marks. And look, they've actually got 4. You've got 4 marks without even making the actual molecule, which is crazy. You've got 4 marks without even making the actual molecule. Do this and this will get you marks. Even if you did this, that's calm. This is calm. Okay, but this is absolutely disgusting. I can't lie. That's crazy. That is so crazy. I'm gonna actually make a video on that. Thank you, Avarice, in Discord for that. Thank you very much. But yeah. Alright, let's move on to different topics. Thank you for the subscribe. We're gonna be going through rates. I wanted to do carboxylic acids, but I'm gonna skip over. I'm gonna go to actually we're gonna do benzene first, and then we're gonna go to rates. Okay, benzene. We already went over the benzene. What's it called? The Phenylamine equations. Okay, so I'm going to skip over that, but we do need to go over nitrobenzene. So nitrobenzene, you have NO2. That's what you're going to try to make, and you're going to start off with a normal benzene. Sometimes you can have CH3. It doesn't really matter. I'll keep a CH3 here actually. We're trying to make this into a nitrobenzene. Okay, how do we make it into a nitrobenzene? Well, first of all, you need your equations: concentrated nitric acid plus concentrated sulfuric acid. Okay, this makes it into the following: NO2 plus, also make HSO4 minus, and you also make H2O. Okay, cool. Now what happens is, make sure you have your N. I would recommend that you put the plus on here. You won't lose marks if you did put it here, but just because in terms of the mechanism, I think it's just to have a good habit, because you need a positive charge on your nitrogen. So what you're going to have is this negative to positive. Electron bond goes to the N. And I've kind of drawn that wrong actually. Let's try to make this instead. Okay, so what happens is your intermediate is going to look like this. CH3, NO2 binds here. Now if NO2 binds here, we also have a H that is here. The name of this mechanism is going to be electrophillic substitution, because we're swapping out the H for the NO2. Now to make your horseshoe, you can't just draw it. You need to make the horseshoe between 1, 2, 3, 4. How many sides does it have? 5 carbons, sorry. Yeah. Okay, so you're going to make your horseshoe on every single carbon except this carbon here. Okay, and this is going to be plus. The H, negative to positive, bond to the positive. That comes off, and that's your whole mechanism complete. Electrophilic substitution. Okay. Similarly, this is actually very similar for your Friedel stuff. Okay, your Friedel crafts. Your Friedel crafts, this is going to be using your ethanol chlorides. So, if you have a CH3, that's the equation, yes, of course. Concentrated nitric acid, concentrated sulfuric acid. This is your reagents if it ever asks for reagents. And this is just a balance. There's not just one equation, but I think this is the easiest one to learn. There's a couple, but this is just a 1-to-1-to-1 ratio. Acylation, this is basically acylation nanomoles. What's the point of H2SO4? Good question. Guys, what's the point of H2SO4? What's the point of H2SO4? What's the purpose of it? Catalyst. Thank you, Kylie. Catalyst. If you're unsure, just say catalyst. Okay? And then, yeah, it gets regenerated. You get H plus in the end. Okay? Come on. Alright. Now with Friedel crafts, you also have an equation for this. I'm just going to pick the simplest one, just because this is the one that comes to my head. HNO3, it makes your NO2 plus. That's the purpose of that. Okay. I'm just going to pick ethanol chloride, but it can be any sort of acyl chloride. Okay, and you're going to be using your AlCl3 here. Okay, in OCR you're able to use FeCl3 as well, I believe, off the top of my head. I haven't looked at it in a while, but this is going to be the main one. And the purpose of this, again, is a catalyst. Okay, and this makes the following: CH3CO plus. And actually, I would probably put the plus on the carbon just for habit, but it doesn't make any difference in terms of your equations. And you also make AlCl4 minus. Okay, remember, this is a good thing to remember. Every time you react your acyl chlorides, you always make HCl as a side product. And I'll show you how to make HCl right at the end. Okay, so first of all, this is going to be very very similar to your previous question. So we're going to have our C. This is your double bond O CH3. Okay, and we have a plus on our ethanol chloride. Again, negative to positive. And what happens is, it doesn't really matter. I feel like I should probably put a final product. Let's just attach it onto this carbon here. So this just makes CH3. This will be C double bond O CH3. And again, we have to have our H here, and this is going to be a horseshoe. You can call it acylation if you want, okay? Because you're essentially adding a ester kind of group, or still electrophilic substitution. Both are fine. Okay. Again, bond breaks, and that's your final mechanism done. Okay. Your final product will look like this: C double bond O CH3, and this is going to be CH3 on the top. Doesn't matter. It doesn't have to have a CH3. It's just there for the purpose of the question. Okay. And then finally, because your H plus comes off from here, okay, you go ahead and react this with AlCl4 minus, and this makes your HCl that we were talking about right at the beginning, and H to AlCl3. It's essentially, you have multiple equations. Okay, this is just one of the equations. There is an equation with H3 or plus. If you want to memorize that, great. I think this is the easiest one to learn. 1 to 1 to 1. There is one with H3 or plus, and I know which one you're talking about. Okay. Yeah, of course. Yeah, it is deteriorating, man. There we go. I'm not gonna go through voice. I think I'm losing my voice. This is asking in terms of mechanisms. I want to go through this one real quick. I want you guys to try this. Try this question. And then we're going to start with some rates stuff. Actually, no. Before we do that, I want to go over some benzene properties real quick, just in case it can pop up. Let me get my notes for that. I don't actually have notes for that real quick. So my OneNote somewhere. Where is it? It is. I found it. That's cool. All right. While you guys are kind of doing this, I'm just going to blab on about some properties of benzene. Okay, that can potentially come up in a 6 mark or in something like that. I've seen it before. Essentially, with benzene, it has the same bond length each time, whereas in comparison to your Kekulé model, it does not. Okay, it is a hexagonal structure. Okay, it has planar, so it's a planar structure as well. And each time when you have a C and a C like that, in fact, let's not worry about that. When you have your hexagonal structure like this, each one of these has 3 bonds. Okay, if it has 3 bonds, essentially what happens is this angle is going to be 120 degrees, and that's what causes it to be planar. Every single one of those carbons is a trigonoplanar. Okay, the spare electrons, what happens to those? They get delocalized into your electron pi cloud, and that's essentially your ring in the middle. Okay, and that's more or less it in terms of that. In terms of if it's ever in a question and you're talking about the Kekulé model, make sure you just mention the fact that it's more stable, because you'll have some numbers to work with essentially. I won't go over that right now, but I'm sure you've seen it if you've been looking at past papers. How much longer? No idea, young man. We'll push to maybe 7:45. Maybe 8. Yeah, give me a second. All right.
Now you guys are doing really, really well, really well, man. Just a little bit longer, and we're done. Okay, step one. What's happening here? If you want to practice a mechanism, this is going to be your nucleophilic addition elimination for that top bit. Okay, longer than CC, shorter than CCC. Yes, Yassine, yeah. But essentially, they're the same length. That's the main thing. That's the main thing, yeah. Question 5. Let me just quickly go over that. Reagent for step 2 is a mixture of concentrated nitric acid. Yep, we just did that, so that's going to be NO2 plus. Right. Name the mechanism for step 2. That's going to be electrophilic sub, as we just did. Type of reaction in step 3. That's going to be what is that going to be? Because so essentially, what happens, that pops off. Entropy lower than expected. That comes in the physical, no? You don't need to know that. But it's basically because of your solid and liquid gases. Okay, but for this if we did our carboxylic acid topic, essentially what you have here is your amide group. Okay, how do we get rid of amide groups? It's not hydration. Someone said hydrolysis. It is hydrolysis. Okay, these are amide groups. To get rid of them, you can do acid hydrolysis, any sort of hydrolysis. Oh, you talk about the hydrogenation. Okay. I'll go over that. Yes, the hydrogenation of enthalpy. I'll go over that in a second. Okay, but essentially, to break an amide bond, you just introduce water, and a bit of energy, and you're good to go. Okay, but you can have acid hydrolysis, and you can also have alkyl hydrolysis. Identify the reagents used in step 4. That's pretty simple. We're going to be using SN and concentrated hydrochloric acid. Okay, this is from the amine stuff we did before. If you guys missed that for whatever reason, okay, your nitrobenzene to a phenylamine, you need SN, and you also need concentrated hydrochloric acid. Okay, in terms of the equation, it's going to be 6 reducing agents, goes to the arrow, and you make 2 waters. And you also have adding NaOH to remove any salts. No, that's for converting nitriles to amines. Yeah. Okay, what's the difference between amide and amine? Amide is when you have N, H, and CO. So this is the amide, and this should have a double bond, single ring in here. And amine is just this, and it's NH2. Okay, Amelia? The last equation, this one here? Or are you talking about the previous stuff? These two. Oh, I would prefer you use this. I would prefer you use that. Can I explain the hydrolysis, of course? So in terms of the hydrolysis, essentially what you can have is you have esters, okay, and you also have this kind of your polymer stuff, right? And you also have amides. Okay, to break them up, well, originally what we needed to make these esters was an alcohol and a carboxylic acid. I don't know what that was in my head. Similarly here, we need an amine and a carboxylic acid. These are joined together and they go ahead and release a water. Okay, I'm going to show you how that looks like. OH, and you also have some sort of alcohol group here. Okay, I'll show you the same thing with the amines in a second. Okay, what happens is these go ahead and join together. Okay, you have this that comes off, that's your water. Okay, and then you make an ester. Okay, well, how do we go ahead and bring that back? That's something called hydrolysis. Okay, so you go ahead and split this apart. You go ahead and split this apart, and then you bring in water again. The carboxylic acid bit becomes OH, and the OH also comes back. That's your hydrolysis. It's concentrated. Make sure you have concentrated. Yeah, use concentrated. Concentrated is better. Okay, same thing here. Okay, we're going to split this apart. Okay, and what happens is this becomes NH2, and then we have an OH here because we brought in water. Right? With the mechanism for the water acting as a nucleophile and attacking the CO. If you were to do the mechanism, if you were to go ahead and do the mechanism, you would do to the C first, because your C would be your most negative. So if you were to go to, I don't think it will ever come up, but if it ever does, I would probably start with a H plus, because there is a catalyst. Usually it's going to be your sulfuric acid. Actually, no, not even C plus. We'll do from the lone pair. This attacks like so. Okay, and it's going to be some sort of R group on these. Okay, this will make 4. Okay, what happens is we have 4 bonds here. This is a positive charge right now. You don't need to know this mechanism, by the way. And then what happens is this donates electrons to there. What happens now? R, N, H, H. This becomes positive. What do we have left over? A OH minus. That can be from water. That can be from anywhere. And that would be nucleophilic addition. Okay. You don't need to know the mechanism for this, but that's how you probably do this. Okay. All right. Next part, rates. Rates. I'm gonna do some maths for a bit. Okay, I'm gonna quickly do some maths for like 10 minutes, and then I'm gonna show you how that links over to Arrhenius equations, because I think it's really helpful for it. Okay. I'm gonna draw a straight line. How do you guys work out a gradient of the straight line? For the guys doing maths, it's probably very easy. How do you guys work out the area? Not the area, the gradient of a straight line. Gradient of a straight line. How do you even get triangles, bro? Good. Difference in your y divided by the difference in your x. Okay, good. Remember this. Y over x, or it's just a change in y over change in x. Perfect. You can make a triangle if you want. You can use change in y over change in x. Okay, so y equals mx plus c. Your m is related to your gradient, so this is your change in y and your change in x. Your plus c is your intercept. Now you might be like, okay, why is this guy teaching me maths? I'm doing chemistry. Watch, it's relevant. Okay, so when you have questions like this, your y equals mx plus c, in my opinion, is so relevant. It will make everything really easy for you. Okay, this part I think is pretty easy. This next part will require a bit more math stuff. Okay, you will always be given the equation. Do not panic about that. Okay, now the first bit I think is pretty nice. Okay, it's a bit blurry, but we'll worry about that. We don't have to worry about that too much. But essentially, okay, we're trying to fill in the table here, and I'll show you how the y equals mx plus c is going to relate for the part B. First bit, we want to work out temperature in Kelvin. Your Arrhenius equation is given with this. K is equal to AE to the minus EA over RT. Okay, this is your rate. This is your rate constant, which will be given to you. Okay, EA is your activation energy, obviously. R is a gas constant, which is also given to you. And T is your temperature, which is in Kelvin. Okay, now they've given you 1 over T, which is 1.6 times 10 to the minus 3. From there, can you work out what temperature would be? What is the temperature? If you know 1 E is actually a very special number. It's like 2.71 something. It's just a number in your calculator. I will pull that up in a second. It's Euler's number, yeah. You guys got 625? What do you guys get for the temperature for that? K is rate, A is rate constant. Okay, how you would work that out? If you know that 1 over T is this, that means you can just do 1 over 1.6 times 10 to the minus 3. It'll just essentially just cancel it out. 625, beautiful. Nice. Mr. T's after. Nah. Not Mr. T's, bro. Okay. Now, this part here, pretty simple as well. If we know that L and K, if L and K
ignore this for now. If ln k is equal to minus 2.25, we want to work out k. The opposite of ln, the opposite of ln, is this e function. Just as you have the opposite of plus is minus. Constant. Yeah, you're right. Sorry, yeah, you're right. Yeah. Sorry. I'm confusing that with something else. No, you're right. You're right. Switch clips, you're right. It's rate constant. You're right. Okay. ln k is minus 2.25. The opposite of ln is e. Just as opposite of plus is minus, opposite of times is divide, opposite of ln is e. So how do we do it? We do k is equal to e to the minus 2.25. Now if you put this into your calculator, yeah, I am, man. I am. Opposite of, if you put this to a calculator, there's a button, special button, that's e. Minus 2.25. Equate that, that gives you 0.105. Okay, and we can just put that here. Yes? Alright. That is the easy bit. And the second bit, I'm going to make it easy for you as well. Alright, let's go back to the idea of y equals mx plus c. Okay, now you can see that we have a graph here. You can see that we've got a graph here. What is our y-axis and what is our x-axis? I know it's a bit obvious, but I just want you guys to just state it. Just write it down. What is our y-axis and what is the x-axis? On the graph. What is the y-axis and what is the x-axis? Good. Y is ln k. Perfect. And x is going to be 1 over t. Okay. Now what we're going to do is actually compare this with our y equals mx plus c. Okay. Perfect. Perfect, guys. So I'm going to write this as ln k is equal to m 1 over t plus c. I don't care what my plus c is at the moment. Paper 2 will probably will. It doesn't come up all the time, but it comes up a decent amount. Now you can see they've given us an equation here. Let's try to compare what are the similarities between what we've just written down and what is here. What are the similarities between them? Can anyone tell me what m is? What would m be? What is m? M is a gradient. But in terms of this, if you compare this equation to this equation here, what is m? And what is m equal to? Good. It is minus EA over R. Okay, so we are timesing something essentially. This m has to be everything there except the t bit. Okay, that means your gradient must equal to minus EA over R. Okay, we don't include the t bit. The t bit is just your x-axis. Okay, this is your x-axis. Okay, think about when you multiply your fractions, multiply the numerator, multiply the denominator. That just goes ahead. So gradient must be minus EA over R. Now, the question is asking us here, find the activation energy. So essentially what we need to do, essentially we need to find out the gradient from this graph and work out the activation energy. Okay, now a lot of the times you might be like, you'll probably end up reading off the graph. I actually would not recommend that. Just because sometimes you might misread. Use the numbers they've given you. Okay, what you're going to do is you're going to pick the top one and you're also going to pick this bottom one. And we're only going to be focusing on 1 over t and ln k. So I know I've scribbled it out, don't do that in your exam, but we're only going to be focusing on these two columns. Okay, it should be more than 2 marks. I have no idea why it's 2 marks, but yeah. How do I get 6.25 for t? It should be 625. 625, Angie, not 6.25. 625. Okay, it'll be 1 over that number. Now, essentially, what you're going to do, as you said at the beginning, you told me my gradient is the same thing as change in y over change in x, right? So change in y, my change in y is going to be my lnk. So that's going to be minus 9.4 minus 0.6 as my y. And then my change in x is going to be 1.76 times 10 to the minus 3 minus 1.24 times 10 to the minus 3. Can anyone calculate this and tell me what this would be as a gradient? Can anyone tell me? You are the person who impersonates Jay's grade 9s, yeah? Come on. We got rates, literally only rates, to be honest. Okay, can someone tell me what this M would equal to? Minus 19,230. Thank you, Rico. Okay, cool. Alright, so that means that minus EA over R is equal to minus 19,230. We know, 0.7, we know that R is equal to 8.31. Go ahead and solve for EA. Okay, go ahead and solve for EA. It's 0.8. Fairs. Right. Alright, we're going to times both equations, or both sides, sorry, by 8.31. And you guys get activation energy is equal to 159,808. But the question wants it in kilojoules. So you're going to divide this by 1,000. And your final answer should be 159.8 kilojoules per mole. Okay. Cool. Now, question 9.2. It says use your graph here to work out what the value of K is. Now, the value of K is actually very, very simple. When we have our temperature at 675 Kelvin, well, we need to work out actually first, we need to work out 1 over T. Keep it positive, always positive. Always positive. Yes, Gem, works every single time. Works every single time. Okay, this is the equation we made at the beginning. Okay, compared it, your gradient is going to equal to minus EA over R. Yeah, how come I didn't use a graph to work out? Yeah, you can do that, 100% you can do that. Why not? Your range, you can use a graph if you really want to, but I think it's just easier from the graph itself. Because sometimes what happens is sometimes you have to plot the graph, and if your graph is wrong, to be fair, then you'll get carry through marks. But what happens is a lot of the times you have a range, and if you plot it wrong, I can't. It's a long day, bro. Just lost marks for no reason. When you can use a table. Okay, because eventually, more or less, you're going to be using the table to plot anyways. So why not just use the table? Okay, let's find the value of K at 675 Kelvin. Well, first of all, we are not working in Kelvin, we're working in lnK, and we're also working with 1 over T. So first thing what I'm going to do is work out what 675 is as 1 over T. So I'm going to do 1 over 675. Okay, that gives you 1.48 times 10 to the minus 3. So that is like here. I know it's a bit hard for you guys since you don't have the table with you. That's 1.5, 1.1, 1.2, 1.3, 1.1, 1.2, 1.3, 1.4. What was the calculation I just got? 1.48. So that's like almost there. That's like there. Cool. And then I'm just going to draw across. That's like there. So that means my lnK is about, if this is minus 5, minus 4.1, 4.2, 4.2, 4.4, 4.6, 4.8. That's like minus 4.2. Okay, so I've just read that off the graph. So that means my lnK is equal to minus 4.2. Therefore, my K value is equal to what? What's catastrophic? What did I do? What did I do? Did I do something wrong? What did I do? So K value, you do e to the value for that, and that should give you the final answer. Let me check that. E to the minus 4.2 equals 0.01499. Did I count from 1.4? I counted from 1. 1.42. No, I meant like, no, because this is going to be 1.42, 1.41, 1.42, 1.43, 1.44, 1.45.
Oh yeah, that is horrendously wrong. Brain. Oh, brain. Smart guy, man. Yeah, no, you're right. That's 4, 4, 2, 4, 4, 4, 6, 4, 8, 1.5. So 4, 8 is there. Yeah, no, you're right. Oh yeah, so you get ln equals -4. Yeah. Why do we choose? Why do we choose -4? Why do we choose that point? Is because we want 675 Kelvin. So we choose essentially we're doing 1 over 675. So use 1.48 times 10 to the -3. Same thing though. K will equal to e to the -4, and that gives you whatever that is. Lidder, try to do chem for like 5 hours straight, and then let me know. Yeah. 0.018. 3. Cool. Chromatography. I might have to skip through carboxylic acids. I'll quickly go over the nucleophilic substitution, the nucleophilic addition elimination for this because it's, yeah. All right. CH3. One sec. Ethanoyl chloride plus, actually, 1 second. Guys, get this exact equation down, okay? Anhydride plus alcohol. You will always make the following: ester and carboxylic acid. This will help you, okay? If you're ever unsure what this makes, you'll always make an ester and a carboxylic acid. So, for example, okay, C double bond O, like so, H and H, yeah? And then if we have, for example, an ethanol, what happens is, this is your ethanol anhydride. What happens is you can kind of split it in half, okay? So this part you can take, and this will make a carboxylic acid, as we've just said. This makes a carboxylic acid. And the other part, well, we'll just make an ester. So that's going to be your CH double bond O, O, CH3. That's going to be ester, okay? Use this, it's going to help you a lot, especially in your aspirin stuff. All right. I'm going to show you guys, I'm going to go over the recrystallization real quick. Okay, I'm going to go over it really quick. So yeah. All right, get this down. Recrystallization. I'm going to be going like back and forth between a couple of topics. I'm going to do the mechanism next. Okay. And then chromatography, and then we're finishing off. What was I going to do? All right. First thing what you're going to do is you're going to take your sample. The reason why you do recrystallization is to essentially purify a sample. Okay. So you're going to take your sample and you're going to dissolve it in minimal hot solvent. Okay. That dissolves. You want it to dissolve it. Yeah, you essentially want to dissolve it. So your minimal, why do you choose minimal? Essentially, you choose minimal so crystals can form at the end. And then you choose hot. Why? It's so it just fully dissolves. Okay. Now, when your sample has fully dissolved in terms of recrystallization, okay, you want to use a coffee filter. Okay, exactly. So you're going to use a coffee filter, and this you're able to then essentially, this should be dotted lines actually. Coffee filter. Okay. This causes removal of insoluble impurities. Okay, so anything that's solid, anything that doesn't dissolve, you're going to remove those. Okay, after you've done that, you're going to take that hot solvent, and it needs to be hot, by the way, while hot. Okay, we're going to use a Buckner funnel in a second. Okay, these are both necessary. This is for insoluble. Okay, where we at? We're going to take the Petri dish or whatever conical flask you have, and you're essentially going to put it in a ice bath. That's my ice. Okay, this cools, and your crystals form. Okay. Then what you're going to do is you're going to take the crystals, and you're going to put it into a vacuum filter or Buckner funnel. Vacuum filter is completely fine.
Okay, why do you do this? So then you can go ahead and remove the soluble impurities by use distilled water to wash. You can say wash with distilled water. You guys need to know the diagram for this. Okay, that's going to be like so. This is your filter paper on top. That's your Buckner funnel. Okay, you also have a conical flask. That's going to be going out. Okay, vacuum there. Vacuum out. And you should also have a bung here actually as well. Okay, that's your Buckner funnel, and then you also have your filter paper, and that just causes it to remove all your insoluble, your soluble impurities removed. Okay, cool. After that, you take out your sample and you just leave to dry. Now, to check purity on them, here's a fat funnel. To check purity, there are 2 ways you can check purity, or technically 3. Okay, big crystals. Okay, the more white the product is, more pure. And lastly, your melting point. So you have a sharp melting point. Okay, if it's an impure product, you're going to have a range of melting points. And the way to test this is just something called the melting point apparatus. You don't need to know much details about this melting point apparatus. You can just say that in terms of that. Okay, that's completely fine. Okay, you have to use a drying agent, but that should be fine. Okay, range of melting points. Just let it dry. Just pat it dry with tissue or something. Okay, and you also can have a lower melting point. All right, cool. All right. There's something called the separating funnel as well. I want to talk about this really, really briefly. Essentially, the separating funnel, you have something called your drying agents. Okay. Anyone know any drying agents off the top of their head? Good. Calcium chloride. Calcium chloride is a good one. Calcium carbonate. I'm gonna actually double check. Don't know off the top of my head. Drying agent. I don't think it is, to be honest. No, it's not. Use calcium chloride. Alright, so calcium chloride, essentially the purpose of this is to remove water. And actually, I would advise that you put anhydrous as well. Okay, to remove water. Yeah, sodium sulfate is a good one. Sodium sulfate is also a good one. Okay, the reason why you use a drying agent essentially is when you have different, when you have a solution or a mixture of different things with different densities. Okay, sometimes the densities or sometimes the solution, the mixtures can have water in them. Okay, so essentially a separating funnel, when you have a higher density, it goes to the bottom. Okay, and then you open the tap up, and then essentially the liquid is released into a beaker or something. Okay, the water gets released. You pour it into this beaker here, and then let's say, for example, this is not already the water. Let's say it's hexane. Hexane is a good example. There might be a bit of water in the hexane, right? And then what you essentially do is you add MgCl2, you add it into there, and it becomes essentially a precipitate. Okay, and then you can remove that precipitate with filtration and such. Okay, so that's going to be your separation with the separating funnel. Okay, main thing you need to know about is about density. Magnesium hydroxide, no, because magnesium hydroxide is already a it doesn't absorb water really well. I'm going to be honest, because it's really, really like, you see, it has partially soluble, so it doesn't really dissolve in water at all, so it doesn't really absorb it. Okay. All right. Let's go to nucleophilic addition elimination. So you're going to be using your ethanol chlorides. Now, every time you use an ethanol chloride, you always make HCl. Okay, we always make HCl. Magnesium chloride is your drying agent. Now, I'm just going to use ethanol chloride just as a basic, but it can be any sort of acyl chloride. Let's start off with a simple one. Water. Water? Yeah, water. Let's start with water. Lone pair to the C, breaks off. This is delta plus, this is delta minus. This pops off. Okay, and because you also want to make an alcohol, this goes to a single bond like so. This is a Cl, this is an O, H, and H. Oxygen now has 3 bonds. I'm going to remove this for now, actually. Oxygen now has 3 bonds. Chlorine goes off. We don't want 3 bonds on the oxygen, and this becomes a double bond. This rule applies for every single nucleophilic addition elimination. Learn this. Okay, this works for everything. Okay, and you're always going to make a HCl on the end. You can see that this is a H and this is a Cl. You always make a HCl. You can say magnesium sulfate, sodium sulfate, magnesium sulfate. Did I say that? Calcium chloride. Those are ones that come into my head. I think calcium oxide. Don't say that. Ooh, my one not crashed. Oops. This is not AS content. No, it's not AS content. This is A2. Okay, learn this. Okay, I'm gonna give another mechanism. Ethanol chloride plus ammonia. Do that. Okay, this also works with ammonia, and you're gonna make something. Yes, I will go over that. I will go over that. And then while you guys are doing this mechanism here, reasons to not use acyl chlorides. Thank you, BMZ, for that. I did make a note of that in my PowerPoint, but I completely forgot. Okay, I made a whole list for this. It's corrosive. Produces corrosive gases, specifically HCl. Okay. It reacts violently. I've got a list like up there, so that's why I'm looking up there. It's expensive. The reason why it's expensive is because it oxidizes in the air like really quick, so it's really hard to store. And it's dangerous to use. It's kind of like under the violent stuff, but dangerous to use. These are kind of your reasons to not use acyl chlorides and to use ethanol chlorides instead. Okay. Your mechanism for this, H3C, C double bond O, Cl, NH3, lone pair to the C, this goes off. Okay, this should be delta plus, this should be delta minuses. Okay, then single bond, Cl, 3 H's on the N, we don't want that. Okay, this is a plus, this goes off, this comes back, easy. You don't ever do mechanisms with anhydrides, to be honest. So yeah, I'm gonna avoid that for now, just because I want to go to chromatography. Okay, it's pushing 8 o'clock. All right. Let me just see if I've missed off anything. Huh? What do you want to repeat? That you go from, you always make HCl. You can also react this with what's it called, alcohols to make esters. And such. Okay. So additional elimination, I think is a really nice mechanism, to be honest. Learn this. The excess NH3 part. So the H goes away because you don't want 4 bonds on the nitrogen. Okay. Yeah, I'm doing chromatography, bro. I'm doing it. Alright. Last bit, guys. Chromatography. Well done for staying so long. Alright. I'm gonna use questions to really explain chromatography. But the way that chromatography works, essentially, let me actually do it without. The way that chromatography works, this is what you need to know in terms of the drawing part. Okay, you have a very thin layer, so it's called thin layer chromatography. Okay, you have a solvent, and you also have the starting line. The starting line needs to be above your solvent. If it's not, it will just get dissolved. It needs to be above. Okay, you put your samples on it, and then it moves up. When it moves up, you take off the thin layer. It can be made out of anything. Usually it's silica, but it depends on the question. And you draw a solvent line with pencil. Make sure you're doing these with a pencil. If you're doing it with pen, the ink will also spread up. Okay. Also, put a lid on top to prevent evaporation of solvent. Okay. Now, you have two things. You have something called the mobile phase, and it's something called the stationary phase. And you can have different affinities to those. Now, your stationary phase is essentially in this case, it's going to be the plate. And the mobile phase is going to be your solvent. And essentially, it's really how much they're attracted to each one. So for example, let's call the mobile phase hexane, and let's say the stationary phase is silica polar. Is silica polar? It's polar. Alright, cool, that's good. Silica. And silica is polar. Okay. Now what I'm gonna do is, let's say let's just use ink. I'm gonna call it ink 1. Okay. Ink 1 travels up. But then ink 2 travels up even more. This means essentially yes, Shah, yes it is. Yeah, you did I not put that? Yeah, there should be a minus there. Sorry guys. There should be a minus there. That should be a minus there. Sorry guys. One of them will be polar, one of them will be non-polar. Okay, it's really about the affinities. So ink 1 travels less than ink 2. That means that ink 2, because it's traveled up more, it doesn't want to stay. It doesn't want to stay down. That means that ink 1 is more attracted to the stationary phase. Don't say attracted, I should say more, has more affinity to the stationary phase. Okay, now just by using that knowledge, if we know that hexane, well, hexane is a non-polar molecule, right? So that means that ink 1 must be more non-polar, whereas ink 2 must be more polar because it wants to move. Okay, it really just oh, sorry, should be polar just because of this. But even if I swap them around, the stationary phase is your silica, polar, it stays. Ink 2 moves, non-polar, hates staying. Should I re-explain that? Because I feel like I just swapped it around by accident. Let me re-explain that. Let me quickly re-explain that. Sorry, guys. Ink 1 stays, likes infinity, or affinity to stationary. Stationary phase, as we know, is silica. Silica is polar. Therefore, ink 1 is more polar. Ink 2, more affinity to mobile phase. It likes to move, therefore more non-polar. Why? Because hexane is more non-polar. Calm? Let me scroll down a bit. I know it's a bit of a mess, but yeah. All right. 1 second. There we go. All right. Cool. Now you can also have thin layer chromatography for amino acids. Now amino acids. Now the difference with amino acids is that they are not really, they're colorless. Martina, it really depends. It depends more. It all depends on what it is. Hexane is mobile phase. Okay. Sometimes what they can do, they can give you a non-polar solvent. Okay. Stationary is what stays. So stationary is going to be your plate. Okay. Mobile phase is going to be your liquid. Silica, yeah, you expect to know it's polar, yes. Hexane is supposed to be non-polar, yes. Okay. Hexane, all your molecules, so all your hydrocarbons, if they don't have C double bond O's and stuff, if they don't have a double bond O, they're probably going to be non-polar. As soon as you bring an O here, as soon as you bring any hydroxide groups, that makes it into a polar molecule. Okay. Ethanol is polar. All right. In terms of amino acids are colorless. Okay. So what happens with colorless molecules is that you can't identify them straight away, so you need to use a locating agent. Specifically, ninhydrin is the best one. Ninhydrin and UV light. Okay. You can also use iodine, but I think this is the best one. Oh, why is it doing this, bro? TikTok, why are you doing this? Oh, there we go. All right. So for this, it says the spot just above the baseline labeled A contains a mixture of substances, blah, blah, blah. Identified developing agent, same thing, can be used to locate. So this is going to be ninhydrin. Okay, working out the RS value is actually very nice. Center, so that's going to be your center point. This is your distance traveled. Okay, divided by your total distance, like so. I'm going to call this A. That will be B. That'll be A over B, whatever that distance is. It is pushing up 5 hours. Yeah, key. Suggest 2 reasons why there are only 3 spots on the chromatogram. Because there are only 3 things that are going to be have affinity to the mobile phase, essentially. Okay, so only 1 second. Yeah, only 2. 1 second. Let me read this again. Which cannot be separated using this method. Identify that. Suggest 2 reasons why there are only 3 spots on the chromatogram. In the experiment, a student heats the peptide with acid to help hydrolyze it. With 4 amino acids. Oh, sorry. So 4. Okay, so originally we had 4. Okay, and why is it that we only have 3? So essentially, all the peptide has not been hydrolyzed. Okay, so we probably have a bit that's kind of like this left. Okay, and potentially to do with some affinities. So you can see that 2 amino acids may have the same affinity, so they might be overlapping. Same affinity to mobile phase. Alright, glycine and stuff, these are all your amino acids you don't necessarily know, but identify 2 amino acids in the hydrolyzed mixture that can be identified. That's just your RF value. Okay, it says, I didn't really answer this question properly, did I? Suggest a possible reason why the RF value of the compounds in spot A is low. Essentially, it's because it hasn't moved up much, so it's essentially to do with your affinity. Because it hasn't moved up much, it's going to be more affinity to stationary phase. That's essentially why. And then state why the structure of the peptide cannot be determined from a chromatogram, even if the identity of all the amino acids are shown. Is because don't know the order in which the amino acids are bound. All right. If you say same RF value instead of affinity, yeah, that should be fine. Yeah, that should be fine. It says so don't you say it's more polar? Yeah. You can talk about retention. You can say retention. You can say affinity to stationary phase. That's fine. Low RF value. You can say more. Has it told us about anything about the molecules? It hasn't said anything about the solvent name. So don't say talk about polar, but say talk about stationary phase. Okay. All right. Last bit. Let me pull up these questions. Actually, you know what? Before I do that, I'm gonna go over amino acids real quick. Just a small bit of amino acids in terms of azido ions and such. Let me pull up the formula book again. Give me a sec, guys. Okay. So what you can have is something called zeta ions. I'm sure you know about this. So essentially, zeta ions just means that, and this is a key bit, that the overall charge is 0. This is only for AQA. If you're OCR, you don't need to know this. But overall charge is 0. Actually, no, I take that back. You do need to know it for OCR. You do. Okay, so alanine, for example, let's use alanine. What you're essentially going to do is you're going to convert the NH2 to NH3. And then this becomes a COO minus and a CH3. You turn the top CH3, you turn the top carboxylic acid group into a COO minus, and you also turn the NH3 into NH3 plus. Okay, every single amino acid acts in the same way. However, you do not do this for every single carboxylic acid group and amino acid group. Okay, you only do this for these top bits. Why? Because you need the overall charge is 0. Okay, I did this in my exam, and I literally figured it out afterwards. This was in paper 3 of my exam. It was a multiple choice question actually. Only the top bits will be plus and minus. Okay, you leave the bottom bit for zeta ions. Okay, now low pH and high pH. Yes, you do, Jeremy. Yes, you do. Okay, low pH. So low pH is very, very acidic. It's very acidic. Okay, so if it's very acidic, you have loads of H plus ions. So what happens is, if I use alanine again, alanine is going to be, let me just draw this molecule again, fresh. Only, is it CH3? Yeah, only the NH2 gets converted. So this is going to be NH3 plus. Okay, when it's low pH. When it's high pH, it's really, really basic. So what happens is, only the C double bond OH converts into a C double bond O minus. However, in the terms of this, it does it to every single functional group. So if you had an NH2 on the bottom, it would also turn into NH3 plus. Okay, if you had a C double O C carboxylic group on the bottom, it would also turn into C double O minus. It does it to every single one. So it doesn't care about the overall charge in this case. It does it to every single group. Okay. These are ions, light work. Light work. Okay, let's quickly go over column chromatography. Now, column chromatography and all your chromatographies are, are very, very similar. Okay, in column, essentially you have beads. Okay, and you have two things. Again, you have a mobile phase. Deuterion, if it's deuterion with a more than one carboxylic acid, only the top bit. Only the top, because you need your overall charge to be 0. Okay, this is a column. Okay, column chromatography. All right, Dodo Bodo. Appreciate you for staying, man. We've got literally gas chromatography after this and we're finished. So column chromatography, you have two things in all your chromatographies. You have your retention, or sorry, your mobile phase, and you also have your stationary phase. Okay, now your mobile phase essentially will be a sample dissolved in a liquid. The liquid goes in pores, goes through, and comes down the bottom. Your stationary phase is actually the beads. Okay, so what happens is essentially the reason why you do this is to separate mixtures. That's the whole purpose of this. Okay, you have beads. They can be made out of silica. They can be made out of anything, and they'll tell you. Okay, and your mobile phase is a sample dissolved in some liquid. I'm going to choose silica for a stationary phase, which is polar. And I'm going to choose hexane again for your mobile phase. Okay, layers can form, yes. Layers can form. Overall charge is for deuter ions S. Now, let's say we have our sample. Now, if it's really, really coming out quickly, if your liquid comes out quick, what does that mean in terms of the affinity? Is it more affine affinity? Does it have more affinity towards mobile phase, or does it have more affinity towards stationary phase? Good, it's more non-polar BMZ, exactly. Okay, so if it's coming out quickly, exactly, guys, it's going to be more non-polar. Why? Because hexane is more affinity towards mobile. Okay, if it has more affinity towards your stationary, it will probably stay up there. Does that make sense? That's all your column chromatography is. It's just for separation. Okay. Now, in terms of your gas chromatography, no, Tiddy, no. It depends on the. It depends. It depends on the actual thing. It depends. I've seen questions where it's actually swapped around. They'll tell you. Usually, I'll say yes. Usually, it is, but it depends on the actual thing. They'll tell you it's dissolved in this. This is the solvent. Stationary phase is something else. Okay. Yeah. Okay. If they don't tell you, just use the phrase stationary. Use the phrase mobile. Okay. Don't mention polarities if you don't know the actual solvents. Do not mention them. In terms of gas, now gas chromatography, we actually went over this like around 5-6 o'clock. It's not really much different. I went over it more or less fully. But essentially, you have, again, your mobile phase and your stationary phase. Now, your mobile phase, what happens is a sample is dissolved with some gas. And usually it's a kind of inert gas, so usually it's an argon. Okay, but that's your mobile phase. Your stationary phase is your oils, so it's some sort of oil. So what happens is you put the gas through the machine. It's a really swirly machine, and within the swirls, essentially what you have is oil moving through. Okay, there's oil within here. Okay, now again, let's say this oil is, let's use hexanol even. Let's use hexanol here. Hexanol. Now hexanol is polar, right? Your gas, for example, argon, will be non-polar. So if it comes out, if the gas takes really long to come out, where is affinity more towards? Stationary or mobile? Takes long to come out. If it takes really long to come out, yeah, if it takes really long to reach the detector, is it going to be more towards stationary? Good. Amazing. So it's going to be more towards the stationary. Therefore, your sample is probably polar. Okay, and essentially what you have in each of those, you have something called essentially detectors. You have retention phases, right? And the longer the distance between the peaks, that'll tell you, okay, that means there's more retention. Okay, that's essentially how you find out. It depends on how far the distance between the peaks is. Sometimes you can have a mixture. So if you have a really, really close peak that comes out quick, that means it's going to be more in the mobile phase, therefore non-polar. If it comes really, really late, like you guys just said, it's going to be more towards the stationary phase, more affinity towards the stationary phase, therefore more polar. Does that make sense? Okay, that's all chromatography is. Mobile phase, stationary phase, that's it. Alright. They transfer over. Don't overcomplicate it. You guys know it. Alright guys, we're going to finish here. I'm going to make predictions. I wish I did have time for practicals, but I don't. But I'm really tired. Go over these practicals in depth. Okay. Specifically, specific heat capacity, discipline cross, and the iodine clock. Okay. You guys did really, really well. Smash tomorrow's exam. Let me know how it goes. Join my Discord in the description. Let me know how it goes. You guys have been amazing for staying so long. Yeah, you guys will smash it. You guys will hopefully smash it. Okay, everything that you learn, I've summarized it in the best way. Apply that content, and you're gonna do amazing. Okay. Yeah, man. Top tier, guys. Top tier, top tier. Come join my Discord, man. Come join my Discord. I'm always active there. We have a good community now. Yeah. Yeah, come on. My guy, yeah. I appreciate it, Dodo. I appreciate it. I apologize for the mistakes here and there, man. I'm only human. So yeah. You guys, by the way, Avarice, send me that 2024 paper, bro. I actually want to see them. I really want to see that. I haven't seen it at all. I've completely forgotten about it completely. But yeah. Alright, well then guys, I'll see you guys later, yeah? Take care. And this will be on YouTube as well, so for the guys on TikTok, you guys can literally rewatch